Welcome to the very first video of this series, Production Grade Go from Scratch, where we actually learn stuff, not just talk about how to learn stuff. And before we start, I want to make some things clear so that we have our priorities straight. And if people have questions, they have the answers right away. And if you just want to start with the content, just want to jump right into the basics of Go, you can skip it. You can find the timestamps below in the description. You can just skip right into it because in the first part, for the first few minutes, I am going to clear up some questions. I am going to give some tips. I am going to give some advice on how to make this whole process more efficient for you, less time consuming for you, and more smooth. That's my goal. I just want to make this whole process of you starting with the language Go and you writing actual projects, production grade projects with Go. I want to make that timeline as short as possible, as smooth as possible, as stress-free as possible, and as valuable as possible. And I hope you will enjoy it, and I hope you will learn a lot. Okay. And the first question is, what are we doing here? If you have watched the previous video in this playlist, where I explain what are the series of steps that we are going to follow in this playlist to go from scratch to writing production grade Go backends, then you will have some idea what are we doing here. So the idea is we are going to follow this resource, which is called the Tour of Go. This is recommended. This is one of the recommended resources from the Go official documentation, which gives a very high-level overview, a very high-level tour of all the features of the language Go, so that you are familiar with all the new concepts that come with the language, all the quirks of the language, all the syntactical concepts, all the syntactical differences with the other language. Basically, pretty much all the basics that you need to know to get started with the language, to have a very good understanding of the language, to write legit programs, useful programs in the language. Okay. And I have personally used this resource a lot of times, on and off, to get my basics clear. And that's why we are going to follow this one in this video. Okay. That's what we are doing in this video on a very high level. What we are exactly doing, I'll get to that shortly. So next, let's jump into the second question, which is, who is this for? If you're wondering, if you're watching this video and if you're wondering if this video is for you, then the answer is, if you want to learn the language Go without wasting too much time, without being a scientist, without being a master of the language, because unlike other tutorials, unlike other paid tutorials, free tutorials in Udemy, YouTube, where people dive into every single feature of the language, how every single concept works, the differences, the definitions and all. We are not going to follow that pattern. Those patterns are useful if you want to dive deeper into the language. But as I've already mentioned, the goal of this playlist is to start from scratch and to get to the production level project writing phase as fast as possible, as efficiently as possible, without going crazy. So that's why I have strategized how I am going to proceed with the series, and what are the steps that I can skip now, what are the steps I can add later, what is the most optimal sequence of the steps, and everything. I have thought a lot about how to structure this and how to make this as painless as possible. So yeah, so if you are here to learn the basics, or if you're here to revise your basics, because as we learn a new language, a lot of time it happens that you start with it, you learn all the basics, then you get busier, and then you leave it for some time. Then you come back after 2 months or 3 months. You have some idea, you have some kind of, you remember it in a very light way. So in that case, if Go is that language for you, where you have explored a while back, and you remember some of the concepts and you just want to revise before you get started with the projects, then this is also for you. Because what we are going to do in this video is we are going to go over all the basics in one video. I am not going to stretch it out to part 1, part 2, part 3, part 4. No. That's just waste of your time, waste of my time, and it gives people the idea that you have to learn a lot. I want to change the psychology a little bit. You can learn the basics in one video. You can learn it in one video, and we'll dedicate other videos to other areas of the language, best practices, how to structure your projects, how to read code and stuff. But I believe in long form content, even though YouTube algorithm favors short content because people have less attention span. But I am going to stick to this style because this works best for people who are serious, and this gives the idea that you can do it in one video. I think that's more important. Okay, so that's about who is this for. If you want to learn the basics of the language, if you want to revise the basics of the language with a single video, with the most efficient way and the fastest way, this video is for you. What are the prerequisites of the video? The prerequisites are, it's nice if you have experience in some other language, or if you're a computer science student or you have done a boot camp, or you're just curious and you have learned the basics of programming. You have done some kind of programming. It does not matter you have written big applications, big open source applications or big production style applications before. It does not matter. As long as you understand basic concepts of the programming, stuff like what are variables, what are arrays, why do we need loops and all. Because that is way too fundamental of concepts for me to get into and way beyond the scope of this video. So as long as you have some understanding of programming concepts, then you're good to go. This you can jump right in. Okay. Then what is this video? This is kind of similar to what are we doing here, but this video is basically a complementary resource for the tour of Go, which is a recommended resource while people are learning the language Go. So this video is a complementary resource to that resource. So it is not a replacement. It is definitely not a replacement. None of my videos are replacement to any of your typical tutorial or practice or projects, anything. I'm just here to guide people. I'm just here to share my experience of how I did it, how I think you should do it, and what is the most optimal way of doing it. So that's I want to make clear. None of my videos are replacement for any of the other resources on the internet. I just want to make things easier for people, and just that's it. So yeah, this is a complementary resource, complementary video resource for the tour of Go exercises. Okay. And what I am going to do in this video is I am not going to write code. This is tour of Go for your information. And here there are a lot of exercises, example based approach to demonstrate all the features of the language Go. It covers pretty much everything that you need to know as a beginner to get started with the language. And what I'm going to do in this video is I'm not going to write code because one of the reasons for me deciding not to write code is this is from my experience. What I have noticed is when we watch tutorials, when we watch Udemy courses or big tutorials in YouTube. So what do is we just take our coffee, we get comfortable, we slide back and we watch the other person write the code. We get very comfortable and our mind tricks us into thinking that we are the ones who are writing the code, or we now know how to write the code ourselves. So we don't put that effort anymore. So I want to avoid that situation because this is the universal truth. Programming has a lot less to do with your brain, your genius or your talent. It has nothing to do with that. A good coder, a good programmer is basically someone with a good pattern matching skill. What I mean by pattern matching is they have over the years or over the time, they have developed this ability to use the right tool at the right time. For example, if you're a programmer, then the moment a problem like let's say you have a string which is comma separated list of strings and you want an array. So if you're a beginner, don't worry about it. I'm just giving an example for people who are already experienced with some kind of programming. So the example is you have a comma separated string. It is a bunch of strings which are comma separated. The moment you see it and you want to obviously parse it in some kind of array, the moment you see it, instantly the function split. Now it can be any language, Python, Java, Go, JavaScript. I'm pretty sure every language has some form of the implementation of the function split. The moment you see it, the function split comes to your mind and you apply it, you have your array, which is an array of strings. Now you split the array, you split the string which was comma separated into an array of strings, because that is some form of pattern matching. Because over the time, after using the same pattern again and again, you don't have to worry about it anymore that what to use. So pattern matching is basically the skill of using the right tool at the right time at the right place. And it has nothing to do about your genius or your talent or basically nothing, no mathematics, nothing. Just code velocity that I usually what I call. The more code you write, the more code you read, that's your pattern matching keeps improving. And it just comes naturally to you. It's like muscle memory. There's nothing to worry about. Just trust the process. So the point is, in this video, I am just going to copy paste all these examples in my local IDE editor. Also, I'm not going to go through how to install Go in your local system, because you could have an Windows system or Mac or Linux and all. So that is also out of scope for this video. We are not going to waste much time. So I believe that if you're serious about learning a language, you should be able to figure out that part yourself. You will find all the instructions that you need for installing the language and configuring the language in your favorite editor. It could be VS Code, or you can use Golang from IDEA or NeoVim. Does not matter. I hope you can do that on your own. That is also not covered in this video. So I'm going to copy paste all these examples in my local editor, and I am going to just go through them and give my insights, and we'll run the examples, and I'll go through all the concepts while I run the examples and give my own insights from my own experience of the language over the years. And with that, one more thing that I'm planning to do in this video is, while I'm explaining some concepts, for example, while I'm explaining packages, we'll see how packages work in real life projects, when open source, actual production grade projects that people are building businesses around. I have cloned some of the open source GitHub projects, some of the famous ones. I'll show how these concepts, these basic concepts, we'll see basic examples first from the tour of Go example. Then we'll jump straight into how it actually applies in a real world project, in a real world complex open source production grade project. Okay. So you get familiar with the concept and you see the use of that concept in an actual real world environment right away. There is no gap there. You don't learn the concept, then you don't write basic CRUD APIs, then you see how production grade projects work over the years. No. We are going to shorten that gap to seconds, from years to seconds. You are going to see how good code looks like right away from the very first Go basics video that you're watching. And this, I feel, is no one is doing in the market, any tutorials and any Udemy courses or anything. At least I have personally not come across that myself. And I think that is a very important and crucial resource that people are missing, because until you see how a concept is actually getting used, imaginary and hypothetical examples are only going to take you so far, because you're always stuck in imaginary examples, and it's a waste of time. So I am going to shorten that gap. You're going to see a basic example and jump right into real world examples. Okay. That's another thing. So that is your answer to what this is, what this video is all about. Next question is what this is not. What are we not doing here? We are not, at least I am not making a typical traditional tutorial where I explore every single corner of the language one by one, give examples and waste 30-40 hours of your time. That's I'm not doing. I am going to keep this relevant. I am going to keep this relevant for specifically backend development. All the concepts that you need to know, that you need to understand to get started with real world backend servers, real world backend based projects in the shortest time. So this is not your typical tutorial. I'm not an expert. I'm not a teacher. I'm not a Golang expert. I am a backend engineer myself, and I am just sharing my experience of how I learned the language in the most efficient way. And that's it. It is not a traditional tutorial, and that should not be your expectation in the first place. That is clear. And the last question is, how should you follow it? My advice is, before you watch this video, you can pause now. This is what you should do. You should pause now, and you should go to this resource, go tour of Go. You can do a Google search and find it. And you should do all these exercises. These are very simple exercises, and it follows this format that on the left side, they have explained the concept, and in the right side, when they have an example, and you can run it here and you can see the result here. This is the typical setup that they have in this website. So my advice is, you should come here, you should finish this whole tour of Go exercises on your own by studying the concepts and running the examples. It will max take you 2-3 hours if you are doing in a one sitting, and it is nothing that will make you go crazy. It is very basic set of examples. You should be fairly comfortable with doing it. That's the first thing you should do, and you should not worry about understanding the concepts and all. Just do it. Just go through with it. It does not matter your level of understanding after doing it. After you do it on your own, and then you should watch this video where I go through the same examples. I follow the same examples. I explain the theory in my own language, in a language that I think gives people more scope of understanding, with my demonstration of real world examples and all. So what this process will do is, once you write the language yourself, once you explore the language, once you read all the concepts yourself, you will put some effort and you will develop some kind of muscle memory. You will get the feel of the syntax, how this new language feels. That is a very important step. Before you understand the concept, you should have a feel of the syntax. That's why I say, do it yourself first, then watch this video, then try to understand what's happening while I'm explaining stuff. That's the pattern. You should do it, and that's all you should know about it. Okay, and before we start, some other things, some tips that I want to, some advice, some tips that I want to give people is, since you're starting with this new journey of learning the language, these are some of the things that you should keep in mind. First thing, don't freak out. Okay, Go has a lot of concepts. Go has a lot of novel concepts that are very different from other languages. Or if you're coming, if you're a fresher, or if you're coming into programming, if you've only started programming in college, Go has some complex concepts. So my advice is, don't freak out. Does not matter how complex a concept seems, because at the end of the day, it's all about pattern matching. That's one thing I want everyone to understand. Being a good programmer is all about using pattern matching to your advantage. So this is a secret that I want everyone to know is, when you're learning a new language, the worst thing that you can do is trying to understand everything. Don't do that. That will only freak you out. Of course, if you have, let's say, 5 or 6 years of experience in different languages, then the first time you learn a new language, everything will just click and you will understand everything. And this concept does not apply to you. But if you're starting out, trust the process of pattern matching. And what that means is, the more you see the language, the more you read the language, the more you write the language, does not matter initially that if you understand everything or not. As long as you're writing it, as long as you're reading the language, you will get there, and you will get there before you know it. So trust the process. Don't freak out. If you don't understand something in this video, you will understand it in a later video while we are exploring the standard library code, while we are exploring the real life examples of open source repositories, while we are reading the code there, or while you are making projects. So there is a lot to cover here, and a lot of resources that we'll cover, a lot of tasks that we'll do, and over the time you will understand it. So understanding should not be your priority. Your priority should be pattern matching and consistency, and pattern matching will improve with your consistency. So try to write as much as possible the language. Does not matter if you understand it or not. Try to write it, try to get the feel of the syntax, and try to read as much as possible the language. And once you start building the projects, everything will just start clicking. You'll connect all the dots, and before you know it, you'll be very comfortable with the language. So that's something I want people to understand about how to learn, not just Go, not just this, any concept in programming. Just know how to do it. Just get started. That's why the getting started section of any documentation is so important. Once you get started, once you use the thing, it becomes very easy for you to understand the thing. It becomes very easy for you to understand the theory behind it. But first you have to use it. You have to get the feel of it. The feel is more important than the theory or the concepts. Okay. First thing. Second thing. The first thing was about how to learn programming or new languages in general. The second thing is about Go. My advice for people who are learning Go as their first language, or they're coming from a second language to Go, is Go has some advanced concepts. I won't say advanced, but very new concepts as compared to other languages. So concepts like interfaces, or the value-based error handling, or concurrency. A lot of concepts in concurrency, different patterns, fan out, fan in, or mutexes, read mutex, write mutex, and select case, channels, read, send channel, receive channel. A lot of concepts in concurrency. What happens is, this is something that I have struggled a lot when I was learning Go. What happens is, when you're learning, we'll follow some tutorial, or we'll follow the official docs, or some YouTube video, everything. And all those resources, pretty much all those resources will have sections where they will go very deep into interfaces, concurrency, reflection, all these advanced concepts. We can say it advanced. As a result, even though those advanced concepts are only 20% of the time that you will actually use. Now, interfaces is something that you will use a lot compared to the other concepts in the language that you will mostly write. We can say 80% of the stuff that are very simple to understand, that are very simple to use, are the 80% that falls into the 80%. And the rest 20% of the stuff, the esoteric stuff, the concurrency primitives and the advanced interface patterns and all the abstractions, generics and all, those fall in the 20%. Especially since we are making this playlist for backend development as a application developer, not a library developer. Okay, this series is completely focused for an application developer. People who will be writing APIs, who will be developing backend applications. Okay, so for them, especially for them, initially when you're starting out, I'm not saying don't understand these concepts ever. When you're starting out with the language, you can ignore interfaces, concurrency primitives, reflection, testing, and all this. Testing is important. I believe testing is important. Don't ignore it. But we will get to that when we are making projects. But when you're learning the basics, these concepts are blockers. These concepts are blockers because they make you feel that Go is a very complicated language, very complicated systems programming language, which it is. And also it's not. It has two sides. For an application developer, you can go a long way. You can work for years without actually working with advanced concurrency primitives like fan in pattern, fan out patterns, and select channels and all. You can actually do that. You don't have to master all the concurrency patterns as an application developer. If you want, of course, you can master it. Of course, you can do it in your applications, but you don't have to do it. Okay, and that's my advice. Don't freak out when you're learning these concepts. Just know that they exist. Just know that where do we need them, why do we need them, and when we're using libraries, those libraries are internally using them, but you don't have to use them right away. You have to use them at some point when you are working on some advanced features and you need these primitives to your advantage. But as you're starting out, you don't need them. You need them. You need them indirectly. You'll be using them, but do them in the mindset of pattern matching. You're doing it just for the sake of doing it, just because I told you to do it. Don't try to understand everything. Don't try to wrap your head around all these concepts. Just trust the process. Just believe the process that eventually you will get it. Okay. That's one mindset that is going to set you apart from a lot of developers who are starting with the language. Because once you get intimidated with the language, once you get intimidated with all the advanced features of the language, you'll drop it. Of course, you will drop it, and you'll drop learning it, and you'll move on to whatever language you usually work with, or you will move on to some other language, which is obviously not what we want. We want consistency. We want to get pattern matching as far as possible. So that's my 2 advices for people, 2 tips, if you can say that. So with that attitude, with that mindset, we can start with the resources. Couple of points to keep in mind before you start. First, don't try to understand everything and don't try to remember anything. You don't have to remember anything, because eventually you will learn all the patterns and it will come naturally to you. And if you don't understand anything, just move on and trust the process. You will get it eventually. Second, while I'm explaining some concepts, I will be showing real life examples of open source repositories, how people out there who are building startups around the Go programming language, who build servers using Go in real world, in production grade projects. I'll be showing examples from there. So while I'm doing that, please focus on the parts that I am showing at the moment. Do not try to look at the code around it and get intimidated. So just focus on what I am showing, and eventually by the end of it, we'll learn how to read all the code of different open source repositories from end to end. Okay, cool. And now this is our first Go program, and before I explain all the concepts, let's just run the program to see if it works as expected or not. So to run a Go program, we can do go run and the name of the file. And we can see in the console, it says hello world. By the way, this character, this is in Chinese, which means world. And I will explain soon why did we write it in Chinese instead of just world in English. Okay. Now, first thing that we see here is a go.mod file. Now, what is a go.mod file? If we look inside it, we have a couple of lines. The first value is the name of the module or the name of the project you can imagine. And the second value is the current version of the Go, or the version of the Go that the project depends on. It does not necessarily mean this is the version that you have to install in your system, but this is the version that this project, that this program depends on, this particular version of the Go. Okay, that's what it means. Now, why did we need a go.mod file in the first place? It has a couple of use cases. First thing, if you have a project, then obviously you have to name it something and you have to document the name somewhere. So that is the natural use case of a name for a project, and that we can record here in the first line of the go.mod file, the name of your project. Now, as convention, the name should be unique and it should have a prefix with your code hosting provider. And by code hosting provider, I mean it can be GitHub or GitLab or Bitbucket or anything. That is by convention, because a Go program or a Go project can be of two types. It can be of two types. Now, first type can be an executable, and the second type can be a library, or we can call it in Go's terminology a package. Now, an executable program is something that we run. For example, since we are learning about backend technologies, our programs, our Go projects will be in the category of executables, because we'll write the code and we'll run it. We'll run it in our own system, and that's how it will work. That's why it's an executable. In the same way, for people who build libraries or packages, those are the code that get imported into other people's Go projects. For example, there are a lot of packages in a standard library that we will see soon that we import into our project. For example, FMT, that we'll soon see, is a package provided by the Go standard library, which means those are the programs that those are the code that we do not have to explicitly install in our project. They are available to us by the Go runtime. Now, those are the packages that we use in our program or in our project. They fall under the category of packages. In the same way, we also use a lot of external packages for building web servers, for doing validations, or for managing our configs. A lot of external packages that we will use when we are building projects, right? Those are called packages because someone has built them and they have distributed it in GitHub or other hosting providers, and we can import it into our project, which is an executable because we are running our project and we are importing the packages. So you import packages and you run executables. Those are the two major categories that you have to notice. Don't necessarily have to remember, because obviously you'll be mostly working with executables if you are building backends. That's something to remember. Okay. Now here we are building an executable. Okay. So next, after these two lines, the name of the module and the version of the Go language that the project depends on. Later on, this will also have all the dependencies of the project, all the external packages that this project depends on. That will also be recorded here in the go.mod file. So by convention, as I said, the module name should be a name of the project prefixed by the code hosting provider. So ideally, if we delete this go.mod file, let's delete this. We can generate it again using the command go mod init. By convention, this is how you name your projects. .com/my username seriously /pggs. Okay. And a go.mod file is generated here, and the module name is taken from the command. So this is a conventional module name of a Go project or a Go module. Okay, that's all you have to remember about go.mod files. It has a module name, which is the name of the project prefixed by your code hosting provider. It has the Go language dependency that the project depends on, and it has external dependencies recorded here with the version numbers, so that over the time when we are adding external packages. So okay, let's just see a real world example, then I can explain better. Now if we go here, this is a project called Fider. It's an open source project for a platform, it's a feedback management platform, and it has very good Go code in my opinion. They follow a lot of conventions, a lot of idiomatic Go writing practices. That's why I often come to this repo and I study it for learning and for referencing code and different kinds of stuff. During the course of our videos, we will be following some of these good open source repositories so that I can show how these concepts work in the real world, so that you don't have any abstract idea or hypothetical ideas about how these concepts work. We'll see exactly how they work and how you will use them. And yep, So let's just see how the go.mod file looks for a real world project. So again, as I said, this is the name of the project provider prefixed by the code hosting provider, which is a github.com, and this is the organization name or username, whatever is applicable. And this is the version of the Go that this project depends on, or the minimum version of the Go language that this project needs. After that, we can see these are all the external package dependencies of this project with the exact version number. So when we run this command called go space get space the package name, for example, we run go get github.com/aws/awsdk go. When we run this command, it appends that package in the go.mod file with the version number, with the latest version number, or if you specify a version number, it appends with that version number in the go.mod file, so that the next time we share our code in the hosting provider and someone else in our team, they fetch the code, they clone the repo in their local, and they can run the command go mod download, and all the packages with the exact version numbers will be fetched in their own local system, and they can use the project without explicitly doing go get this, go get this, go get this, go get this with the exact version numbers. They can just run one command and all the dependencies will be installed. So that is one advantage of using recording all the dependencies of your project in one file, a go.mod file. Those are the three major use cases of a go.mod file. It has your project name, it has the minimum Go language dependency, and it has all the external packages with the exact version numbers. That's all you have to remember. We won't have to manually change contents of this file, because we'll be mostly running commands that will make changes here. Unless we want a specific version of any package, then we can come here and make some changes in the version numbers. Otherwise, we will most likely never touch it. Okay, that's all to know about a go.mod file in a basic example and in a real world example. Now let's go back to our example. Now let's jump into the main.go file. Okay, now couple of things to notice here. We have a package declaration, we have imports, we have a function which name is main. We are using the imported package here, and we are calling this function println, and we are passing a string which gets printed in our console. Okay, that's what happening here. Now to dive deep into what exactly is happening, we have a main.go file. Okay, the first thing is the package declaration of a package called main. Now packages in Go are there to organize our code in a meaningful way, in a useful way. Because what happens if you just write your code in one big file, you keep writing, you keep adding functions, and you use all the functions in the same file. It works. If it's a small program, you just want to run one script, it works, and it works quite effectively. But the moment the program starts getting bigger, you add thousands of lines, you add millions of lines, you add billions of lines. At that scale, the program will get impossible to read, and it will get impossible to debug. And naturally, that's why a lot of programming languages have different techniques to organize code in a meaningful way. If we come from JavaScript, we have imports and exports, CommonJS modules and ESM modules and all these concepts. In Go, we have modules and packages. Module we already saw. If you're starting a new project, we'll run one command called go mod init with a unique project name prefixed by our code hosting provider. That's all about module. You never have to think about module in a project ever again. Assuming you're working in a typical backend based project, not on libraries. Now, second thing in the hierarchy comes packages. And that's pretty much all Go has to offer in the code management department. So packages, now the rules are every Go file, every file that ends with the extension .go, it does not matter what the file name is. Every Go file will start with a package declaration. It will declare which package it belongs to. Okay. Typically, in a big project, a project which follows a typical Go project structure, the directory, the folder name of the folder name will often match the package name. Now, that's the first line, the package declaration. It says that this file belongs to this package called main. Now, the rule is, if you are building an executable, a program that will run in your system or in a cloud or anywhere, program that will run, it is a kind of a script. It will run and will have outputs and logs and all. If it's an executable, it has to have one main package, and inside the main package it will have a main function. And why is that? Because this function is the entry point of the program. And by entry point, I mean when we compile this package or when we run this package, this is where the execution will start. And the main function will call other functions and it will have different components and all. But this is where the program will start executing from. Okay, that's the rule. An executable, then it will have a package main and it will have a main function. Now, the directory structure and the file structure we'll focus on later when we are studying other projects or when we are building projects. For now, just focus on this part, the code part, not the folder structure and file. I will explain what is the ideal way to structure your files, what is the ideal way to structure your folders and all. We'll follow all the idiomatic Go recommendations. Okay, that's all about package. Package are a way to organize our code, to divide our code in different files so that it is easier to manage. Okay, and it also offers some kind of properties like encapsulation and all that we will see soon. Next line, we have a import statement which imports a package from standard library because our project name is github.com/pggs. Okay, pggs. Since we are not importing from our own module from a different package, and we are not importing from an external package, this does not have any prefix or anything, which means it is coming from standard library. That's just how you can understand if it is coming from standard library or an external package by looking at the prefix, the hosting provider, if it's there or not. Because all the packages from the standard library, from the Go's own standard library, is already defined in your Go runtime. You don't have to explicitly install them. You still have to import them, but you don't have to install them. So the second part is the imports. We are importing the package fmt. Now the package fmt has a lot of functions all related to print or string manipulation, everything related to strings. For now, that's all you need to know. We'll see what are the different functions provided by this package fmt. For now, we will just look at the println function. Okay, that's all about imports. Next, we have a function. Now, functions, people who are familiar with programming concepts, functions are a way to group logically related code statements or expressions so that this function is callable and this function is grouped into one segment. Something like that. That's a typical definition of a function that we don't need to understand in a very deep way. It's just a function. And the name of the function is main. And as I said, every executable code has to have a function named main because that is the entry point. And now inside that, we are running this line. And this is using the imported package fmt dot. And using the dot, we can access the variables, the different functions of a package that the package exposes. Okay, and here this is fmt.println, and we are passing the string hello in Chinese world, and we can see the string when we run it, when we run the program. Now another thing to focus here, this p here is in capital letter. It is not small p, and that is important. It is not case insensitive. This is definitely case sensitive, and why it is capital we'll explore soon, but that's something to notice here. Whenever you are accessing functions, variables, interfaces, structs, any data types from a package from a different package, it always will be in capital form, the first letter. That's how we know that is exposed. Okay, otherwise you cannot access it. That is the Go's mechanism of exposing data outside of a package from inside a package. The second thing, now another thing to notice here, why did we write Chinese here? To express the concept that Go is a language which supports UTF-8, which supports UTF-8 encoding characters, which means previously in previous programming languages, they mostly supported ASCII, which is a character encoding format, which has a mechanism to express up to 127 characters, which consisted of lowercase English letters from A to Z and uppercase English letters 0 to 9, and some special characters like at and end, stuff like this. Only 127 characters, which is of course very limiting, because in our world there are like a lot of languages, and a lot of languages have a lot of different types of characters. So programming languages had to support them. So when people were designing Go, they came up with this character encoding scheme. This falls under Unicode character encoding system, which you can study more about. And UTF-8 is one encoding scheme, which almost supports, I think, around 120,000 characters from across like almost 1,000 different languages across the world, so that inside a program we can express a lot more types of characters. Okay, that's why we use Chinese here to show the fact that Go has support for a lot of characters, unlike previous languages which were only limited to ASCII characters up to 127. Okay, that's all to focus here. Now for this program, that's all the concepts. We have a package declaration, we have import statements, we have a function main, and we have used the package, and we have accessed this function from this package, and we have printed this statement, which is a string. Okay, and we can see this in the console. There is another way to run this program, to build this program. So to show one of the features of the Go, so what we can do is we do go build main.go. What it does is it generates an executable. It generates an executable, and we can run this executable using main. And here we can see the same output. What happened here is Go provides a feature which is called cross-platform single binary executables, which means a Go program can generate a executable binary, which means you can take this file, you can take this whatever main file whose name resembles the name of the file. You can take this executable and you can run it in any Mac operating system, the operating system that matches mine, because during the build command I did not specify which operating system or which architecture I am building the executable for. If I did mention it, then we could take this executable file and we could run it in that system. Let's say we want to generate an executable for a Windows operating system from a Mac operating system. So this is the command we can use. We can say operating system was Windows and Go architecture is AMD 64, and the typical Go build. We can mention the file, or we can just say dot, and it will take the file by default. If we do this, then it will generate a file called pggs.exe, and if you are aware of it, .exe is the Windows executable file extension. Now you can develop your backend in your system, which is a Mac operating system, and now you can compile that code using Go build, and you can compile that code for a Linux operating system or a Windows operating system. And now you can send these binaries. Now you can send these binaries to other system, and they can just directly run it, and they will have the same results without installing Go explicitly. Because when we generate an executable, all the Go runtime, whatever dependencies that are needed by the program, that gets embedded into that single binary executable, and that gets distributed across different systems. So this is a huge advantage that Go offers, that you can run a single command and you can generate different executable for different operating systems from any operating system. Okay, now let's delete these. Now another question to ask here is, what is the difference between the command go run and go build and running that executable? So the one line answer to that is, while you're developing, you should use the go run command. And what go run command does is, go build, it goes through your code, it compiles all the packages, and it does all the linking and all, and in the end it generates the binary. What go run command does is, it goes to the code and it compiles all the package, and it directly runs your system without generating a single binary. It directly runs your program with a temporary binary somewhere in the system. And it is relatively faster because a go build command, after compiling all the packages and linking and stuff, it throws out all the results of the compilation into the garbage. It does not store anything. It does not cache anything. The next time you run go build, it again starts from scratch. That's why it's a little slower process. Now go run, what it does is, after compiling and after linking, it saves that result somewhere in your system. And the next time you run go run, if nothing has changed in those files, the results will be faster, and it will use those cached results to compile your program faster and to run your program in faster. So that is one advantage of go run. When you're building in your local, when you're developing your application, you will typically use go run instead of go build, which you will usually use when you're deploying your application, when you're distributing your application across different systems, in your CI/CD pipelines or in cloud development environments. Typically, we use go run command to run the project, to run the program in our local. Okay. Now moving on to the second example, we have one little change here. We are using another package called math.rnd, and this is a package which we can use to generate random numbers and typical functionalities like that. And again, we are using the same println function from the package fmt, and we are printing a random number between 1 to 10. Okay, and if we run this program, go run go, we get a number 9. And if you run this again, we get 3. If you run this again, we get 3. Again, it's 0. So basically, every time we run the program, we'll get a random number between 0 to 10. Okay, that's just a basic example. Now, another thing to focus here, the reason we are looking at this example is this part. When some packages, most packages will have these prefixes, the path the package can be accessible from, but those are not the important parts. The important part is the last part after the slash. So that will be the name using which you will use that in your own program. So because the last part was rand here, that's how you referred it, rnd.intent. Now, because of that, because of how we access the packages using the name of the packages throughout our systems, the convention, the standard practice, the best practice to name your packages, first thing, the package name cannot be capital letter. It has to be small case, like we have here, the main package and the fmt package and the rnd package. All the package names have to be small case. The second thing, the package names have to be as short as possible. Now that is not a rule, but it is a convention, because since when you import a package, it can be an external package or it can be an internal package from your own project. You will use that package using that name throughout the execution of your program. So you don't want to write a 10 letters package name again and again and refer it by that name, because that will be very cumbersome. That's why it is advised that your package names should be as short as possible and all small case. Okay, we can take a look at how people name their packages in a real world example. So if we go to our Fider project, now we can open any projects. Now again, Don't focus on the folder structure and all the code. Just look at the package names. Here you can see the package name is actions. The package name is action tests, is actions. Now, as I said, typically the package name matches the name of the folder. Now, as you see, there is a folder named actions, and all the files inside that will have the package actions. Apart from the test ones, we have not gotten into tests yet, but this is how people name their test packages, using underscore test. So all the files in this folder will have the same package, actions. And as you can see, it's small case and it is pretty short. Similarly, if you go to handlers, we'll see handlers. All the files inside the handlers folder will have the package name handlers, any file you go. And it is also pretty short and it's in small case. Same way, if you go to webhook folder, the package name is webhooks, it matches the directory name and it is a pretty short name. So that's what I wanted to show. In real projects also, when you see the package names are all short. As you can see, this is how people import the packages. If they have multiple packages, instead of writing import crypto RSA, import crypto RSA, sh1, this is a format we typically follow when there are more imports in a Go file. So we write an import and there is a starting braces and there is an ending braces, and all the package names are written in different lines. And as you can see, the last part, the IDE here, VS Code, it highlights the package names here, and it makes it easy to understand. But even if you're working in IDE which does not do this, then also you can refer to that package using the last part, the last component, all the package. And the conventions that I was mentioning, the package names are short and they're in small case. Okay, that's all you have to remember. There are packages and they have to be named in small case. The name has to be short and they have to match the folder names. We have not got into folders yet, but that's something to remember that we'll use in the future. Often packages reside in a folder which matches the package name. Okay, great. Now going back to our own example, that's all here to notice. Okay, now let's go to that. Now in this example, we are importing the package math from the standard library, and we are trying to access a variable named pi from the package math. The rest of the things are pretty much the same. We have the package declaration main, we have the import statements, we have the function main, we are printing something. Okay, the structure is pretty much the same. Now we are doing something new here. We are trying to access a package name. We are trying to access a variable from a package math. Now if we hover, as you can see, there is an error here, and if we hover over it, it says undefined math.py. But we know that there is a variable named pi inside math package. And what happens if we try to run this, and you can get the same error, undefined math.py. Because we are using VS Code and it has support for the Go language, it has the LSP integration, we directly get compile time errors in the IDE itself. We don't have to run it explicitly to get these errors. So that's one advantage of using a IDE which has first class support for the Go language using the extension. Now the thing to focus here is, as I mentioned earlier, whenever we are accessing a variable, a function, an interface, a struct, an array, whatever the data type is, from a package, from inside another package. So we are in the main package right now, and we are importing the standard library package math, and we are trying to use a variable called pi from the math package. In this scenario, when we are in a different package and we are trying to access something from another package, the name will always have to start in capital letter, because all the variables, all the data types that start in small case, those whose names start in small case, they are hidden from external access. Only those data types whose names start with a capital case are accessible from outside the package. So this is one example of Go's encapsulation technique. So if you come from a programming background and typically object-oriented programming, you're familiar with the concept encapsulation. It is a technique to hide the implementation of private variables and stuff. So Go offers something like that. You should not think in terms of object-oriented programming when you are coding with Go, but if you want to relate, you can think of this as encapsulation. So for this to work, we have to make this capital case. We make this capital case, and now if you hover over it, there is a variable, there is a constant named pi, and it is a float type. We will explore data types soon. And now if we compile it, we can see the result here. It prints successfully because we are now accessing it using a capital case letter instead of the small case, because a package data types are only accessible outside of the package using capital letter. Okay, that's something to remember. In this example, we are looking at custom functions. The main is also a function, but there will be thousands and millions of other functions in a typical life cycle of a program. Now we are looking at one of those functions, how to define functions in Go. Now this is the structure a function follows. First, we have the keyword func. That's how a function starts. Then we have the name of the function, whatever name. Typically, we give a function, the name of the function. Then we have a braces inside which we'll have parameters, and the parameters will follow the structure, the name of the parameter and the type, comma, the name and the type. Okay, that's the structure we'll follow for parameters. Then we will explicitly have to define the return type of the function. It is mandatory to define what type the function will return. Now we'll explore data type soon, so nothing to worry. Just focus on the function part here. We'll define the return type here. Then we'll start a curly braces in the same line. Then we'll write all the statements here, and we'll end the curly braces. This is how the typical structure of a function looks like. And now we can call the function inside println, and we can provide two arguments of type integer, because we have defined this is an integer type, because Go is a statically typed language, which means all the types are verified and they are checked during compile time. So now if we try to provide a string here, and if you hover, it says cannot use h untype string constant as an integer value in the argument to add. So since it is a statically typed language, Go is a statically typed language, we can only use the defined data types that a function accepts. We cannot use random any data types. See, it has to be an integer. Okay, now if we run this, we get the result 49. 42 plus 7, 49. And that's pretty much all you need to know about functions, how to define functions. So this is the structure you have to remember. It will have a func keyword, the name of the function, then the parameters inside the braces. The parameters will follow the structure of name, then type, name, then type. Then it will have a return type, and inside it all the statements. Now we can modify this function a little bit, because both of the parameters are of type integer. Now what we can do is we can write x comma y integer. Now this is also an acceptable form of writing function parameters, but in my opinion, I prefer the earlier type, because it on the first look it explicitly says x is of type integer and y is of type integer. Now it is a little easier to our eyes. It is more readable, and less likely someone will misunderstand by looking at this. Just my preference, but of course you can write the other way also. If both the parameters are of the same type, then you can get rid of the type of the first parameter and add it to the end of second parameter. Okay, that's all about the structure of the function. Go has a feature that a function can return multiple values from inside it. And to demonstrate that, here we have a function called swap. It takes two parameters, and it's in the merged form, where both the parameters are of type string. So we have removed the string type from after x to, we have merged it here after y. Okay, it takes two parameters, x and y, both of them are of type string, and it returns two values, And when we return more than one value, we have to add braces here. Okay, if it's a single value, we can write just string without the braces. If it's more than one value, we have to write braces here. It returns two values, both are of string. And what it basically does, since we are swapping, it takes x and y and it returns y and x. Okay, and we can use the swap function here, and we provide it two arguments. One is hello and second is world in this sequence. And we can take the values returned from this function. So it returns two values. Now we can use this structure, the comma separated variable structure, to read both the values returned by the swap function into these new variables. Now we'll get to what's happening here soon. But for now, let's just focus on the multiple return values. A function can return multiple values, and to read that, we can use this structure, a comma separated list of new variables, and both the values will be read into these variables in that sequence. So y will be inside A and x will be inside B. Now world will be inside A and hello will be inside B. And if we try to print it, when we run this program, we'll get world hello instead of hello world. Okay. Now, the only thing to focus here is Go has the capability to return multiple values from a function. Okay. Now there is another way to define your return values in a function. So we have a function split here, which takes one parameter of type integer, and the parameter name is sum, and it returns two values of type integer. But instead of writing it like this, int comma int, we have written it like this. What we have done is we have named those return values with x and y. And with this structure, what happens is when we name our return values, those two variables are initialized. They are initialized with their zero values. Since it is an integer type, now with the start of the function, before anything is executed, before the first line, two variables are implicitly declared. Now we have x equal to 0, y equal to 0. Now, because of that, if you see here, we are not initializing a variable anymore. We are directly assigning it. We'll get to the variables right after this, but for now, let's focus on the return values part. Both the values are implicitly initialized, and now we are assigning values to those two variables, x and y. Okay, we are assigning this. Now, because of that, we now don't have to write return x comma y. We don't have to write like that. We can just write return, and what the program will do is it will return x comma y in this format from the program body, whatever the x and y's values are. And if we try to run this program, we are getting 7 and 10 after the calculations. Now, this is something Go supports out of the box, but my suggestion is you should not use this format. I have never used it. I don't want to use it because it is very difficult to track. So let's say it's a very large function and you are at the end of the function, and now you look at this return. Okay, and now you want to understand what this function returns. Now you go to the first part of the function, you look at the x and y, and now you try to find those variables in the function body. Now you have to track a lot of stuff to understand the flow of the program. Right? It just makes things more complicated than they have to be. So for that reason, I prefer to use the explicit return type. So in this case, what should ideally happen is we should just do int, and we should initialize these variables like this. We'll get to the initialization variable part right after this. Now I should do x comma y. Now if we run this program, we're again getting 7, 10. Now if you read this, this is much more readable. We are initializing two variables and we are returning x comma y. Okay. The implicit return feature is not very readable and it is prone to mistakes. So you should know that they exist, but you should not really use them unless you would want to, then feel free to. Now let's understand about variables. Okay. Now this is how we declare variables in Go. Outside of the function, we can write the keyword var and the name of the variables. And if all of them are of the same type, we can just add the type at the end. If they are not of the same type, we have to add the type after each variable's name. Since all of these are of the same type, we can just write bool at the end, and all these variables are initialized to their zero values, because in Go, a variable is never in a uninitialized state. It is never in an undefined state or null state. A variable, a struct, or whatever the data type is, always initialized to its zero state. So since it is a of type bool, it will be initialized to its zero state, and the zero state of boolean is false. Okay, this is how we declare variables outside of a function body, inside a package. This is not inside any function, because that's why this is the only way to declare variables outside of a function. Now, if we are inside a function, we have a couple of ways to declare a variable. The first type is this, the same way we define the variables outside the function using var. Var, the name of the variable and the type of the variable. And this will initialize I to the zero value of integer. What is the zero value of integer? It is 0. Okay. And if we try to print these variables, let's just run it. We get 0, false, false, false. The 0 for I, and since C, Python, Java are all initialized to the zero value of boolean, they are all false. Now there is another way to declare and initialize variables in the same statement. That is only doable inside a function. We cannot do it outside the function. So we can write it here, I with colon equals to 0. And if we follow this pattern, it is pretty short to write, and this is one of the patterns that you'll use mostly. You'll also use the var pattern, but if you already know the initialization value of a variable, then you'll use this pattern, the colon equals to. And since we know the i's value has to be 7, now we can do this. And if we print now, and print 7 false, false, false. Now this format, this colon equals to format, is only accessible inside a function. We cannot do it outside the function. If you try to do it here, let's do it. Let's do k colon equals to 8. If we hover over it, it will say expected declaration found k. So all the declarations outside a function has to follow the var pattern. It cannot follow the colon equals to pattern. Okay. Now there is another way to write it using the var pattern. You can say var I equals to 10, and if you print it, it prints 10. And using the initializer, it interprets that I is of type integer. Okay. And this is just a long way of writing the colon equals format, because this is the same thing as writing, if we take out var and we just put colon here. So this colon equals to is kind of a syntactic sugar, a short way of writing this var. Okay. If you don't want Go to interpret the type, we can write var I, can write string. Now the moment we write the type here, the initializer value has to support this type. Now it says cannot use 10 untyped integer constant as string value. Now we have to make this a string. Now it satisfies. Print it. It prints 10. Okay. Those are all the ways you can initialize variables in a typical Go program. Now, if you have questions now that which pattern to follow when, this is how you should think about it. These are the rules. First rule is if the initial value does not matter and you're fine with it initializing with a 0 value, then go with this pattern, this var I integer. Since it does not matter what the initial value of I is, and we will set the value of I in the course of the program in a later phase, we can initialize it like this. It implies that to the reader of the program, whoever is looking at the program, they now can understand your intention that variable I has a value of 0 when it is initialized, and the initial value of I does not matter, and the value of I is set somewhere later in the execution of the program. So that's the first type. The second type is if you know the initial value of the variable and it is important, then you can go with this colon equals to. Now, since you know the initial value of the variable I is 0 and has to be 0 and it is important for it to be 0, then go with this pattern. Okay. The third thing, if you are outside a function like this, if you are outside a function, then you don't really have a choice. You have to follow this pattern, var c bool. You can also initialize it here, var c true. Okay, those are typically the three patterns when it comes to variables that we have available in the language. Now, to get a little concrete idea about how people use variables in a real system, let's go back to our example of FIDER. A couple of examples that we can see using the var form of variable declaration is here. As you can see, these variable declarations are outside of a function. They are in the level of package. They're the package level variables. And that is the reason they have declared it using var, even though they knew the initial value. And in the same way, these variables are declared at the package level, and that's why they are declared using var. And you can find a lot of examples like that. All the variables that are declared at the package level, they have to be declared using var. And another example, which is declared inside a function and still uses this pattern of var instead of the short declaration of colon equals to, because they have initialized the variable at this stage, but at this stage, the initializing value does not matter. The value that will be assigned to this variable, which is of type error. It is of type error, but the initial value does not matter. We don't have an initial error value. The value will be assigned during the execution of the program. So if you focus here, the value is actually assigned to the ERR variable is at this point. At this point, this function returns an error type in the second return value, and that's what gets assigned to this variable. Okay. So in this pattern, when we have a variable that for which the initial value does not matter, in that case, we can go with this pattern. In the same way, if we look for the colon equals to pattern, let's look for the colon equals to, do a global search. And you can find this pattern pretty much everywhere, because most of the time, most of the times we know the initial value of our variables or of our data types. So in that case, we pretty much go with this pattern. For loops, we have not explored for loops yet, but there also we use this colon equals to, the short declaration form of variable declaration. You can find this example everywhere. This is the go-to method of initializing variables when we know the initial value. Okay, so those are the two things that you have to keep in mind. Eventually, when we do more practice, when we use variables a lot in Go, you'll get it. You'll get which pattern that we use where. For now, just know that these two kinds of patterns exist in a typical Go project. Moving on to the next example, which is of data types. So in this example, various data types are declared. We have Boolean, we have unsigned integer, we have a complex, and we are printing the variables and the type here using printf. Okay, and we are using the %t verb. %t verb is used to print the type of a variable, and %v verb is used to print the value of a variable. There are other verbs, which is %s to print the value of a string. There is %q to print the value of a string in double quotes or single quotes. Okay, and there are different verbs that you don't really have to remember. The more you use, the more you will get the idea, and you'll remember the pattern the next time you need them. So let's see. So what are the data types that we have on a high level? All in all, let's say Go has 4 major types of data types. The first one is basic. In basic, we have number, we have string, and we have Boolean. These are the 3 major categories inside the category basic data type. The second data type that we have is aggregate data types. And these are of types array and struct. Array is basically a collection of similar data types, collection of homogeneous data types. You cannot store a string and a number inside the same array. The type has to be same for all the values inside an array. And inside a struct, in the opposite way, struct is a collection of heterogeneous data types or different kinds of data types. You can store an integer, you can store a string, you can store a boolean, all inside the same struct. So that's the difference between array and struct, and they are called aggregate data types because they consist of different basic data types inside them. Okay. We have the third type, which are called reference data types. Reference types, inside them we have pointers, which we'll explore soon. We have slices, we have functions, we have channels, and we have maps. These are the 5 reference data types, and they are called reference data types because they themselves don't contain the data as a container. They refer to some data type which works in the background, and they refer to that data for functioning. That's why they are called reference data types. They don't have the data in them. They refer another data type to access the data. And we have the fourth one, interface types. We'll explore interfaces later, but they are another major type in Go. So these are the 4 major categories of data types in Go. And inside basic, we have number, string, and boolean. So if you go here in the tour of Go, here we can see we have boolean, we have string, and we have inside number, we have all these categories. We have integer, we have integer 8 and all these numbers 8, 16, 32, 64, and uint, which stands for unsigned integer, and 8, 16, 32, 64, etc. So what is the difference? What do these numbers mean? These numbers basically help you to decide the size of your variable, How? Let's imagine int 8. We take integer int 8. What this means is this variable can have numbers between -127 to 128. And how did I derive this range from this number 8? So this 8 means basically this variable can use 8 bits to represent the number. So 8 bits means 2 to the power 8, which is roughly 256. And 256, since it is a signed integer, we can have negative numbers inside this. If we divide this range can be -127 to +128. That is the range. We can store numbers inside this range in int 8. And in the same way, you can derive what can be the range for int 16 or int 32, etc. And for uint, the unsigned integer 8, what that means is, since it is unsigned, we can only have positive values. So 2 to the power 8, which means 256. So our range can consist of 0 to 255. We can assign numbers inside this range. That's what these numbers mean. What can be the range of your integers? How much size that you want the language to assign for these variables. Now we have other 2 types, which are integer and uint, unsigned integer. What these mean, for example, if your operating system is of 32-bit architecture, then int will have int 32 in size. And if your architecture is 64-bit architecture, then int will have int 64. Same for uint 32 and uint 64. So the Go official documentation recommend that you should always go with integer and unsigned integer, depending on you whether you need positive values or negative values. You should always go with the system defined variable units. But there are times when using int 8 makes more sense than using int, which if you have a 64-bit architecture, which will have int 64. In cases when you exactly know what is going to be the range of your integer value. For example, if you take a look at finder and we try to find uint 8, and if you take a look at here, We don't need to understand what's exactly happening in this system. But all in all, on a very high level, we can understand this, that there is a type which has the data type uint 8. And we are declaring some variables of different levels. And on a very high level, without understanding anything, we can say that they need this level type to be the range from debug 1, 2, 3, 4. So maximum 1 to 5. This range is enough for this use case to define different levels of logs inside a backend system. Okay. So in this case, if they had gone with the system defined unit, which is int or uint, then that would have assigned the uint 64 unit. And that range is a little bit too much for this use case. So 2 divided 64 can have these many numbers, which they don't need for this use case. So for this, they went with the smallest available unit for unsigned integers, which means unsigned integers 0 to 255. So since they know their range is going to be maximum 5, or in the worst case 10 or 12, if they come up with more levels in their logging. So worst to worst case 50. You want to go ridiculous levels. It cannot exceed more than that. So for this use case, going with a uint 8 saves a lot of memory for your system. So it's pretty much common sense that if you beforehand know the range of your integer, if you know what is the maximum value you can assign to your integer, go with that range. Go with that range. So that's the mental model you can use to either go with any of the numbers, any of the weighted units. Now, while working on backend systems, when dealing with user data or data that you are not very sure of what is going to be the size of those integers, then you can safely use integer. It is not a very huge performance effect, since Go official documents also recommends you to use the system defined unit. Okay, that's the mental model you should have. Then we have byte, which is an alias for uint 8. Bytes are also used to represent strings inside Go. We'll explore more on that later. Then we have rune, which is an alias for int 32, and it is used to represent UTF-8 characters inside a Go program. Then inside float, we don't have system defined units. We only have float 32 and we have float 64 to define different floating point values which have decimal points, 32.64, something like that. Okay, those values can be used using float 32 and float 64 data types. Then we have complex, which I have personally never used, but you should know that they exist. Okay, those are all the data types. Those are all the different data types inside basic. These are all the basic data types that we have available in a Go program. So going back to our earlier example, this is a program which defines a boolean, unsigned integer 64, a complex data type. Then we are printing the type and the value. And if you run this, then we can see the type bool, uint 64, complex 128, and the values of the variables. That's pretty much all there is to it in basic data types. We have integers, we have numbers, we have strings, we have booleans. Inside numbers, we have signed integers, we have unsigned integers, we have floats, and we have complex and bytes and runes. Great. Another concept that we can touch up at this point is, which I have already mentioned, that Go always initializes variables with their 0 value. And by 0 value, I mean for integers. For any number data types, the 0 value is 0. For any booleans, the 0 value is false. And for any strings, the 0 value is an empty string, a empty quote. Okay, those are all the 3 basic data types, and those are all the 0 values that you have to remember. There is another 0 value called nil, which we will see when we look at reference types. All the reference types will have 0 value of nil. Okay, and we are printing here using %v. %v prints the value in Go format of any variable, and here we are using %q. %q is basically printing a string with quotes. Okay, and if we run this program, we can see 0, 0, false, and empty string. So in this case, if we change this from %q to %v, then what happens? We don't see the quotes anymore. So if we want to print the quotes, then we have to use %q. That's the use of %q verb. So in case of strings, it will explicitly print the quotations. Okay. Next up, we have type conversion. Type conversion basically applies in statically typed languages like Go, because unlike dynamic languages like JavaScript or Python, conversions are not done implicitly by the language. You cannot assign a float value to an integer value, and you cannot depend on the language to implicitly convert it. You have to explicitly convert the value. That's all there is to it. To understand that in Go, every data type needs to be explicitly converted into another data type. There is no implicit conversion, even though a number satisfies. So in this case, let's say you have an int 64 value and you have an int 32 value. Even though both are the same numbers, let's say both have the value 32, and this variable is k, this variable is v. Even though you have this use case, you cannot assign the value of k to the value of v, because the internal data type is int 64. Even though the values are same, they are both the integers and they both satisfy each other, you still have to explicitly convert like this int 64, the name of the type, and pass the value of k. Then you can assign it to v. This is the format that you always have to follow. It does not matter whether the type internally satisfies us or not. You have to explicitly convert the types before assigning. Okay, so in this example, what's happening is we are defining two integers, x and y, and we are calculating a value of type float using these two integers. And we are trying to assign the value of that float to another unsigned integer using explicit type conversion here. So if you try to remove this, if you try to remove the explicit type conversion, then we'll get this error. If you hover over it, you will see cannot use f variable of type float 64 to unsigned integer. And if you try to run this, we'll get a compile time error for the same. Now, that's pretty much all there is to it. Every time you want to convert one type to another, you have to do explicit type conversion. You cannot depend on implicit type conversion. And usually you don't have to worry about this while you're developing applications. You will get these errors while you're developing in your IDE itself. You won't get it during runtime because these are compile time errors and your IDE can catch it using LSPs. So you will get these errors and you can fix this. So you don't have to actively worry about it. You will get hints from your compiler to fix your errors. So we can go back to it, and using the explicit conversion, we can print the value 345. Next up, we have type inference. What type inference means? When we are using a short declaration form using colon equals. In this form, we don't define the type of the variable explicitly. We let the language go, the Go runtime, the compiler, to derive the type using this initializer value. So in this case, if we hover over it, we can see that the type of value is integer because we have assigned 42. So if we change this to 42.7, and if you see this, now this is a float 64 value. And in the same way, if you change this to a string, and if we check this, this is a string. And another thing to notice here is once the type inference infers the type of the variable with the initializer statement, in the later phase, if you try to do v equals to 9, in this case, you will get the error that cannot use 9 untyped in integer constant as a string value. So once the compiler infers the type from the initializer statement, you cannot change the type during the course of your program. The type will be constant. The type is only inferred once and it stays like that throughout the execution of your program. That's why Go is called a statically typed language. Okay. Next up, we have constants. We declare constants using the keyword const and we assign a value. You always have to initialize a constant. Otherwise, it's an error. So constant have some properties. First thing is they are, of course, constants. And what that means is you cannot change the value of a constant in a later phase of a program. The second thing is they are they are evaluated evaluated during compile time. And that's the reason we always have to assign some initializer value to a constant, because the values of constants are evaluated during compile time. They are not evaluated during runtime or when the program is executing. During the compilation phase only, the program will know the value of the constants. So if you try to run this, we get all these values printed. And what if we try to change this? Truth equals to false. And if we hover over it, we'll get that cannot assign to truth because it is a constant. And if we try to run this, we'll get a compile time error that cannot assign to truth because it is a constant. So what is the difference? When do we use variables and when do we use constants? What is the mental model there? So basically, every time that you have some hard-coded value, you have some predefined value, whether it is a string or a number or a boolean, because constants can only have these three data types in them. A constant can be a boolean, a constant can be a string, or a constant can be a number. These are the only three data types constants are allowed to have. So when you're developing, if you have a use case where you have a hard-coded value, you have a port that you want to listen to, or you have a URL that you want to make a request to, or you have an allowed set of values that you want to validate against, any kind of hard-coded value. So instead of using the hard-coded value as it is, you can name the value using a constant. And that implies that this value does not change ever during the course of your program execution. And it has a semantic meaning and it also has a runtime meaning because constant cannot change. So if we look at the use of constants in our example, a real world example, you can do a search here, const space. And if you try to go files, so as you can see, it's kind of implementing an enum pattern using Go, using constants. So it has an allowed set of values. We will see what are enums and how to implement enum pattern in Go later on when we are building projects. But as of now, you can see that these are some hard-coded values, and in order to name them in a meaningful way, we are using constants. In the same way, we are using 1, 2, 3 hard-coded numbers to a meaningful name, that a role visitor, role collaborator, role administrator. Okay. In the same way, there are hard-coded values here. There are hard-coded values here. So that is the pattern. You have a hard-coded value. You want to name them. You want to name them in a meaningful way. Those are the scenarios when we use constants. Next up, we have loops. Now, unlike other programming languages, Go only has one loop. This is for loop. We don't have while loop. We don't have do while loop. We don't have any other those loops, because the for loop with semantics, by changing the syntax of the for loop a little, we can implement all those patterns. Now, how does a loop work? By the way, a loop just means executing a set of instructions again and again until a specified limit in order to reduce the boilerplate code. Instead of writing these statements again and again until like 10 times, we can use the construct of loops, which is available in every programming language, to run this same statement 10 times. Okay, so how does this loop work in Go? We are here declaring a variable of sum, a variable named sum, which is of type integer. If you hover over it, it will say integer because the initializing statement is 0. Now we are initializing a variable named sum. Now this is how the loop works. The first statement is the initializer statement. It is some kind of expression. So here we are initializing a variable called I. And I is only usable inside these curly braces. It is only usable inside this scope. This is called lexical scope. And I only works inside this. And after every iteration, I's value changes. A new instance of I is created. Okay, the previous instance is destroyed. Now, this is the first expression that is that runs with every iteration. Second, the iteration, the whatever statement inside the loop construct, this is executed. After the execution, this statement runs. We change the value of I. We increment the value of I. Then at the end, we check this condition, whether this condition is true or false. If this condition is false, then we break out of this loop. If this condition is true, Then we again continue with this, then we execute this, then we execute this, then we check this, then we execute this. So this is how this cycle of a typical for loop. Okay. Now to visualize it, what we can do is we can use a debugger. So if we add a breakpoint here, so a debugger basically means you can investigate the flow of the program using this tool called debugger to better understand how the program works, to investigate the flow of the program basically. Now if we run this, VS Code has a inbuilt debugger for Go. Now we can run this, and in first iteration we have I with value 0 and we have sum with value 0. We have a breakpoint here. The program stopped here at the first iteration. Now using this, we can go to the second iteration. So after I click this, we came outside this loop, and here we are checking whether i's value is smaller than 10 or not. Since i's value is 1 after the first iteration, the condition is true. That's why the loop runs again. And if we click on this, now i's value is 1 at this point, because in the previous iteration i's value was incremented to from 0 to 1 after the end of this statement. Now since you're entering this loop again, now i's value is 1. After this, i's value will be 2. If we click on this, at this point i's value is 2 and the condition is still true. So now we come inside the loop again. Now sum's value was 1. When you click on this, i's value is 2. When you click on this, sum's value gets to 3. And this is how the loop works. Every time the iteration runs, the increment happens, the conditions checks, and if it's still true, then it progresses. It proceeds to the next iteration. And this is the way we have 7, we have 8, and we have 9. And at this point, i's value is 10. So in the next statement, the loop will break and we will reach the end statement. So we'll break out of this loop and we'll reach the end of the main function. And after this, the value will print. And so that's how a typical for loop works in Go. Now, if you want to implement the while loop from other programming languages, we can just get rid of the first two expressions, the initialization and the increment, the expression, and then we'll end up with a while loop, which basically has a for statement and a condition and the execution statements. So this is how you do while loop in Go. So if we run this, we have 1024 is the sum. So until this condition is true, this loop will keep running. And once this condition is false, it will break out of this loop and we'll see the print statement. And at this point, what if we take out the condition? If we take out the condition, and what if we run this? At this point, our program is stuck in an infinite loop. An infinite loop basically means because there was no condition to break out of this loop, our program never exits and it is stuck inside the same set of calculations. So unless you have a specific condition at this step, the program will never exit. The program will never exit out of this loop unless there is an explicit break statement here. So at this case, let's stop this execution. And here, what if we add a condition? So we have not seen if conditions yet, but if add a condition, if sum is greater than 100, then we break. We add a condition here for breaking out of this loop if the value of sum goes out of 100. And now if we run this, we can see that once the program reached 128, into the next iteration, the condition was true and it broke out of this loop. Now this pattern, if you're wondering why do we need infinite loops in the first place, since it hangs the program, we have some patterns, especially when we get to the concurrency chapters. There we have some patterns where we are constantly listening for signals from different Go routines and all. There we use this pattern of infinite loops. So we keep listening for signals and all. And the moment we get some signal, we break out of this loop. That's how this pattern works. So you should know that we have a way of implementing infinite loop which is not always bad. There are uses for infinite loop also. Now it is a very good point to show if conditions. It is pretty simple to wrap your head around. We have a condition which starts with if, and whatever the condition that is provided after that, there is no braces. You have provided a condition which should evaluate to either true or false. And if it is true, then this statement will run. Otherwise, it won't. That's pretty much all there is to if condition. In the same way, in the for loop, in the first part, we could assign, we could initialize a variable, we could call an expression in the first part, in the first semicolon here, for here, this part. In the same way, in the if statement also, in the first part, we can initialize or we can call an expression in the first part. This variable v will be valid in the if condition, will be valid in the if lexical block. So for example, if we try to access v here, we try to see, let's say k equals to v. Now if we hover over it, it says undefined v, because v was initialized in this if block in the first statement, and it is only valid inside this lexical block. It is not valid outside. So it is a very nice way of initializing and checking errors that we use with this feature of if. It reduces some amount of boilerplate code because of this pattern. We can initialize a variable and we can check a condition, and if that condition is true, then we get inside the if block. If not, then this is not executed. So this is a very nice way to reduce boilerplate code. The same way, after if, we can also use else. If this expression is evaluated and if this condition is true, then we get inside if block. If this condition is false, then we get to the else block, and this part is executed. And as I said, the value of v is only available inside the if block and inside the else block. We cannot use the value of v outside the if and else block. And now I think it's a good time to take a look at some examples in the real world of how we use for and how we use if conditions and if else conditions. Here we can see they are looping over the number of CPUs and doing something. It does not matter what they are doing. And this is how people use for loops. And here you can see they're dynamically taking the length of this variable and initializing this loop and running these executions. Okay, this is how for loops work. And let's look at if. And this is how typical if, else if, and else conditions work. This is basic programming stuff. If this condition is true, then this part is run, or if this condition is true, then this part is run. Otherwise, if there is an else condition, that is run, or the program just keeps executing. Typical if-else behaviors that we have in other programming languages. Nothing too special here or nothing to remember here. Go also has a switch case. In the first part, you can evaluate some expression, and this variable is available throughout the scope of this switch block. It is not available outside it. Now, using this, you initialize this variable using runtime.go operating system, this environment variable that is available to your Go programs by default. And you use this variable as a condition. You are checking, check the value of OS, this variable, and you are checking different values. Whether the value of this variable is this string, Darwin, or if the value of this variable is Linux, or if none of these cases satisfy, then it reaches the default block and this block gets executed. Otherwise, if one of these statements are true, if one of these cases are true, then that part gets executed and this breaks. It does not proceed further. It breaks out of this switch statement. And if we try to run this, we are getting Go runs on OS X because this matches our Go operating system. This environment matches Darwin. And that's why we are getting this. And the moment it matched this case, we came inside this block and this statement got executed and it broke out of this switch statement. Okay, this is the typical behavior of switch statements. Now this is another example of a switch case. A switch case condition can also be an expression. It can be a constant string, it can be a number, or it can also be an expression. If this will get evaluated, and depending on that, we'll get inside any of these blocks. And the moment any of the case statements are true, we get inside that block and the statements are executed and we break out of that loop. And if you try to run this, since today is Saturday, we'll probably get today. When is Saturday, it prints today because we came inside this block. There is another pattern with switch, which is a replacement for writing these kind of code. Let's say if we have if condition and we are checking something, then we have the block, then we have else if. When you are checking something, then you have another block, then you have another else if. We are checking something, we have another block, then at the end we have else. So instead of writing like this, we have this construct in a switch statement. So we can initialize a switch statement without any condition or without any expression. We just start with a curly braces with an empty switch. And now this is like an if else block. So this is an if condition. You can imagine this is another else if, and this is an else condition. So this condition is checked from top to bottom. The moment one of the conditions are true, that block is executed. It comes out of the switch statement. If none of them do, then the default one is executed. So if you try to run this, we get good afternoon because it's not 5 yet when I'm recording this. Now we have a very interesting concept which is called defer, and this is very unique to the language Go, and other programming languages might have different implementation of the same concept, but in Go we call this defer. Why do we use this concept? The defer concept is, before that, let's just execute this function and we get first this is printed, the hello part, and then this is printed. What exactly is happening here is, the moment you use the keyword defer and then you provide some expression, it can be a function call, it can be a expression, whatever is provided in this part, this gets stacked in, let's say, some kind of stack. So we have a stack here and this is pushed here. So this world, this instruction of print world, this stack is pushed here, and then this expression is pushed into the stack and the program starts to execute normally. Whatever instructions that come after it, they are run sequentially, however you can expect your program to run. So that's why after this evaluation, it did not print yet. This does not get executed yet. It is just evaluated and pushed into a stack. Now we reach at this stage and this is printed here. You can see the first hello. Now after this, the main program is finished. There are no more statements to run. At this point, the main function returns. We call this the main function returns. At this point, what the Go programming language does is, it takes the stack and it starts to call all these functions, call all these expressions that were provided throughout the function execution, all the defer statements. There can have multiple defer statement in a function, and all the defer statements are pushed into the stack one by one, and the Go program starts to call them in that order by popping them off the stack. So that's why after the function return, after all the statements were executed, we see this getting executed, the print ln to world. So the first world hello is printed and then the world is printed. Now to understand this concept of differs and the stack of differ a little better, we have a loop, and in this loop what we are doing, we are calling differ multiple times, let's say 10 times. We are calling the differ statements 10 times in this for loop, and let's just execute it and then we'll understand what happened here. So say go run main.go, and you can see First the counting got printed, then we have done, then we have 9, 8, 7, 6, 5 okay, in the reverse order. Now let's understand what exactly happened here. Okay, minimize this. First thing, the first statement in the function counting. First we saw this got printed in the console. Okay, this is done. Then we reach here in the for loop. With each iteration, let's say now we have a stack here. You have a stack where the Go programming language pushes all the defer statements, the call of all the defer statements. So in the first iteration, the i's value is 0 and we call defer. So this function, this expression is pushed into the stack. So we have print 0 here. Okay, this instruction is pushed into the stack. Second iteration, zeros, the i's value is 1. Now print 1 is pushed here. Then 2, then 3, then 4, then 5, then 6, 7, 8, 9. 7, 8, 9. Okay. And at this point, this statement, the for loop statement, the condition is false and it breaks out of the loop. And we reach here. At this point, counting, after printing counting, we see done getting printed here. Okay. And then there are no more statements in the program to execute. At this point, the main function returns. And when returning, the Go programming language runs all the deferred statements of that function. It runs all the deferred statements of that function when returning from the function. So at this point, what it does is it pops out of the stack. Since it's a stack, we push all the values on top of each other. It pops in that order. So that's why after seeing counting, then done, we see 9 getting printed, then 8, 7, 6, 5, 4, 3, 2, 1, 0. In the reverse order, all of them getting printed because the Go programming language pops all the elements from the stack in the order they were pushed. Now you should have a good idea of how defer works. Defer is basically pushing the execution of some function calls, some expression into a temporary stack. And when the function returns, the Go programming language executes all the functions. Now, the question is why? Why do we need differs? Like, what are the use cases? Why would we need to execute statements before returning of the function? Why not execute them explicitly? Why not just execute them here? Now, there are two answers to that. One is sometimes it is easy to forget running some statements when we are developing, when we are writing code. For example, when we are opening a file. So since Go is a systems programming language, we have constructs to open files and read data from different sources. Now, after you open a file, you have to explicitly close the file. Otherwise, there will be memory leaks and your program will eat a lot of memory because there will be a lot of open files in case you are reading a lot of files in a for loop. In that case, every time you open a file, you have to explicitly close it. So what happens? You open the file, let's write in pseudocode, you open the file, and at the end of executing all your complex calculations, you have to remember to call close on that file, on that function. Now there are two things that can happen here. Either as a human error, you can forget to close the file. That is a very expected scenario. A lot of times there are a lot of human errors in a program and we can forget and we do forget. And it can be a file also, or it can be a database connection that we need to explicitly close while we are returning from the program. Otherwise memory leak happens. There are a lot of instances where after you start something, you have to explicitly stop it. The start and stop comes sequentially. The stop is mandatory. In these scenarios, you have to remember calling the close functionality. So either you can forget it, or during the execution of the program is broken. The program throws error. It panics. To talk in Go's terminology, it panics. We have not explored what is a panic yet, but panic basically means Go's way of throwing an exception. Go does not have the concept of exception where the program completely, the flow of the program completely changes, but you can think of think of it as an exception. It throws an error and the program stops executing. That is basically a panic. Exactly what the name sounds like. So let's say you opened the file or you opened the database connections. You were running some instructions here. You are running some business logic. And at some point before you called close, at some point your program panicked. It threw some error, it panicked. And instead of going in this flow and calling close at the end, it panicked and it stopped the flow of the execution and it directly took this path. Now you never got to call close because in your mind, the way you had imagined it was, you'll open the file and you'll run some instructions and in the end you'll close it. Now you remembered to close it, but since your program panicked, since your program threw some error and returned from that statement, you never got to close the file. And all these database connections and all these open files are still there in the memory. Now you have a memory leak problem in your app. So for these use cases, the Go programming language has given the feature of defer. Now you don't have to remember to close the files, to close the database connection at the end of your function. Okay. What you can do is you can open the connection, open, let's say, file. And in the next line, what you can do, you can say defer close file. Now it won't instantly close the file because as you saw, the function is not called instantly when you call it using defer. It is evaluated and it is pushed into a stack. So the moment an error occurs at some point here, the Go programming language is configured in a way that the moment an error occurs, it starts executing all the functions that were in the defer stack, It starts popping all these functions and it starts executing them. That is a construct provided by the Go language itself. So for that functionality, for that feature of, in case of a panic, you still want to execute these statements. You still want to close a file in case of an error. In case of a panic, you still want to close your database connections in case of a panic. For this use case, we can use defer. And it's also readable. You are opening a file and you're instantly deferring the closing of file. So it does not matter what happens after a few hundreds lines of codes. The closing of file will always happen because of the way Go is built. The defer functions are always executed when the function returns. It does not matter it is successful or it panics. We can take a look at some examples of how people use defer in the real world. So if you search for defer here, you can see some functions where, as you can see, people are setting some database and in the next line only, they are calling defer. So that so this is a test in Go for your information. Don't have to worry about what all these are, but this is a test. Initially, they are starting some database connection and in the next line only, they are deferring the teardown, basically the closing of the database connection. So that during the flow of this test, it does not matter it errors out or not. This closing of database connection is always executed and is also readable that you started the database connection here and you close the connection in the next line. So after all these executions, the Go program runs this part, the defer, the teardown of the database. Okay, and you'll find a lot of differs in this project, which have different meanings in different contexts, but you should have a good idea by now. But what defer means? Basically pushing the execution of a function to the last statement, and ensuring that it always runs. Does not matter the function is successful or errors out or not. Okay, that's all about differs. It is a very important concept and we'll use it a lot. Not a lot, but we'll use it quite frequently. And we should remember this pattern. Now we are in the territory of reference types. As I had mentioned earlier, Go has around 5 types of reference types. We have pointers, we have slices, we have functions, and we have channels, we have maps. We have 5 reference types. Reference types basically means they don't have the data themselves. They refer to some other data type they depend on a different data type that works in the background to have the data. They don't have the data for themselves. Okay, so for now, let's explore pointers. Good. Now, Go has this concept called pointers, using which you can access the address of the variable. And what do we mean by address? Now, throughout the execution of the program, you assign different variables. You create different data types and you assign variables where you store those data types. Now, all those data types, all those variables are stored somewhere in the memory. Let's say this is your memory. There are different slots. You can think of them as slots. So when you create a variable, they are given some slot in your memory, in your random access memory, in your main memory, and they are given some slot, and that slot will have an address. It won't be a physical address because we are abstracted out from the core operating system kernel using the Go runtime. We are executing using the Go runtime. So we are given some address. It's a virtual address. Still, it is some kind of address. We can think of it as a physical address, but it's actually not. So that slot will have some address, and using this address, we use our variables. Our variables are stored in these slots. So what pointers do, using this data type called pointer, this data type stores the address of this variable. If we use a address of this variable, and we can access the address using this symbol, the AND symbol. And if we have a pointer, we can use the star symbol to find the value of that pointer that this points to. So this is all different terminologies. So let's see an example to understand how it all works. Now here we declare two variables, this I and j, with 42 and 2701. And we declare a new variable called p, which takes the address of I, because it uses this operator called AND. It takes the address of I and it assigns it to p. Now, if we hover over p, it says star integer, which basically means it is a pointer to an integer. It is not an integer value itself. It is of type pointer, but the pointer points to a value which is of type integer. That's what this means. Okay. And at the next statement, what we do, we print the value of p. Now p is a pointer type. P is not a value type. We cannot print the value of p directly. If you do print it, it will print some random garbage value because it is the address. Now we can print the value the pointer points to using this star operator. So this star operator is used to dereference. The terminology here is dereferencing a pointer, and we can do that using this star operator. So we can get the value of p using this star and we can print it. The next step, what we are doing here is we are taking some value, in this case 21, we are assigning it to this pointer, and we are assigning it to the value of the pointer. And since we have the address, since in this slot using the pointer, we have the address of the variable, we can change the content of the value, the content of the address using this structure. You can do star p equals to 21. Now this address points to a different value, this 21. And when we print this, print I, now instead of 42, it will print 21, because using a pointer to I, using a pointer p to I, we change the value of I from 42 to 21 using a pointer. Now, if p was not a pointer, if p was direct assignment, if we did p equals to I, then in that case, if we change the value of p, it would not have shown in the value of I. Since we used the pointer to I, when we modified the value of p, it also modified the value of I, because now both of them point to the same thing. Okay. The next step, we assign the address of j, and we are dividing this value and assigning it to the p, and now the j's value is also changed. And let's run this program and see whether it works expectedly or not. So if we do go on main.go, we get 3 values for 3 print statements. So what happened here? In the first print statement, i's value was 42 because we have not changed it yet. So that's why it printed 42. In the second print statement, we changed the value of I using the pointer p and we made it 21. That's why we see 21. Same way, here j's initial value was 2701, but after we did this thing, we did some calculation and assigned it to p. And since P was pointing to the address of J using this pointer operator, that's why the value of J is now 73, the result of this calculation. So that's what pointers are. They basically contain a data type which is an address of some variable, and using pointers you can change the content of that variable, whatever it points to. Now there are a lot of concepts in Go related to pointers. We will see it pretty frequently in a lot of different scenarios and a lot of different contexts. So for now, this information, this knowledge is pretty enough, and we'll see what else we can learn about pointers when we add more stuff, more basics to our knowledge of Go. So in the next phase, now let's look at what are structs. So struct is one of the data types of aggregate types. We have two types of aggregate types. One is array and the second one is struct. Array is a collection of similar data types, and a struct is a collection of different data types. So this is how a struct looks like. You say type because struct is a Go's native type. It's a type, the name of the struct, and you literally write the keyword struct, and then you open a curly braces and you write different data types. You define what are the types of these fields. These are the fields of the structs X and Y, and beside them you write what are the types of those fields. Okay, and how do you use this struct? How do you initialize this struct? Here, if you see, you write the name of the struct, and in the curly braces you provide the values for these fields in that order, in the order that they were defined. Okay, now we write 1 and 2, and 1 will be assigned to X, 2 will be assigned to Y, and since these are integers, we don't see an error. This satisfies these two literals that we are providing. These satisfy the condition that X is an integer, Y is an integer, and we are assigning them to a struct which is called vertex. And now we can print this. We print it, go run main.go, we get this representation, string representation of struct, which is 1 and 2. There are also other things that we can do with a struct, which is, let's say we initialize a variable and we initialize this struct with X is 1 and Y is 2. Now we can access the fields of this struct. The struct has two fields, which is X and Y. We can access the fields using this dot operator. We can say whatever the variable is which we initialize the struct with, we can do v dot, and we can use X or Y because those are the fields of the struct. And we can also assign some values to the struct. Even though we initialized with value 1 for the field X, we can change the value of X after in the next statement, v dot X equals to 4. And now if we print v dot X, it will print 4 instead of 1. Now let's look at how pointers and structs work together, because this is very important. This is something that we'll use a lot when we are building projects. Now what we are doing here is we are initializing a struct with value X as 1 and Y as 2, and we are assigning it to V. And in the next statement, we are initializing another variable with name P, and we are assigning the address of V, the address of this initialized struct, and we are assigning to P. Now here what we did is, we using this pointer, we changed the value of X. Instead of 1, we made it this number. Okay, and what happens when we print V here? Let's print it and see what happens. Now we get this number, which is basically 10 to the power 9. We have 9 zeros here. Now that's the point. If we use a pointer, and if we have a pointer to a struct, and using that we can change the values of the fields of the struct using a pointer to a struct. This concept is something that we will use a lot when we're actually building real world stuff. In this example, we are just looking at different variation of defining a struct and different variation of initializing structs. First run this example and then we'll see what's happening here. Okay. Now in the previous example, we had written it, we had written the fields this way. We had written X integer, and then we have written Y as integer. Instead of doing this, since both these fields have the same type, both of these fields are integers, we can put them in the same line. We can do x comma y integer. So this is one variation of declaring a struct. Okay. Then let's come to initialization. What are the different types you can initialize a struct? This is one type that we have already seen. You can write the name of the struct and you can provide the fields in that order. So 1 will be assigned to x, 2 will be assigned to y. And this is one way of initializing struct. The second way is you write the name of the struct and you can provide a key value pairs. You can write the name of the field, in this case x, and you can provide a value. And then with comma, you can provide another value of I, y, and colon 2. You can do it like this. If you don't provide an explicit value for a field, by default, since Go has this concept of zero value initialization, by default, Go will assign the zero value of that data type. In this case, since it is an integer, Go will assign the value 0 to y. Does not matter whether you provided an explicit initialization value for y or not. Go will assign the value 0 to y. That is one way of initializing struct. Another way, what if you don't provide any fields? Just type the name of the struct and you initialize it. In this case, Go will assign the 0 value of both the fields to them. In this case, both of these fields are integers. So x will have 0 and y will have 0. Then you can also do this. This is struct literal syntax. And what this means is, this is kind of similar to this, but instead of providing the type vertex, P will have the provide pointer to vertex. And if you hover over it, v1 is a type vertex. If you look at it, v1 is a type vertex, but P has a type star vertex, which means P is a pointer which points to a struct which has the type vertex. It is a pointer to a struct. Okay. And that's why when we printed for v1, we got the result 1, 2. For P, we got the result 1, 2, which is a pointer, that's why this ampersand, the symbol and stands for. Then for v2 and v3, we have 1, 0, because here we only initialize x with the value 1 and the y was initialized with the 0 value. That's why we have 1, 0. And in this case, we did not initialize any of the fields. That's why x has 0, y has 0. Now to wrap our heads around where do we actually use structs, we can look at a few examples of our open source repository. Let's search for the keyword struct here. Now structs are something, if you are a backend engineer or any kind of Go engineer, and you are using the Go programming language, structs are something you'll use a lot. Your day-to-day life will involve dealing with a lot of structs because it is a very versatile data structure and very commonly used data structure. If you get some JSON from front end, you have to parse it and store it into a struct before you can use it in your Go program. Because unlike JavaScript, you cannot use a JSON directly with your JavaScript object. Okay, you have to parse the JSON into a Go struct and then you can use the struct. That is one use case of structs. Okay, now let's look at some examples. We'll just skim through them to get a feel of how people are using structs. Okay, so this is one struct which has a field called plan ID and is of type string, and these are called struct tags. And what it says is the key is JSON and the value is plan ID. And it is a bit out of scope for now, but this basically means, let's say from the front end, from the client, we receive a JSON. We receive a JSON with this value, say plan ID as 3. Okay, this is the JSON we receive from front end. So when we are trying to read it in our handler, okay, first we have to do is you have to take this request body and we have to parse it. We have to unmarshal it into a Go struct before we can use it. We cannot use it directly because it's a JSON type and it is in bytes. When we are parsing it, we can use a struct like this, which has a field, a struct field with Go's own convention, and Here we are saying that we are using this struct, and any JSON field with the key plan ID will be parsed into this field, this plan ID. So using these tags, these are called struct tags, and with the key JSON, these tags are one way of mapping JSON fields to our own Go's struct fields, because the naming will be different. In Go, we'll have camel case fields, and the styling of Go is a little different than what we follow in typical JSON based payloads. That's why we have struct tags, so that we can map the JSON keys into our own struct fields. So that is something a little out of context now, but something useful to remember for now. This is what a typical struct looks like, and we have more examples of structs. We have this one, invite users. There's a string and there's an array. There's a slice. We have not explored slices yet. And there are a lot of examples of structs in this code base. You can notice it. First we have field names, then you have type, and you have tags. Depending on which application, which package is using it, we'll have different tags for a struct for different parsing mechanisms. Okay. So as you can see, structs are pretty versatile. We can store any type of data inside them. It does not matter what type is. In array, we can only store homogeneous data. In structs, we can store heterogeneous data. It can be an integer, it can be a string, it can be a slice, it can be a map, it can be anything. It can be pointers. Okay. So structs are very useful and something we'll use a lot. And this basics is enough to get us started with structs. Now, another thing about structs that I want to mention here is the capitalizing of the first character of the fields. And as you can see here, all the fields start with capital letters. And this is not a styling thing. This has a use case, as we have seen before. Capitalizing of fields and variables in a package in Go results in that variable or that type being exposed to code outside of that package. So for example, in this, we have this package called CMD, and this is another package called some test package. If we see the name here, and the package name is API v1 test. These two are different packages. Now, this package is using code from another package, from the CMD package, and it is using this struct, and it is importing that struct into this package so that it can initialize a new instance of it. What happens if we change this field from a capital R to small r? Let's change it and let's see what happens. And the moment we made it small case, as you can see, there are errors everywhere in the program, especially in those scenarios where we were accessing the field, this particular field of this struct that we were importing from another package. So that's the use of the capitalizing. If the first letter of that field of a struct is not capitalized, then we cannot access that field outside of that package. That's why we capitalize fields of a struct. And then we have arrays. As I said, arrays are a collection of same type of data types. Okay, that is the one-line explanation of arrays. So what we are doing here, we are declaring an array which has this type. It is a string and it can have two items. So this part, this two part, this is basically the size of the array. So when we say toString, when we say this, we mean this array is of type 2 items string. This size is the type of the array also. So this size is part of its type. So this array and this array, 3 string, these are of not the same types because it is of size 3 and it is of size 2. So that is one thing to remember. The size of the array is part of its type. Okay, next, what we are doing here, we are declaring a variable which is an array of length 2 of strings. And in the first index, we are storing the string hello. In the second index, we are storing the string world. We can access the indexes of the array using this syntax. The square brackets, and inside is the index number. And then we can print it, the index 0, the index 1. We can also print the whole array. The same way, instead of doing it like this, instead of declaring it here and initializing it this way, all the indexes, we can also use this syntax. What this syntax is, we can write the size of the array and we can write the type of the array. In this case, it is an integer of length 6. Then we can provide all the values in this order. 0, the index 0 will have 2, index 1 will have 3, index 2 will have 5, and so on. And we can print this. And let's run this. And as you can see, we have all the expected results. Now the two major points here are: one, Go is a statically typed language, and second, an array's size is part of its type. Now since we have these two facts, now arrays cannot be resized because a size of an array is part of its type. You cannot resize an array. You cannot reduce the size of an array. You cannot append to an array. You cannot do any of those things. An array is just a constant that whatever value you initialize it with or whatever value you push to it, and that size will always be the same. You can only push up to whatever value you initialize with. Arrays cannot be resized. And that is the reason you will not see arrays being used as frequently in real world systems. We will still use it when we have a fixed number of elements that we know the value of beforehand. But in most cases, we use another data structure provided by Go, which are called slices. And this is how we can make a slice using an array. And if we try to run this, we get this result of 3, 5, and 7, because this syntax, this indexing syntax that we use to slice, to create a slice out of an array, this is how it works. In the first part, we have a opening square bracket. In the first part, we have the starting index, and in the next part, we have the ending index, and this is excluded. This is not part of it. So since the starting index is 1, we start from here, and the ending index is 4. So 0, 1, 2, 3, 4, and we exclude it. So this is the range 3, 5, 7, and that's what gets printed here, 3, 5, 7. Now a slice is a very special data structure that is available to us. It is very flexible and it is very useful, and its mechanism is a little different than our typical arrays. And slices are also called a reference type. They are called a reference type because a slice has always some backing array. A slice only refers to an array that is working in the background. So if you want to understand how it all works, let's imagine this. We have an array. Let's see. This is the array. And we have different indexes of the array. And let's say we have numbers 0, 1, 2, 3, 4, 5, 6. Now this is an array in Go, and its type will be the first part 1, 2, 3, 4, 5, 6, 7. 7 integer. This is the type of this array. Okay. Now, if we create a slice, now how slices work is, a slice has 3 parts to it. So you can imagine a slice. Say we have a slice, and a slice has 3 parts. One is the length of the slice. Second, its capacity. We'll come to capacity soon. Capacity. And the third is a pointer. And a pointer to the first element of the array, or a pointer to the first element of the array that the slice is pointing to. So in this case, it does not have to be 0. It can be this also. It can be 2 also. So now a slice, when we have a slice, it has a background array, and this slice points to this element. So this first element of the slice is 2. Now the capacity of an array, the capacity of a slice is basically starting from the element the slice points to up to the last element of the backing array, not the last element of the slice. So in this case, the capacity can be 1, 2, 3, 4, 5. The capacity is 5, and the pointer is 2. That's what it points to. And what is the length? Now length can be the same as the capacity depending on how we sliced it out of the array, or it can be different than capacity. So in this case, length can be, let's say, 3. Capacity can be 5, length can be 3. Length can also be 5. Now it's all a little confusing. Now we will see a couple of examples and it will become more and more clear. I've just shown the figure here so that we can come back to it and we can imagine and visualize how it all works. Okay, so let's get to the example first. Now here we have an example. We have an array. We have an array, not a slice. We have an array whose length is 4. Now let's picture this. Let's picture this here. We have this array. Okay. Sorry. Let's picture this. We have an array like this. Okay. And these are the elements. So we will start the indexes from top to bottom, 0 to 3. Okay. And in the first index, we have John. In the second index, we have Paul. Third, George. And then we have Ringo. Okay. This is 0, index 0, this is 1, this is 2, this is 3. This is the array that we have. It is a fixed size array. We cannot expand it. We cannot reduce it. We cannot do any kind of changes to it, but we can slice it. Now let's understand how slices work. In this example, what we are doing, we are constructing a slice A, and it is slicing from this array from index 0 to 2. So now the slice A will have 3 parts, as I said. First part is the length. Length will be, since it is slicing from 0 to 2. So let's say 0, 1, 2, 3. 0 to 2. And since we exclude the last part, so the length is 2. Okay. And second part of the slice is capacity. You'll be more clear about the capacity after we go through some examples. For now, let's just stick to the concepts. Now the capacity, as I said, is starting from the first element of the array that this slice points to, which is 0, up to the last element of the backing array, not the last element of the slice. Now, how much is the capacity? The capacity is 4. Since we start from the first element, the capacity is the same as the backing array. Now we have the capacity 4. And we have a pointer. It has a pointer which points to John. Basically, this part, John. Okay. Now we have A. In the same way, we have B. B, what it does, it starts from the second index, basically index 1. So now we have length as, it starts from this index, and it goes up to the last index, 3rd. And since you exclude the last one, the length will be 2, the same way. And the capacity is starting from the first element of the array that it points to up to the last element of the backing array. Now the capacity is 3. And the pointer is, what is the element that it points to? Is Paul. Okay. This is how the physical representation of an array and the slices that come from it looks like. Okay. Now in this example, what it is trying to do is, it is doing in the array, in the slice B, it is changing the first index to XXX. What is the first index of the array B? Since it starts from here, it is trying to change the first index, the value of Paul, this part, to XXX. So now the value of Paul has been made XXX. Okay. And now we are printing A and B, and we are also printing the backing array. Now let's understand why are we looking at this example. Since we know slice is a reference type, and now you understand why do we call it a reference type. We have an array which is a fixed type and we cannot expand it, but we can slice from it. So we have 2 slices from the array names. One is A, another is B. Now this array, the array names, the slice A, the slice B, all 3 of them point to the same thing. All 3 of them have the same value. Names is the actual data type, and the slice A and B point to names. They are sliced from it, but they point to the same data. That's what you have to understand. A slice does not have the data for itself. It points to an array. It points to a backing array. In this case, all three of them have the same value in this position, which is Paul. And now any of them. So in this case, B has tried to make this value as XXX. Now what happens? This will change for all of them. This will change for all of them. A, B, and names. Now, if we run this, let's see what we get. Let's create this and try to run this. You can see in the first print statement here, in the first print statement, we are getting John, Paul, George, and Ringo. And after slicing, we are printing the value of A and B. And the same way we have John and Paul and George. Okay. Nothing has changed up till now. The moment B has changed the value of Paul to XXX, now we have printed A. Now A has John and XXX. We have printed B. B has XXX and George. And we have also printed the names. There's John, XXX, George, Ringo. Now this, since one of the slices changed the value in that index to another value, that value got reflected in all three of them. The backing array that contains the data, and all the slices that point to that array. Okay, that's the point that this example is trying to make. Whenever a slice which is pointing to some array changes some value in that array, the value of the array changes, and all the values in all the slices that are pointing to that array, they also change. We don't always create slices out of an array. We don't have to declare an array and slice from it. We can directly create a slice. Go provides us the ability to directly create a slice, and in the background, Go will create a backing array and it will give you a slice which points to that array. Okay, and that's how it will work. So this is the syntax using which you can directly declare a slice. You do not have to declare an array and slice from it. You can directly declare a slice, and this is called a slice literal. We are literally declaring a slice in one line. Okay, we have a variable declaration pattern here, with the colon equals to, and here we are saying it is a slice since there is no number in between the square brackets, which means it is a slice. That is the indication. That is the difference between an array and a slice. In an array type, you will find a number, which is the size, and it is part of the type. And in a slice, there is no number. It is a dynamic array. Okay. So this is a slice, and it is a slice of integers. And here we are providing the values during the initialization phase. And here we are printing it. In the same way, we are creating a slice of booleans. So we can only store true and false. We cannot store any other data type in a slice or in an array. It is a collection of homogeneous data types. In the same way, we can also make a slices of structs. So this is how the syntax looks like. You write a pair of square brackets, then you define the type. In the same way, here we have defined the type. You can integer, boolean, or a struct. If it is a struct, you have to provide the type of the struct. And the type of the struct is this. It has two fields, I and B. I is of type integer, B is of type bool. Now, right after, since it is an slice literal initialization of type struct, okay, we have to provide all the values that goes inside this slice of structs. So we can provide, we can follow this pattern. 2 will get assigned to I, and this true will get assigned to B. Same way, all the structs are initialized in these slices, and then we can print it. So let's run this and see how it looks like. Okay, and we can see all the slices that got printed here. And this, since this is a slice of structs, we can see all the structs being printed here in the Go's format. Now another thing is you can also slice from another slice. Here we don't have an array here, but you can create more slices out of this slice. Okay, and also we can modify, we can make changes to this syntax. We don't always have to provide the low bound or high bound. We don't always have to provide the start index and end. We can leave one of them and the other range will be implied. So for this case, we are saying we are slicing from the first index, from 0 to 2. And here we are saying we are slicing from index 1 up to the end. Okay, those things are implied here, and we can run this and see the example how it looks like. So we have 357 for the first, then 3, 5 and 5. Here for this we have 357 because we are indexing from here up to here, from index 1 to index 4. So we are taking 1, 2 and 3. That's why we have 357. From this we have this 3, 5 and 7. This is the value that we have. Then we can slice it again, and when we slice it, we are slicing from the first position, from 3 to the index 2. So 0, 1, 2, and we exclude the 2, so we have 5. We have 3, 5. That's why we get 3 and 5. And here we take this slice and we slice it again, and we are slicing from the first index. So this is index 0, this is index 1. So we are taking the first element is 5 and up to the end. And since this is the last element, we end it here. And that's why we have 5 here. That's how slicing works. And you can slice from an already existing slice. You don't always have to slice from an array. You can also slice from an existing slice. Now in this example, we take a look at lengths of slices. What we are doing here, we are defining a function called print slice. What it does, it takes a slice of integer as a parameter, and what it does, it tries to print it. And how does it format it? It is taking the length of the slice, and it is taking the capacity of the slice, and it is then taking the slice itself, and it is printing all three of them in this format. Okay, that's what this function does, and we use it here. We create a slice using the literal syntax. We say it's a slice of integer, and we provide all the integer values, and then we do the print. We call the print slice function, which displays the length, the capacity, and the value of the slice itself. The same way, what you're doing here is we are slicing from the start, because we have left the starting index from the start up to the 0 index, which basically means the length of 0. We don't want any elements because the last element is excluded, and we are starting from the start. We have now 0 elements. We don't have anything. We have an empty slice. Okay. In this print statement, we should have an empty slice. Now let's picture this, how it exactly works. So for the first, initially what happens, we have initialized a slice. So we have initialized a slice. So we have a slice here, and it has a backing array. But for the sake of this example, let's imagine this is the backing array, because when you initialize a slice literal, then the length and capacity of the backing array is the same as the length and capacity of the slice. So you can imagine this slice as the backing array. Okay, now we have 2, 3, 5, 7, 11 and 13. And these are the slots. Is index 0, 1, 2, 3, 4 and 5. Okay. And this is what S looks like initially in this print statement. So for this print statement, what will be the length? The length will be the initial length, which is 6. And what will be the capacity? For a slice literal, the capacity of the slice is the same as the capacity of the backing array. It has a backing array which looks exactly like this, because we initialized a slice using the literal syntax. That's why and that is the reason for the first print statement, we get length as 6 and capacity as 6. Okay. And when we print the slice, this is 2, 3, 5, 6, 2, 3, 5, 7, 11, 13, all the elements of the slice. Now moving on. At this point, what happens? What happens is we are saying we are starting from the start. Okay. We are starting from the start, but we go up till the 0 index. And since the last bound, the higher bound is excluded, we exclude the 0, 1. So in that case, we don't have any elements. So this is an empty slice. But what is the length here? For an empty slice, what is the length? Length is 0. Length is 0. As you can see, length is 0 because we don't have any elements yet, because the higher bound we mentioned was 0. What will be the capacity? Now, as we know, the capacity is the first element that the slice points to. In this case, it is 2, the index 0, up to the last element of the backing array. And this is the backing array for this slice. And that is the reason we have the capacity of 6. We have capacity of 6. And as you can see, the capacity of 6. Starting from this to this, we have 6 slots. The capacity is 6. Then what happens? At this point, we are saying we are starting from the start for this slice, this is the backing slice, okay? And this slice points to this. Now what happens? We are starting from the 0, 1, and we are going up till 4. And we are going up till 4. Now we are extending the length. Length was 0 here. And since we have a capacity of 6, we can extend the length. What happens when we extend it? From 0, we go up till 4. Now this is 4. So now we have 2, 3, 5, 7. We exclude the 4th index. We have 2, 3, 5, and 7. These are the elements of this slice. And what is the length here? The length is 4. That is the capacity here. The capacity is still 6 because starting from this, we go up to the last element of the backing array, which is this. That's why the capacity is 6. Okay, and we can see here length is 4, capacity is 6, and the elements are 2, 3, 5, 7. Now, what happens at this point? At this point, this is the backing array. Now, what happens this? Now here, this is the backing array, and we slice from this slice. We slice from this, but the backing array still remains the same. Okay, this is the backing array. What are we doing here? We are starting from the second index. So we are starting from here. Second index, we include this. We are starting from 5 and up till the last element. Now last element, not of the backing array, last element of slice. When you are slicing, we go to the last element of the slice. Okay, now what is the last element of the slice? Is 7. That's why we have 7 here. Okay, and what is the length here? Since we have 2 elements, the length is 2. And what is the capacity here? Now, as we know, capacity is the first element of the array that the slice points to. What is the first element this points to? This. We start from this and we go up till the end last element of the backing array. Okay, and what is the last element? 13. So how many capacity do we have? 5, 7, 11, 13. That's why the capacity is 4 here. As you can see, length is 2, capacity is 4, and the slice we print is 5, 7. This is how it works. Now, as we already know, in this case, Go assigns the 0 value of that data type. In case of a string, it is an empty string. In case of integer, it is 0. In case of a boolean, it is false. Okay. Now, what happens in this case? What is a 0 value of a slice? What will Go assign in this case? Since we are following this syntax, so ideally, if it is an integer, s's value will be 0. Since it is a slice of integer, what is the 0 value of s? Let's run this and you can see, okay, this is what we get. For this println statement, we are getting s. If you try to print s, it is printing an empty array or an empty slice. The length is 0 and the capacity is 0. So for a 0 value slice, a slice which is declared without an initialization value, the length will be 0, the capacity will be 0, and it will have 0 elements. But the thing to focus here is the value of the slice itself, not talking about length or capacity or the print statement. The value of the slice will be nil. When we try to compare it, if s equals to nil, we get inside and we print this statement because the 0 value of a slice is nil. So now the point here is 0 value of reference types. Reference types are nil. We already know 0 value of an empty string is a string in quotes. 0 value of a boolean is false. 0 value of an integer 0, and 0 value of an array is all the, let's say if it's an array like for integer, then the 0 value will be 0, 0, 0, 0. Okay, this is the 0 value of an array with size 4 and type integer. What is the 0 value of a struct? So let's say, okay, let's come here. We have a struct, and here we have a, it's an integer, and b is a string. Now, what is the 0 value of this struct? The 0 value of this struct is a 0 and b as an empty string. Basically, in case of an array and in case of a struct, the 0 value is that data structure with all the 0 values of the elements. Because an array is a fixed type with 4 integers, it's 0 value 0, 0, 0, 0. In the same way, since a struct has two fields with a integer, b string. Its zero value is a is 0, b is empty string. In the same way, we have reference types. What are the reference types do we have? We have functions, we have channels, and we have pointers, we have slices, we have maps. And since we are talking about slice here, the zero value of a reference type, which is a slice, is nil. It's a very important thing to remember. The zero value of a slice is nil. Now we saw the first way to initialize a slice, which is the literal syntax. So in this case, we saw that we can declare a slice and we can initialize it like this. A, and we have integer, and we have our curly braces. We have 1, 2, 3. Okay. And we saw we can declare and initialize a slice with this syntax, with the literal syntax. We also saw we can declare a slice using var and the name of the slice and the type of the slice. And for this, the value of the slice will be nil, the length will be 0, the capacity will be 0. For this, the length will be 3, the capacity will be 3. Okay. And the value will be 1, 2, 3. We have one more way where we can initialize a slice or declare a slice is using make. A make is a function, a predefined function. Make, M-A-K-E. It's a predefined function given by Go for initializing reference types. This is something to remember. Initializing reference types only. Okay. We can use make to initialize channels, to initialize slices, to initialize maps, all the reference types that we can use make to initialize, because we have a reason to use make instead of using the literal syntax. Why are we using make? So let's see that in this example. When we initialize a slice using make, what happens? So what we are saying is we are initializing a slice of A and we are saying make a slice. Make, you can take it as semantically, whatever it reads like. You're saying make a slice of integer. You're saying make a slice of integer, with the second argument. The second argument to the make is the length. This is how makes signature looks like. Make, it takes three things. First is the type. And what are we providing in the type? We are providing, it's a slice of integer. It is a slice of integer. Since we also use make to declare and initialize maps, to declare and initialize channels, so we have to explicitly say that it is a slice of integer. First parameter, first argument is a type. What is the second argument? Is the length. You can say what is the length of this slice going to be. Okay. Now we already know that slices are dynamically sized. We will see how the dynamically sized mechanism works. But initially, you are saying initially the length should be 5. Okay, you are saying the length should be 5. Now there is a third parameter. There is a third parameter called capacity. We already know the mechanism of capacity. We still have not gotten the exact use case of capacity, but we'll get it soon. Now the third parameter is capacity, but by default, if you don't provide the capacity, it will take whatever the length is. So in this case, the capacity will also be 5. So now we have a print slice function. What we are doing is we are printing the length, the capacity, and the slice itself. Okay. Now, in the first case, what should it print? Now that we have the theory, before you run the program, we can visualize it. For the first statement, for the first print, what we are doing, we're printing A. At this point, what's the state of A? The length will be 5 and the capacity will be 5. Okay, then now let's move on to B. What's B? Okay, now we are using make. What is the type? The type is a slice of integer. What is the length? Length is 0. What is the capacity? The capacity is 5. Now, you cannot provide a length that is greater than capacity. That is an error. Okay? That's something to remember. The capacity will be always same or greater than length. The capacity cannot be less than length. Okay? Since capacity represents the size of the backing array, So capacity will always be the same or greater than length. Okay. Now this is the state of B. Now when we call print slice, what should it print? It should print length is 0, capacity is 5. Also for A, I forgot to mention what will be the actual slice print. In case of A, since the length is A and it is a slice of integer, ideally it should print, A should print 0, 0, 0, 0, 0, 5 zeros, because the length is 5. What should B print? It should print an empty slice because the length is 0. So we don't have any slots to initialize it with. In case of A, the length was 5 and the type was integer. So the 0 value of a slice of integer with length 5 should be 5 zeros. Okay. Now C. Let's move on to C. We have C here. Now we are slicing C from B. What are the properties of B? You have length 0 and capacity as 5. Okay. And what we are saying, we are saying for C, we want to slice from the 0th index to the second index. Now C, now B has the capacity of 5. B has a capacity of 5. So let's imagine B has a capacity of 5. Now for C, B is the backing array. There is another backing array, but for C, you can imagine B is the backing array. What you're saying, we are saying starting from the first index. The first index is of course 0. We want to go up to the second index. So ideally we should have 0, 1, 2. Since we exclude 2, we have 0 and 1. We have 2 elements. Okay, we have 2 elements. Now what will be the elements? Since the length is 2, we are slicing 2 elements. Length is 2 and it is a slice of integers. We should have the 0 value of 2 elements, which is 0, 0. Okay, the length is 2. And what will be the capacity here? The capacity of the backing slice is 5. And we did not slice, see, we did not slice from first index or second index. We sliced from the very first 0th index. That's why the capacity does not change. The capacity only changes when you slice after the first index, after the 0th index. Any index which is more than 0, if you slice from there, then the capacity reduces. But it does not reduce when you slice from the end. Okay, that's a mental model. You don't really have to understand or memorize, but you'll get it after you use slices a little bit more. Now, what is the capacity here? Capacity is still 5 because we did not slice after the 0th index. We sliced from the 0th index. Now, what is D? For D, what we are saying, from C, starting from the second index, it has only 2 elements. We don't really have index 2, but we have capacity of 5. So we can slice up to 5 elements, because the capacity is 5. Okay, what you're saying, 2 to 5, since 5 is excluded, we print 2, 3, 4. Okay, print 2, 3, 4, but there are no values here. So we go to 0 value. What are the 0 value of integer? We have 3 zeros. It's 2, 3, 4 for index 2, index 3, index 4. What is the length now? Length is of course 3. What is the capacity? Now, since we sliced from the start, we did not slice from 0, we sliced from 2. Now the capacity decreases. Now, so 0, 1, 2, 3, 4, we had 5 indexes. Since we slice from here instead of here, this is gone. Now we have 3. The capacity is 3. From 5, since we sliced from index 2, now the capacity is 3. Now let's try to run this program. As you can see, for the first one, length is 5, capacity is 5. We have 0, 0, 0, 0, 0. For the second one, the slice is empty. Length is 0, capacity is 5. For the second one, we have 2 zeros. The third one, we have 3 zeros with length 3 and capacity 3. As expected, the same values that we saw in our figures. Another thing to know is we can have 2-dimensional slices. A slice can contain other slices. So in this case, what we are saying, we have a slice which is a slice of another slice, and that slice is a slice of string. So we are initializing with each slice, which is a slice of string, and we are providing different strings. So this is how you declare and initialize a two-dimensional slice. We have two-dimensional arrays in a lot of languages, pretty much every language. In the same way, in Go also we have two-dimensional slices. And if we print this, we should have some kind of matrix. And as you can see, we are printing a game of tic-tac-toe. Okay, and we can change the values using the x index and y index in different positions. That's pretty much all there is to it in two-dimensional slices. Whatever your intuition, whatever it sounds like. Initially, I said that slice is a dynamic array. And dynamic means we can extend a slice, extend its length, extend its capacity, and add more elements, remove elements, all the dynamic properties that are useful in a real world application. That's why we use slice more often than we use arrays, because of their dynamic nature. Now, how do they work? How do we actually add more elements to a slice after we declare it? So this is how it works. This is the syntax. We declare a slice and we are using the var syntax. So at this point, the value of the slice will be nil, and if we print it, it will be an empty slice, and the length will be 0, the capacity will be 0. Okay, and if in the first print statements, we should get the length 0, capacity 0, and empty slice. What happens here? We are saying we are appending to this slice the first argument. So append is an inbuilt function in Go, and it takes multiple arguments. The first one is the slice, which we want to append to the slice, and we are providing s here. What is the second argument? This is the element, the new element that we want to append to the slice, or that we want to push to the slice. And here the new element is 0. What happens? We had a slice which looked like this, with length 0 and capacity 0. Append does a lot of things, a lot of calculations behind the scenes, but on a high level, the reason we are provided with this function, we are provided, first thing, it takes the slice that we want to append to, takes the existing slice. As you can see here, we are providing the existing slice s. First thing, it takes the slice, and in the second parameter, it takes the new elements. Okay, and it also takes a lot of, you can also pass more arguments into the function. It is a variadic function. Go has a concept called variadic function, where a function can take any number of arguments. Okay, now append is a variadic function. You can pass any number of elements in the after you pass the slice. Okay, now second, it can take one element like it is taking now, 0, or it can take any number of arguments. It takes two things. What it does is, first it checks the length and the capacity of the existing slice. Now what is the length and capacity of our existing slice? It is length is 0, capacity is 0. Now if that is true, and since we are trying to add more elements into that slice, but we don't have the capacity for it. Okay, the backing array that we are using in this slice, the array does not have enough capacity to it. So what append does, it assigns another memory location, another backing array whose length is 1 and whose capacity is 1, and it returns that as a return value of append. Now you are assigning it to s. Now what happens? S has length 1 and capacity 1. What happens here after that? Then at this point, S has length is 1, capacity is 1. Now this is what S looks like as of now. Now what we are doing, we are calling append again, and we are passing 1. We want to append the number 1 into this slice. We pass it, and append checks the capacity of the existing backing array. And since the capacity is 1, we are trying to insert another element. So we need at least 2 slots. So for that, append finds another memory location, and it assigns another backing array. Now we have length as 2 and capacity as 2. And this is what the new slice looks like. And this is what we return, and we assign it to S again. Okay. Now at this step is what it looks like. And since we are inserting 3 elements, now append follows different algorithms to resize the existing slice. There are a lot of internal details there, but on a high level, there can be two situations. Either you are appending one element or you are appending a number of elements. You are using the variadic parameter. Now to understand that, so let's go to our notepad. Now, as I said, there can be two cases. One, you are inserting one element, or two, you are inserting variadic elements. Now, there are a lot of internal details, as I said, for resizing the slice inside the append function. Now we can actually take a look at how the code looks like, which resizes the slice using the append function. Now, if we go here, this is actually the code which does all the resizing of the slice and all inside the Go programming language. You can see there are a lot of internal details here, and there is actually a function which is next slice capacity, the function to calculate what is the capacity of the next slice. You can see there is a threshold of 256, length of 256. If it is smaller than that, it doubles it, otherwise it does something else and all. So there are a lot of things happening here, a lot of internal details. But to have some idea about how the algorithm works, we can take a look at some of these rules. So the first rule is, if it is a single argument, if it is a single element, first thing we know, we use append to resize, to add more elements to a slice. So let's say we have a slice with length 0, capacity is 0. We have an empty slice. Now, if we call append, s equals to, we take s, we pass it to append, and we add another element, let's say 1. What happens now? What append does in this case, since this is a single element, what append does, since the capacity is 0 at this point, it checks the size of the element. Since this size is 1, so append finds another memory location for the new backing array, and it finds the pointer to that, and it assigns that new pointer, and that array will have a length of 1 and a capacity of 1. The first time we call append on an empty slice. What happens the second time? Now this is what the slice looks like. We have 1 here, length is 1, capacity is 1. What happens if we call append again? We call append again with s and number is 2. At this point what happens? It finds, since the capacity was 1, we are trying to insert another element, so we need the capacity of 2. So it finds another memory location for the backing array, and it assigns the pointer to that, to the new slice, and now the length is 2 and the capacity is 2. We'll soon notice the pattern here. Again, let's try to append another element. Append s, and this is what the slice looks like in the previous step, 1, 2, now s3. Now at this step, what append does, since we have capacity of 2 and we are trying to insert another element, now we need slots for 3 elements. Now what append does, it tries to find another memory location for the backing array, and the length will be now 3, but the capacity will be the double of the previous one. So previously we had capacity of 2, now we will have the capacity of 4. Okay, so let's do one more time, then we'll see the pattern. Let's call append, then s, then we pass 4. Okay, and this is what it looked like, 1, 2, 3, and we call it once more. Now we had capacity of 4. Now we are trying to insert another element. We only have 3 elements as of now, so the append does not do anything. It has enough capacity to assign one more element. So now length will be 4, capacity will be 4, and this is what the array slice will look like, 1, 2, 3, 4. Now what happens here? One more time, call append, call s with 5. Now we have 4 elements, we have capacity 4, we are trying to insert one more element. Now we don't have the space for that. Now what append does, now the length is 5, capacity is 8. It is 8, and this is what the slice will look like, 1, 2, 3, 4, 5. Now we can see the pattern. When we are trying to insert single elements, append will try to double the capacity every time there is no space. It will try to double the capacity up to, as we saw here, up to the threshold is, up to the length is 256. After that, it will, as it is written in the comment here, it will, instead of 2xing, it will go in the 1.25x speed. It won't double it. It will go in the speed of 1.25 up to, it will only double it up to the length is 256 elements. After that, it will go 1.25x speed. It won't double the capacity. That is an internal detail. Now, that is one pattern. And if you want to see an example for that, here we are declaring a slice with 0 value, and we are starting a for loop. And in every iteration, we are appending the index into the slice. And then we are printing the length and the capacity of the slice in the print statement. Now let's run this, and we'll have a fair idea how the append works behind the scenes. Okay, now if we expand it, okay, let's focus here. Let's focus what's happening. In the first iteration, the length and capacity was 0. So append made length 1 and capacity and 1, and this, it is 1. In the second iteration, it inserted another index, and now the length is 2, capacity is 2. In the next iteration, when it was inserting, let's say first 0, then 1, then 2. When it was inserting 2, obviously the space was not enough, so it doubled the capacity. From 2, it went 4. Okay. Now, in the next iteration, it has enough capacity. It has the capacity of 4. So it can store one more element. So that's why we can see the capacity does not change until this. The length is 4, the capacity is 4. Okay. Now in the next iteration, when we are trying to insert the index 4, now it does not have the storage anymore. Now it needs to increase the capacity again. What it did, it doubled the capacity again. The append function doubled the capacity of the internal backing array. Okay. That's what's happening here. Now we can insert 4 more elements. Up until this, we had 4 elements. Now it doubled the capacity, so we can insert 4 more elements. Now at this point, we have 8 elements and we have capacity 8. As you can see, the length is 8, the capacity is 8. Now append has to assign a new backing array. It has to increase the capacity again. Now it doubled it. From 8, it went 16. Now, after this, we can insert 8 more elements. We had 8 elements, it doubled the capacity, and now we can insert 8 more elements without append having to increase the capacity, without append having to assign a new memory location. It can store the elements in the same memory location. So, as you can see, length is 10, 11, 12, 13, 14, 15, 16. Now, when the length and capacity matches, the capacity is doubled again. So this is the pattern you can see. Every time length and capacity become same, in the next append call, the capacity doubles. Okay, that's the formula. Every time length and capacity matches, in the next iteration, append will double the capacity and it will assign a new memory location for the slice, for the new backing array. And now why am I trying to explain these internal workings of how append actually works? What is the need of it? Because most likely, this is how you'll use. You have an slice and you call append again and again. Every time you have to add more elements. You never have to think about what is the capacity, what is the length and all. Those are internal details. You will never actually have to explicitly think about the capacity and all. The append handles all those details behind the scenes. But the reason I explained it, the reason I explained how it works, what are all the things that happens behind the scenes every time you call append, every time the length and capacity matches, is because let's take an example. Up until this, let's print the value of this. Let's clear this. Row, go, run, main.go. We have length 0, capacity 0, and there is an empty slice. Now, when we try to append another element to this and we call print slice again, Now what happens? Let's run this and we can see that length is now 1, capacity is 1, and we have one element in the slice. What happened behind the scenes? Append checked the capacity and it realized the slice, the backing array, does not have enough capacity to store one more element. So it searched for another memory location and it found another location for the new backing array, and the new backing array has capacity of 1 and length of 1. And as we saw earlier, if you call append again, it will do the same number of steps again, and the length will be 2, capacity will be 2, and it will keep reallocating. It will keep reallocating and finding new backing arrays. Every time you call append, it will try to double the capacity and it will try to do all those optimization steps to resize the slice. And all these internal calculations will keep happening when you start with a slice of 0 length and capacity. But let's imagine there is a scenario like this, when you know beforehand that you want to append to this slice 5 times. You know this information beforehand. And in this case, if you initialize with an empty slice with length 0 and capacity 0, and you run the iteration, it will work. It will definitely work. And if we can run this, and when we run this, we can see that it started with length 0, capacity 0. Then in the next iteration, capacity is 1. Next capacity is 2. Then capacity is 4. And then the capacity is 8. Okay. And every time you know that length and capacity matches, in the next iteration, the append has to do all these internal calculation. It has to find a new memory location. It has to find a new backing array with a double the capacity, and all this extra work. Every time reallocation happens because of the shortage of capacity. Now, if you know the maximum length that this slice can have, what you can do, one optimization that you can do to prevent append from doing all this extra work is this. Instead of initializing s like this, what you can do, you can remove this and you can use the short declaration form, and here you can use make. And you already know, if we use make, we can define a length and an optional capacity. Let's say we want length as 0 because we don't want pre-filled zeros inside the slice. Because if you define length as 5 and capacity is 5, it will pre-fill all those places with empty zeros. We don't want that. That's why we are saying length is 0, but capacity is 5. Maximum we'll have 5 elements, but for now, give us an empty slice. What happens if we run this now? Now, as you can see, the capacity from the first iteration is the capacity is 5. And we keep appending to it, and up until the last iteration, the capacity remains the same, because we already knew that we are going to append 5 elements max, and we just prevented append, the function, inbuilt function append, from doing all those extra calculations every time there was a shortage of space. So this is something you have to remember, that we'll use, especially this syntax, that if we know beforehand what is going to the maximum size of a slice, we can use this syntax to pre-assign a capacity beforehand to prevent append from doing all the extra work every time it runs out of space. Go provides us one more construct to loop over slices. We have a traditional method where we use a traditional for loop. We initialize a variable, we put a condition, we do increment in each iteration, and then we can print the index and the value using the index access method. This works. But Go provides us another construct. It's called range. And using range, you write a for, and with each iteration, Go returns 2 values. First one, the index, and the second one, a copy of the value. Not the value itself, a copy of the value. This is something you have to remember. If you make any change to this value here, it won't show up in the original slice, because this one is a copy in each iteration. And you can access the value of I and B here. And if you try to print this, you'll get this 0, 1, 2, 3, 4, 5, 6, 7. And if you don't want to use the index, then you can use the underscore. And if you don't want to use the value, you only want the index, then you can leave it apart. Okay. And if you want to take a look at some examples of slices in real world apps, then we can take a look at Fider. And we can see we have a lot of use cases. Here they are using the slice literal syntax to directly declare and initialize the slice in the same line. We have some make based syntax to initialize a string slice with length 31 and capacity 31. And similarly, there are a lot of use cases everywhere in the code. Slices are one of the most common used data types in Go, and you will see a lot of examples everywhere. Okay, here we have a range over slice. They're accessing the value of title in each loop and they're doing something with it, and a lot of examples like that. Now the next data type that we have is maps. Go offers a implementation of the data type hash map, which are also called dictionaries, hashes, hash maps in other languages. Go also has a similar implementation. It is called map. And map, a typical structure of a map is it has a key, which is mostly string, but you can also use other data types as the key. And it has a value, and inside the value you can store anything. Okay. Maps keys has to be comparable. So comparable basically means they have to satisfy the equality operator, so that a map keys can be compared with each other. They have to have that property. That is one restriction of maps keys. And in the value you can store anything in a map. Okay. And usually we use map whenever we have a use case where we want to find things quickly. That's the mental model you should have. A lot of people get confused with when to use struct and when to use map. Struct is your typical use case whenever you want to store something, whenever you want to parse data from a JSON. A lot of use cases. In pretty much 70% of the time we use structs. Struct are for storing values, for efficient storing values in the format of Go's native data types. In map also you can store values, but we use maps when we want to find things quickly. Okay, because maps have the lookup time of 1, lookup time and adding time and deleting time. All these, it's a very efficient algorithm to look up things and to add things and to delete things. That's the reason we use hash maps or maps in Go to perform those kinds of tasks. Now let's understand with an example how they exactly work. So what are we doing here? We have a struct, we have a type struct, and it has two fields. One is lat and second is long, one for latitude, one for longitude, and both are of type float 64. Okay, this part we already know. Then we are declaring a variable in the package level with using var syntax. The variable name is m and it is of type map. A map with key as string and value as vertex. So whenever you are declaring a map type, you have to explicitly say what is going to be the type of the key and what is going to be the type of value. Now here we declared a map. Now as we already know, map is a reference type, and every reference type has the zero value of nil. So at this point m's value is nil. Okay, now here what we are doing, we are ignoring whatever the zero value is. We are using make. As I said, every reference type can be initialized with using make. So we are using make to initialize a map. We are not providing any length, capacity and all. We are just initializing a map using make. Then using this index based syntax, we are storing a structs instance. A structs instance, a struct of type vertex. We are storing this struct in the key bell labs. Okay, this is how you store things in a map. And then we are printing it. And if we run it, we get the value of the struct. Okay, that's how maps work. You initialize a map, you store things in the keys, and you can access them using this index-based syntax. The set and get pretty much looks the same way. Now there is another syntax of initializing maps. Instead of using make, you can also use the map literal syntax. Map literal syntax basically means you just write the type and you provide the initialization value right away in the same sentence. So we are saying we are declaring a map whose key is string and the value is vertex, which is of type struct, and we are providing the keys and the values in the same line. Okay, this is another syntax to initialize maps without using make. How do you manipulate values and keys? How do you manipulate keys and values of a map? We have some of the features provided by Go. As you know, we can initialize a map using make. And also, one thing to remember when using maps are, you only have two ways to initialize maps. First, you can use the make syntax, or you can use literal syntax. Third, if you try to initialize a map using var, which we do with other data types like integers, strings, and slices and all. If you initialize a map, declare a map using var syntax, and if you try to assign a key in that map, then you will get an error. You will get a panic. You only have two ways of declaring a map. Either use make syntax or use a literal syntax if you know the initial values already. Okay. We can actually see this. In this example, as you can see, I have declared a map using var syntax. Okay, as we typically do with other data types like slices and integers and booleans and strings. I have declared the map using var syntax, and then I am trying to assign a key to the map. Since it's the key is of type string and the values are of type integer, I am assigning key 1 the value of 9. And then I'm trying to print this. Then what happens if I try to run this? We get a panic. We get an error that assignment to entry in nil map. Since using var syntax declares the zero value of a map, and the zero value of a map is nil. That's why we get this error that assignment to entry in nil map. What can we do in this case? We have two choices, as I said. Either we can do this, we remove the var and we do short assignment, and then we use make. Then make, and then you do this, and then we try to run this. Then we get the appropriate behavior. We have a map and the key has the value 9. We have one other choice. We can do this. If you don't want to use the make syntax, we can write the type, then we can provide a curly braces. This is the literal syntax. Okay, and if you try to run this, we get the similar behavior. So as I said, when using maps, either use make or use the literal syntax. Those are the two choices that you have. Never use var to declare a map unless you know exactly what you're doing. Okay, now we have this example where we are looking at some examples of manipulating the keys of a map. Now here we initialize a map using make. And since we are using make, we are safe to assign keys to the map. Now we are assigning a key answer and we are assigning the value 42. Now we are assigning this another value to the same key. And let's try to run this, how the program behaves up to this point, up to the point here. And let's see the behavior. Now if we run this, so first we have the value 42. Because we assigned 42 here to the key answer. And in the next print statement, we are assigning 42 and we can see the value 42. Then what happens? We have a predefined function called delete. And using this, we can delete values from a map for a particular key. So when we delete a value and then we try to print the value for that key, we'll get the zero value of that type. Since it's an integer, we are getting 0 here. Now, the question here is, how do you know that whether this key answer has the value of the number 0 or the value is absent, the value does not exist? That's why the Go language is giving you the default value 0. How do you differentiate between the absent value and the 0 value? That is the question. So for that particular use case, Go provides this construct. You can try to access this value of a map using this syntax, the index space syntax, which returns two values. The first one is the value If the value exists, then you'll have the value here. If it doesn't, it will have the 0 value here. Then it also returns a boolean, and you can name it anything. The convention is to name it OK, so that other engineers are also aware that you are checking the existence of this value. Now we can, if the OK is true, then we'll know that the value exists, and whatever the value, even if the values is 0, we know that it exists, and that is meant to be the value. It is not an absent value, it is not a default value, that is meant to be the value. 0 is the value of the key answer. If it is false, then we can ignore the value and we can proceed further with whatever the expectation is. We can know that the value is not set for this key. And that's pretty much all about maps. We can do other things with a map. For example, let's say we have this, and let's remove this. And what if we want all the keys and values of a map? So we can use the range construct that Go provides to loop over slices that we can use for maps also. So let's say we write for, in the first result, it will give us the key, then it will give us the value. And in the short declaration after that, we write range, and we want to range over M. This is a map. And here we can print this fmd.println. We can write key, comma, value. And if we run this, here in the last print statement, as you can see, the key is answer and the value is 42. And using this, we can range, we can loop over maps, and we can access all the keys and values. If you don't want the key, you can use the underscore identifier here, like this, if you only want the values. And if you only want the keys, then you can get rid of that part. Now this is how you iterate over a map. Now another concept that I want to mention here is, let's say there are some confusions when you're starting out, that when to use map and when to use structs and all. So maps and structs have a lot of differences. For example, you cannot do this with a struct. You cannot loop over all the fields of a struct, because struct is a static type in Go. You already know all the fields and all the values of a struct somewhere. It is already written. You don't have to loop over it. That is the first difference, that you cannot range over structs, but you cannot range over, but you can range over maps. Second, all the values inside a map, like this is not a variable. This does not have a fixed memory location. You cannot use this to initialize a pointer, because this does not have a memory location. On the other hand, every struct field has a fixed memory location, and you can use that everywhere, and that memory location will be fixed, because map internally uses hashes and buckets and a lot of internal algorithms to hash and to do lookups and to add keys, remove keys and all. So they don't have fixed memory locations. The memory locations keeps changing as we add more keys and more values. That's the reason the memory location of maps are not fixed. The third thing is also this part. When we are iterating over maps, the order in which we get the keys are not fixed. They are intentionally randomized so that you don't depend on the order to be the same. If you want the order to be the same, you have to explicitly sort the keys yourself. That's also something to remember about maps. And coming back to this, another difference between map and struct is just the use case, that we use structs to store data. That is a very oversimplified definition that I have come up, but this is the idea on a very high level. And we use maps to look up. That's a mental model you can use whenever you want to differentiate between maps and structs. So let's go and take a look at what some real world maps look like, how people use them. Then here you can see there are a lot of use cases of maps people are using in all for parsing random JSONs into structs and mapping HTTP headers there, because HTTP headers can be of any type, right? There can be a lot of different types of headers and you don't know all the types. So in those scenarios, you cannot use a struct. You have to go with a map, because you want to assign any string and for the key and any string for the value. This is one perfect use case for maps that we typically use for. And there are others for whenever you want to parse any kind of JSON into a Go data type, then you can go with map. If you don't explicitly know the keys and values of that JSON, in that case, you can unmarshal it into a Go map. Then you can access it. Okay, so there are a lot of different use cases for maps. Another concept after that I want to cover is in Go, functions are first-class citizens. And by that, I mean there can be anonymous functions also. So here we have a function declaration which does not follow the typical function declaration that we have here. Here we have the func keyword, then we have the name of the function, then the curly braces start. We don't have the same structure here. What you're doing, since functions are first-class citizens, you can assign a function to a variable right inside any function. So what we are doing here, we have a variable, we are using the short declaration form, and we are assigning a function to that. What this function does, it takes two parameters, x and y, which are of type float64. It returns the same type, float64, and it actually does this math calculation. It does x into x plus y into y, and it calculates the square root of that and returns it. This is what this function does, and we are assigning this function to this variable. Now we can use this variable's name to perform the calculation. We can use this variable as this function. And as you can see here, we are calling this with two arguments, 5 and 12, and this will be x, this will be y. Okay, so this is one of the features of functions being first-class citizens. You can assign functions, you can assign anonymous functions to variables. Now, the second thing, we have a function here. We have a function here which takes another function as a parameter. We can also do that because functions are first-class citizens in Go. We are taking a function as input, and what this function's signature is, it takes two float64 and it returns one float64. And if you see, this signature matches this signature. We don't have to write the name of the variables here because this is just a signature of the function. Okay, and this is used as a parameter of another function, and in this case we don't have to write the variable names. Okay, it takes another function as a parameter and returns a float64 value. And in the function execution, what it does, it uses this function to do some calculation with 3 and 4, and it returns the value. Okay, and because of that, because it takes any function and it passes 3 and 4 inside that, that's why now we can use any function whose signature matches this. So for now, we have this function whose signature matches this. We can pass the hypot, this function, inside into this function compute, and we will get the result. The same way, we have an inbuilt function which is math.power, which has the similar signature. As you can see, math.power, we has x float64, y float64, and it returns a float64. Since the signature matches, we can also pass this function inside this. And if you try to run this, we will get expected results. We have a print statement for this line, then we have this line, and then we have this line. And this everything works in a very smooth manner. And this is a very nice feature of Go. And we can do a lot of composition by passing functions inside other functions and a lot of other advanced features. Because we can pass functions into other functions, Go provides another nice feature called closures. Now, if you are a JavaScript developer, you're coming from a JavaScript background, or any other programming language which has the same feature of closure, which I'm not aware of, I'm aware of JavaScript, then you'll get it. It works exactly the same as other languages, the same as JavaScript, the same way closure works in JavaScript. But if you are a beginner and Go is your first programming language, or you are coming from a programming language which does not have the concept closure, then I would say don't take it too seriously. Don't try to understand everything around it. Just know that this nice feature exists and they are used in a lot of places, in a lot of libraries. You might not use it explicitly, that you won't think like now I'll use closure for this, but closures are used implicitly in a lot of places. So just know the concept that it's there, and it's not a big deal if you don't understand it right away. Now, this is how it works. This is how closures work. We have a function, and this function returns another function, and this function has access to the variable of the outer function. It has access to sum. Now, because of that, even after this function returns, it has access to a state called sum, which it can keep using. And let's use this example to understand how exactly this works. So let's first run this. Okay. We have different iterations. Let's go through the iterations first. Now, first, we are initializing two variables by calling these two functions. The result of this will be assigned to this. The result of this will be assigned to this. Okay. And the positive, and both of these are different functions of this instance, this type, which takes an integer and it does this calculation with sum and it returns the sum. Now what happens in each iteration? We come inside, now I equals to 0, and we call this function, the positive function, with I. Since I equals to 0, sum equals to 0, sum plus I, which is 0. So here we see 0. And in the same way, in the negative call, we are multiplying I with -2. And we know multiplying anything with 0 is 0. That's why we are also getting 0 here. In the next iteration, now here I's value is 1. Before that, I's value was 0. That's why I got 0, 0. Now I's value is 1. What happens now? It comes inside, it calls this function positive of I. And then we go here, x is 1. Now sum plus 1. Now since sum is 0, sum plus 1 is 1, and return sum. So now this is 1 for this part. Now for the negative part, we -2 into 1 is -2, and -2 is here. -2 plus 0 is -2, and then we see -2 here. Okay, that is this iteration. Now in the next iteration, I's value is 2. We come here, we call positive with the value 2. Now what is the value of sum? Now the surprising part is sum's value does not start with 0 here. Sum actually remembers the previous call, and because this positive is the same instance of calling this function, it will remember the state of sum across different function calls. That is what closure means. Closure basically means if we have a scenario like this where an outer function returns an inner function, then that inner function will have access to the outer function's variables even after the outer function returns. Okay, and because of that, the inner function can use this as a state across different function calls. That's the reason in the next iteration, when I's value is 2 and we pass 2 inside positive call, now in the previous iterations, sum's value was 1 and it remembers that. That's why 1 plus 2 is 3, and we see 3 being printed here. That's what closure basically means. It's not a concept that you will explicitly use everywhere, but it's still an important concept and it's used in a lot of places, and it's good to have the knowledge that how it works or it exists basically. Now Go provides a feature called methods, which allows us to assign functions to types, any type. It can be struct, it can be integer, it can be string, any type, any custom type, as long as that type is defined in the same package. That is the condition that we have to match to assign methods to a type. Now we'll typically see types being assigned to structs, but there are also use cases of types being assigned to user defined types, like custom types that take from integer or strings and arrays and all. Okay. Now, how does it work? How do methods work? Let's first look at the syntax. We have a struct here, which is, and whose name is vertex. It has two fields, both of type float64. Now, in the next line, we are defining a method on the type struct. What it does is, this part is the same as a function declaration. Okay. If we had a function called ABS, then this is what it would look like. it would have a name, it would have a braces, and then have a return type and the execution statements. This is a typical function declaration. But a method is different from a function in a way that before the name of the function, we have the receiver. This part is called the receiver. And this type, and whichever type this matches, then we will say that we are defining a method called ABS on the type vertex, because in the receiver, we have the type vertex. That's how we assign a method to a type. That's about the syntax. And then we have here available V, which is of type vertex, which is a struct. And this is an instance of the struct, not the type itself, but a concrete instance of the struct. And usually we write a short variable because we'll again and again have to access that, but you can make it readable also. It is not that important. And using this, we will have access to the fields of the structs here. We have access to the fields of the struct, whichever struct we are calling this method on. Now, in order to see the use of this here, we are declaring a variable v, and please don't confuse this with, this is a parameter, this is a variable declaration in another function scope. Now we are declaring a variable which is of type struct, a struct called vertex, and we are assigning 3 to x, and we are assigning 4 to y. Now v is a struct, and now what we are doing, now since v is a struct of type vertex and we have defined a method on the vertex struct, now we can call the method using this syntax. We can do a dot and then we can call the method name ABS. And when we do this, this instance of this struct will be passed to this function, this method. And in this place where we have v, this value will be passed. This instance of the struct where x's value is 3 and y's value is 4. So this is how it works. And if we run the program, we can see 5, because after the calculation, the answer is 5. Now, instead of that, what if we comment this out and we define another function which works pretty much the same as this one, but it does not have a receiver. It is not a method on a type. It is a normal function. And how do you call a normal function? We just pass the struct inside it. And what if we call this? We have the same result, 5. Now, what is the difference? Why did we define a method on a struct? Now, there are a lot of reasons for defining methods. So if you come from a object-oriented language background, then you can relate with the idea of methods with class methods. You have a class and there are methods associated with it. And every time you call a method on an instance of a class, then you have that method limited to that scope. So if you come from an object-oriented background, then it will be a pretty clear idea to you that what is the clear distinction between methods and class methods. Now, using methods, we can assign some behavior to a type so that it is very clear that we have a type and this type has all these behaviors, all these capabilities. It forms one kind of a documentation, and it also has some readability advantage and a lot of other advantages that methods offer. But on a high level, you can simplify it to that level, that it offers some advantages over using normal functions. Now, as I have already mentioned before, that we can use methods on other types also. So we have a type here, type, any name. We are saying my float. This is the name of the type, and it is of type float64. So this is how we can define custom types, user-defined types in Go. We have a custom type here, and we can define methods on this type also. It does not always have to be a struct. We can also define methods on custom types, any user-defined type, any type in Go. Okay, and this is how it works. You define a method, and it takes a receiver. And every time you call an instance of this type, so f is an instance of this type, we are initializing it. And when we call this with ABS, it passes this instance to this receiver and we get the result. So the idea is you can define methods on any type, any concrete type. We'll come to interfaces, but you can define methods on any concrete type in Go. Now, when you are defining methods on a type, the receiver, this part, it can be a value which looks like this, or it can be a pointer which looks like this. It basically has a star in front of the type. Now, what is the difference between the two? If you have a value, then whatever calculation, whatever change you do here, it won't be reflected in that instance of the struct that you call the method on. Okay. Every time you call a method, you pass this instance of the struct into the receiver. Okay. That's how methods work. You initialize a struct, and whenever you call this method, this instance gets passed into this receiver. Now, if it's a value receiver, then whatever change you make to this variable, which is of this type struct, this is an instance of this type, it won't reflect in the original instance. But if it is a pointer receiver, then whatever change you make to this struct, will reflect on the original instance. So that is the difference between a value receiver and a pointer receiver. Now, if we run this program, we get 50. Initially, we were getting 3 and 4. By passing 3 and 4, we are getting 5. We got 5 in the previous result. But we used this function scale, this method scale, which actually changes the fields of the structs. And then when we call ABS on it, we got 50 because we scaled it by 10. So this method actually changed the value of these two fields. That is the difference between a value receiver and a pointer receiver. Now, at this point, we can see another advantage of using methods instead of functions. Why do we have methods and how are they different in behavior when compared to functions? Now, we have a function which pretty much works exactly the same as the previous methods. What happens if we remove this star? What happens if we say that v is a value? Now we will get an error here which says cannot use %v value of type pointer vertex as a vertex value. We cannot assign a pointer to a function which is expecting a value. Now, in order for this to work, we have to also remove this. Now we are passing the value, but now the behavior also changed. If we run this, we'll get 5 instead of 50. Now, to see the differences between methods and functions, we have one method here with a scale method defined on this struct. We have one function here, normal function, which is another method. And here what we are doing, we are initializing a struct of type vertex, and we are calling the method scale, And here, as you notice, it is expecting type pointer, but here we are calling the method on a type value. We did not have to do this. V dot scale. We did not have to call the method with a pointer. But in the same way, when we are calling a function, if we remove this, if we pass the value, then Go will throw an error. That cannot use variable of type vertex as a pointer. But in case of a method, Go automatically did the pointer indirection. Go automatically pass the pointer to the method instead of the value. So basically, Go internally did this, converted this into this before calling this method. That's a nice advantage of using method, that you do not explicitly have to think about whether the signature of the receiver matches the instance that I am calling the method on. It can be a value and the receiver can be a pointer, and it can be a pointer, the receiver can be a value. It will do the pointer indirection and it will call with the value. You do not explicitly have to worry about that. Go takes care of it, so that this syntax is pretty readable. Because if you compare, if we had to do this p dot scale, if we had to do this, then it looks very ugly as compared to just p dot scale. So that's why, depending on your use case, depending on the context that it is getting used, Go automatically converts this instance whether to a pointer, or if it is a pointer then to a value, using either ampersand p or star p, depending on whatever the signature of the receiver is, so that the program is more readable. That's all it offers. It makes the program more readable by automatically referencing and dereferencing the pointers. Now the question is, when do you use pointer receiver and when do you use value receiver? How do you make that decision? So there are two things that can help you choose whether to go with a pointer receiver or to go with a value receiver. First, if you are mutating any value in that struct instance or to that type, it can be struct, it can be an integer, it can be a float, string, anything. If you are doing any kind of mutation and you want that mutation to reflect on the original instance, if you want the result of the mutation to show everywhere that struct is being used after calling the method, then use the pointer receiver, because using a pointer will actually change the value. Otherwise, if you use a value receiver, it will just create a copy of that and pass it to the method instead of passing the actual variable, instead of passing the actual instance of the struct. Second thing, if it is a very large struct, if it is a huge struct, let's say fields of hundreds and like 50 or 100 fields, in that instance, if you call the same method again and again on that struct, then Go internally has to assign memory locations for all those fields. The fields can be slices, the fields can be other structs, other arrays, integers, floats, complex, any kind of data type. It has 50s and hundreds of fields. In that scenario, every time you call the method, it has to create a copy of that struct and pass it into the method. So that is a little expensive. Now, it is not a huge performance degradation, but it still affects your system in some kind of way. So if you know explicitly that the struct is very large and you want to avoid making copies again and again, then in that case, go with pointer receiver. Otherwise, go with value receiver. So those are two thumb rules that you can use. Now, the last thing to remember is, once you make some method, for instance, we have scale method on this. For this, we want to mutate the instance of the struct. That's why you are using pointer receiver. Now, after this, we want to define another method called ABS. Now, ABS returns a new value. It does not mutate the existing instance. But since we already had a method which was pointer receiver, after that point, we cannot, or we can, but we should not use value receiver anymore. We cannot use value receiver anymore once we define a method with a pointer receiver. So the convention is either make all the receivers pointers for all the methods of a particular type, or make all the receivers values. Do not mix. If you mix, very bad things happen because of very subtle bugs that we will see later. But this is something to remember. Once you make one receiver pointer, you have to make all the receivers pointers. Otherwise, bad things happen. Okay, just remember these three rules. If you are mutating, go with pointer receiver. If you want to avoid copying a large struct, go with pointer receiver. Or if you made one method a pointer receiver, always go with pointer receiver for all the methods. Those are the three rules to remember. And those three rules will help you to decide whether to go with pointer receiver or to go with value receiver. Now, in order to understand methods with a real world example, we are again in the FIDER open source repository. Now we have a struct here, whose name is user, and it has different fields. It is most probably coming from a database. Okay, that's why it has ID, name, tenant, email, role, providers, and all these things. And we have different types, and we have JSON tags to parse it properly. Now the thing to focus here is, for this user struct, they are defining, in fact, some methods. And if you take a look at these methods, so this method has provider. What is it doing? It is taking an instance of user whenever you call a user struct, an initialized user struct. With this method, it will pass the instance of that user into this method. and it will have a argument for the provider string. And what it is doing, it is ranging through all the existing providers of a user. So we have an array of providers inside for this user struct. It is ranging through, it is looping through all the providers. And if it has an existing provider with the same name that we are passing here, then it returns true, otherwise it returns false. Now, for this, if you can ask a question that there is no mutation happening here, there is no mutation happening here, then why are they using a pointer receiver? Now, there can be multiple reasons, and we won't know it for sure unless we read the whole code base, but we can take some guesses. We can take a guess that maybe struct is very large, or there is another method on this user struct somewhere that mutates the user instance, and because of that they had to use the pointer receiver, and after that point they had to make all the receivers pointer receivers. So as I said, you have to either make all the receivers pointers or values. You cannot mix and match. So the reason can be anything. Okay, and we won't know unless we read the whole code base. So for now, let's just focus on the methods and why are they used and get the feel of it. Why are we declaring methods on this user struct? In the same way, there is a method called isCollaborator, which basically checks whether this user's role is a collaborator role or it's an administrator role. In the same way, administrator is another method, and it checks whether this user's role is a administrator role. Now, by looking at these examples, you can take a fair guess that why methods are important. So if we did not have methods, if we did not have the concept of method, what we would do, we would declare different utility functions. So we can say we declared a function called user has provider or is user collaborator, okay, or is user administrator. And you can see the pattern here that every time you create a new utility function, you have to explicitly name the function in a way that it is clear that this function is supposed to be used with a instance of the user struct. Okay, otherwise it is very confusing if you just create a utility function with the name has provider, and if someone new in the code base, someone new comes in, then there is no way for them to understand that what is supposed to be the scope of this function, where is this function supposed to be used. And having methods provides this semantic advantage that we have a type user, and a user can have a lot of behaviors. A user can check whether it has an existing provider. A user can check whether it is a collaborator. A user can check whether it is an administrator. And now we don't explicitly have to name the methods is user administrator or is user collaborator or is user has provider, etc. Because it is already in the scope of user, and whenever we call it, we will call with user or u dot has provider or u dot is administrator. We have this predefined scope, and it makes things very easy to read. It makes things very easy to process, and the flow of the program is much more simpler. So using methods provides a lot of advantages like this, and as you build more programs with Go, you'll see a lot of advantages along the way. Now we have a very interesting concept called interfaces, and interfaces are something that is very deep into Go's philosophy, and you'll find interfaces everywhere in the standard library, in all the packages, and it's a very important concept to understand. And for now, as long as you understand the basics of it, even if you don't understand completely, it's fine. And we'll use interfaces in our projects, and when we are reading code, we'll look at a lot of interfaces and we'll see how they work. So for now, let's just understand the basics and move on. Let's not spend a lot of time here because interfaces can be a little tricky to understand in the first look, and you get the feel of it as you work with it more and more. Okay, so let's understand what's happening here. For now, we have a type here, and it is not any other type. It is not a struct or integer or string or anything. It is of type interface. Now, what goes inside the interface type? Inside the interface type, we have methods. We have method signatures. That's all there is to it, to interfaces. We have interfaces, and inside that we have method signatures. Now, how do they work? How are they useful? To understand that, let's dive into the example. Here we are declaring a variable of type interface, of type this append interface. We have a variable of type append interface. Then we are declaring another variable of type myFloat. This type is here, and since the order does not matter where you declare the type and where you use it, we can declare the type later after the main function. So we have a type here of myFloat, which is of type float64 internally. This is a user defined type. Okay. Now we are using that type here, and we are initializing it with this predefined function. And if we hover over it, we can find the value of the function. It is some floating point value. Now we are initializing a struct of type vertex. And if we take a look at below, we have a struct called vertex. And this vertex struct has a method assigned to it. Its name is abs, and it takes a receiver of pointer to vertex, not the value, pointer. And it does some calculations. In the same way, for the myFloat type, which is a float64 type, we have a method which calculates the absolute value and returns it. We have two methods, and for this we are using value receiver. We have a myFloat type, we have a vertex type, which is struct, it is a float64. Now going back to this, what we are doing, we are initializing a vertex type. Now what we are doing, we have a variable a, which is of type this interface. Now we don't know what interface does yet. We just know this is of type this interface. Now to this variable, we are trying to assign f, which is of type myFloat, and it works. We don't get an error. Ignore this yellow line. There is some linting error, but we don't get any error here. We can assign the type myFloat to the variable a, which is of type append. Now, if you remember, initially I told you that since Go is a statically typed language, we cannot assign one variable of one type to another variable of another type. We have to explicitly convert the type. But here we are not converting myFloat into append, which is of a different type, even though it's an interface type and we don't know what it does, but it is of a different type in Go, and it should throw an error, but it is not throwing an error. We can assign f to a. That is the first thing to notice here. Second, we are taking v, which is an instance of type vertex, which is struct, and we are assigning the pointer of that variable to a, and that also works. We can assign it to this. But now here we see the behavior. When we try to assign v instead of the pointer to v, when we try to assign v itself to a, we get an error. And if we hover over it, it says cannot use v, variable of type vertex, as append value in assignment. Vertex does not implement append. Method apps has pointer receiver. Now this is the important part here. Vertex does not implement append because method abs has pointer receiver. Now we can assign pointer to v to a, but we cannot assign v, which is of type this struct, to a. Why? Because pointer to vertex has a method called abs, but it is a pointer receiver. It is not a value receiver. That's why we can assign a pointer to vertex to a, but we cannot assign a value to a, because only the pointer implements this method. This method is assigned with the pointer receiver, not the value receiver. That's the reason we cannot assign the value to a, which is of type interface. Now, on a high level, what do we understand from this? We understand that an interface type basically provides some kind of behavior that a type should have to implement that interface. This is what interface means. An interface basically gives you a signature that this is the signature that a type should have to implement that interface, to say that that type satisfies this interface. Unlike other programming languages where we also have abstract classes and we also have interfaces, where in order to use them, we have to explicitly write things like implements, or we have to explicitly use some kind of syntax to say that this type implements this interface. But in Go, the speciality of Go is that as long as there is a type myFloat, and it has a method whose signature and whose receiver matches that of the interface, then we can say that this type implements appser. Since interface has a method whose name is ABS and its return type is float64, in the same way myFloat has a method. It's a concrete method and it returns a float64 and it matches this signature. That's why we can assign an instance of myFloat to a variable which is of type this interface. Okay, now myFloat satisfies appser. That's the word to remember. myFloat satisfies an interface as long as it has all the methods that this interface defines. It does not have to do any kind of explicit mapping to the interface. It is implicitly satisfied. So that's a very important concept to understand. A interface in Go is implicitly satisfied by other types as long as they have those methods assigned with them. Now we could not assign the variable v to a because in here the method is assigned with the pointer receiver, and since now v was a value here, we could not assign v to this. That's the basics of interface. We use interfaces to provide some kind of abstract signature beforehand or afterhand. It does not matter. It is an abstract signature that a type can satisfy as long as it has all the methods assigned to them that the interface provides, that the interface asks you to implement. Now here in this example, we have a struct of type T and it has a value which is called S and that is of type string. And we also have an interface type, which is basically a set of rules. We have a set of rules that any type which has a method called m assigned to it will satisfy this interface. That's what it says. Any type which has a method called m assigned to it will satisfy I. It can be assigned to any variable whose type is I. Now, T struct has a method called m and it is doing some basic printing. It has a value receiver. And now here we are declaring a variable of type I, not of type T. We are declaring a variable of type I, and to that variable we can assign a struct of type T. We can assign it a struct of type T to a variable whose type is the interface I, because T implicitly satisfies the interface I because it has a method called m and it satisfies this signature. And now after this we can call the method m using this variable I, which is of this interface type I. Okay. That's how interfaces behave. Now there is some theory to understand here, that what exactly is an interface type, what does it exactly consist of. So you can think of interfaces as some kind of containers, and that's what they are. Interfaces are basically containers which have two properties. One is dynamic type and the second one is dynamic value. Okay, and an interface itself, let's say when you declare a variable where I of type interface I. When you do this, we already know that whenever we declare a variable in this way, Go assigns the zero value of that type. And what is the zero value of an interface type? It is nil. Zero value of an interface type is nil. And when you do this, you can actually call the method I.m here, because an interface has a signature and it has a bunch of methods that you can call on that interface. But in order to call those methods, an interface has to have these two properties inside it. Only after a concrete implementation of that interface is assigned to the variable of that interface, after that only we can call these methods, and after that only it will be valid. Because an interface, when you declare an interface in this syntax, it is an empty container. It is of type nil. It does not have a dynamic type. It does not have a dynamic value. But in this case, when we assigned the type t, we assigned t, which is a struct. When we assigned an instance of the struct to I, when we did this t hello, only after we did this, then we were able to execute this method i.m. And what it did was, after you assign this instance of the struct to the interface, now this container is not empty anymore. It is not nil anymore. Now, this container has two things. One is a dynamic type. That dynamic type is this struct. This struct type is this interface's dynamic type. This is of type t. And its dynamic value is that instance of the struct, which has this field called hello. And now the interface is not empty anymore. Now you can call methods on this interface and it will work as expected. But what happens when you declare an interface and you call it right away without assigning a concrete implementation of that interface? What happens when you call it without assigning a concrete implementation? Now let's test that and confirm our theory. Here I have declared a variable of type I. I is an interface which has a method. Now the program will allow us to call this method m on this interface because it has a signature and it has the method m. But when we call it, when we run this program, we get this error. We get this error which says this. It says nil pointer dereference. We are basically trying to access a memory location which does not exist. It happened because interface at this point, interface is empty. It does not have a concrete implementation. Only after we do this, only after we assign a concrete implementation which satisfies that interface, because of the same method signature. Only after we assign it to this variable, then if we call it, if we call the same program, then we can see hello. What it does, the interfaces behind the scene, it tries to access this type of type t, then it accesses this field and it passes this receiver and it calls this function and we see it in the console. Okay. So basically interfaces are just containers. They provide you with some behavior that you have to satisfy, but they themselves don't have any data. They have to be assigned some data. They have to be assigned a concrete implementation before they are usable. If you call it before that, it will be an error. Your program will panic and it will break. That is something you have to remember. Now, I said before that interfaces are everywhere in Go. And because of the nature of an interface in Go, because of the nature of satisfying behavior, we have a very useful construct which is called an empty interface. This is a type which is called an empty interface literal. Now, what is the property of this type? What is the behavior of this type? When you have a variable or when you have a parameter of this type, you can assign anything to this variable. The Go static type system will not stop you anymore because it is an empty interface. And as we already know that an interface is satisfied as long as you have all the methods that the interface asks you to implement. And since an empty interface has no methods, it has 0 methods, then any value in the Go's type system, any type satisfies this interface. That's the reason we can assign any value to a variable of type empty interface. And that's what we are doing here. We are declaring a variable with type empty interface and we are assigning different values. We are assigning a string here, we are assigning a value here, and it all goes through. It does not stop us. In fact, if you take a look at the signature of printf, it says ... any, which means you can pass any number of arguments. It is a variadic function, which means it can take any number of arguments of type any. Now, any is basically an alias for type interface. So if you take a look at Go code, this is how any is defined. So you have to type any, and it has interface. So any is just an alias for interface to make things a little easier to write. Okay, and all the print statements use the empty interface or the alias any to take any number of arguments of any type. It does not matter what the type is, they take anything. That's why they are using empty interface or the alias any. Now, when you use this empty interface construct, when you want to assign any value to a variable, in some cases it might be useful, but when you actually want to use it, since it's empty interface, you don't know what exactly is the value inside it, what exactly is the type inside it. And since Go is a statically typed system, it will not let you use the variable until it knows what type it is. And to confirm the type of a variable, which is of type interface, it can be any interface, we have this feature called type assertion, which is basically a way to cast a value of one type into some kind of interface. It is basically checking whether this type is of this type, whether this interface is of this type. Okay, so let's just look at this example to understand this better. What's happening here? We are declaring a variable which is of type empty interface, which means we can assign any value to it. It can be string, boolean, number, anything. And here we are assigning a string here to this variable. At this point, what we are checking, this syntax I dot and a type name. This syntax is basically saying whether this variable I is of type string, whether this variable I is of type string. If it is of type string, until here it says interface, but after the type assertion, we have the type string here. And if you print it, you will get the result. And in order to provide some kind of assurance that this type assertion was successful or it was failure, or this variable does not satisfy this type, in order to provide that mechanism, this type assertion provides two values. The first is the new variable, which has the type this, the type that we are trying to assert to, and a second variable, which is a boolean, which says whether the type assertion was successful or not. Okay, and using this, you can check the value and the success or failure. What happens if you use a type assertion? What we are doing here, we have a variable which has a type empty interface, which means any value can be assigned to it, and we have assigned a value string to it, and we are trying to convert a string type to a float type, and we are asserting this type. We are saying if this variable is of type float64. We are also doing it here, but here we are doing it without this boolean. Now, if you do it like this, the program does not break, the program does not panic, it does not error out. We have an OK, which is false, because a string value cannot be converted into a float value in any way. But in this case, we are not taking the boolean. So the behavior in this case is the program panics. If you're not taking a boolean in the second value of return type, then this program will error out. And if we try to run this, it is not a compile time error, it is a runtime error. Then we see the results here up to this point, but when we execute the last statement, we get a panic because we tried a types assertion without taking the variable OK, without taking the result of the variable, whether the result was success or it was a failure. Now, to assert to this type again and again is a little cumbersome. That's why Go provides a very nice construct for us to systematically check a list of types that we want to satisfy to, and if it matches one type, then we can perform whatever operations that we want to perform on that type. So for that, we have this example. Here what we're doing, we have a switch statement, and in this switch statement, we already know that in the initial part of a switch statement, we can call an expression. So it is calling this expression and it is doing a type assertion. So this is basically a type switch. This is something you'll find a lot whenever empty interface is used. And this is a type switch. What it is doing, it is tying a assertion here at this statement, and this type, the actual type of this variable, this I, will be assigned to v. And then we are checking different cases. We are saying find out the type, the dynamic type of this variable I, and check whether it is an integer or not. If it is an integer, then come to this and break out of this switch statement. If this is a string, then come to this and break out of this switch statement. If it does not match any of these cases, then come to this and execute this default statement and break out of the switch statement. And then what we are doing, we are trying this example where we pass a integer first, then a string, then a boolean. So if we run this, we get different results. For the first one, we are doing some integer calculations. Since the type here satisfies integer, we can do mathematical calculations here. Until this point, we cannot do anything with I. We cannot do anything with I. Let's try to do something here. Up to this point, we don't know the exact type of I. So if you do this, I equals to I plus 2. If you do this and if you hover over it, it will say invalid operation I plus 2 mismatch type interface and integer. Basically saying you're trying an integer operation on a type which is of type empty interface. You cannot do that. Okay. And in the same way, if you try to call length on I, if you hover over it, it will say invalid argument variable of type interface for built-in type length. You cannot call length on this type interface. Basically, you cannot do anything with this type unless you cast it explicitly to some type, some basic data type or to some complex data type, anything. You have to explicitly cast it to some type. Since Go is a statically typed language, you can use this construct. You can use this empty interface to pass a value of any type. But when you want to use this, when you want to use that value, you have to explicitly assert it to some type. It can be integer, string, boolean, or anything. And a type switch is a very nice way to conditionally check different types and to perform different operations depending on that type of this value. And as you can see that in the first function call, it was an integer. That's why it landed here. In the second one, it is a string. That's why it landed here. And in the third one, it is a boolean. That's why it landed in the default case because we were not handling boolean. Okay. And now since we know about interfaces and we know about type switches and different types of dynamic types, there is a concept that is used heavily across the standard library of this interface type, which is called stringer. Now there are two things to notice here. First, in the standard library or in different places where people are using interfaces, you will see this pattern that all the interfaces are ending with this suffix er. It's a stringer or a printer or a downloader or something, a er suffix, because of the behavior. Because interfaces define a set of behaviors, this er thing, this er suffix conveys that emotion more explicitly. So this is one thing to notice here. Second is a stringer interface is defined in the standard library. So this is what it looks like. Let's clear this. We have a type in the standard library which looks like this type stringer, and it's an interface. It starts here, and inside that there is one method which is called a string method. Okay, and this is an interface which is defined in the standard library, and it is used heavily everywhere. Basically, a type, it can be any type. It can be a struct, or it can be a user defined type of type integer, float, string, anything, a map, anything. Now that type is called to be a stringer. It's called to be implementing stringer as long as that type has a method called dot, as long as it has a method called string. Now it is important because in the previous example we saw that using a type switch we can check that whether a variable satisfies an interface or not. Okay, we can check that. So in functions like this, in functions like sprintf and printf and println, if you take a look at this, they take variadic arguments of type any, which is an alias for type interface, empty interface. Now they demand that whatever you pass, they can be any value. That's the reason they have said any, which is an empty interface. They can be any value, but they have to satisfy the interface stringer, which means they have to have a method which is called string. So in this example, we have a struct. And it has a method. What this method is doing, it is taking the instance of the struct and it is printing the name and the age using %v. Basically, it has a string method which represents this struct in a string format. That is the reason we can take this instance of the struct and we can pass it to println, because now this struct satisfies the interface stringer, which this println, printf, sprintf functions require. They require your type to implement the stringer interface, which means your type has to have a method called string. Now what happens if we comment this out? What if we run this? Now if you run this, they use its internal representation. Since this type does not implement stringer interface anymore, they have some default representation of how a struct should look like, and that's how they're printing it. Okay, they don't follow this format anymore. But if you uncomment this and if you run this again, now if you see, this format matches this method, because when you pass any type to println, what they do, they check whether this type implements stringer interface, which means whether this type has a method called string. If it does, then they call that type's string method. If it does not have a string method, that's when we commented it out. It will use the default representation of the any struct that Go has internally. Okay, so that is another thing to keep in mind. Now we have another interface, a very famous interface, which is called error. And you will see this everywhere in Go. This statement, if error is not nil, do something. If error is not nil, do something. Since Go follows this principle of explicit error handling, it follows the principle of explicit error returning errors as values and all these principles related to errors. Go has an interface called error. It has an interface called error, and it is an interface. And since we know the zero value of an interface is nil, that's the reason we can check that whether it is an empty interface, or if there is an error in that, or if there is a concrete representation of some type which satisfies error and it is present in that. Okay, and let's look at this example to make this more clear. Now here we have a type struct which has two fields, when and what. When is of time.time. There is a package called time, and it is of type time of Go of time. There is another field called what. It is of type string. Now this struct has a method associated with it called error. It's called error, and it takes a pointer receiver and it prints the when and the what with using fmd.sprintf. By the way, sprintf basically, it does not print the formatted string into the console. Instead, it formats the string and it returns it if you want to return it. It basically constructs a new string. It does not print it or anything. That's why you're using sprintf. That's what this error method is doing. Then we have this function run, and it basically returning an instance of this struct with these two values, time.now, which basically takes the current time, and string call, it did not work. And in the main function, we are executing this function, and if it returns an error in the signature, we are saying this function returns an error. We are executing this function and we are saying in the signature that it might return an error. That's why. And it returns this error type. And there are some things to notice here. First, we are declaring a custom type, which is called myError. But when we are returning from this error, it is not a myError type. We are returning a generic interface called error. Now, error is another interface like stringer, which is defined in the standard library of Go, which is provided by Go. And it looks something like this. It looks like this. Type error, and it starts. And inside that, it has a method called error. As long as any type in Go, it does not matter it's a struct, integer, float, string, map, does not matter what type it is, as long as that type has a method called error, like we have here, it is of type this interface. It satisfies this interface error. So we can use that type in place of this type. That's what basically interfaces do. As long as you satisfy the signature of an interface, you satisfy the requirements of an interface, you can use your type in place of that type, in place of that interface type. So having that in our mind, this function, this run function, it says in the signature that it is returning a type of error, is an interface, but it is returning a concrete type. It is returning a type struct, but that struct has a method called error, and it is doing some kind of formatting, string formatting. And now the reason we are returning an interface instead of saying in the signature, instead of saying the return type is of type my error, the reason we are returning an interface is because of this. When the caller, the function that is calling this one, the main function, it calls run. When it calls it, it checks whether the value of error is nil or not. And since we know that an empty interface has the value nil. Since we have this knowledge, since this is the fact, what now we can do is, every time we run a function, if that function returns an error, then we can check if the error is nil or not. Since it is an interface, if it is not returning an error, if it is returning nil, then this case will be false and we will proceed in the success flow. And if it is returning some value, it does not matter what value, it has to satisfy the error interface, and it returns some value, some concrete implementation, then the error is not nil. In that case, we will succeed with the error flow. Those are two reasons we use error interfaces everywhere in our program. That's all about interfaces that we need to know as a basics to start out writing more programs. Now, there are a lot of different behaviors to interfaces, and there are a lot of concepts associated with interfaces that we will explore as we learn more, as we read more code, as we write more code. But as of now, that's pretty much all you need to know. Now let's take a look at some examples of how people use interfaces in real world apps. Now going back to our example, you can see there are interfaces everywhere. People are using interfaces to define behaviors, to define methods, get email, get name, get user, get kind. Interfaces are used to define behaviors everywhere in the codebase. Now, there are a lot of different use cases associated with it. One particular use case that interfaces have in a real world app, in a backend app, is when you are writing test cases. As we know that in backend systems, we have different layers of system. We have, let's say, in the base layer, we have repositories. Repositories. Above that, we have services, and above that, we have controllers. Repository layer basically deals with all the database operations, all the database queries and inserts, removing all these core database operations. And the service layer uses this repository layer to mix and match different business logic with different repository methods. So it can execute some repository method like create an entry in database. Then in this service layer, it can send an email, it can send a notification, and it can schedule a task. All these things are responsibility of service layer. It basically orchestrates different repository methods with business layer. And then there is the controller layer, which deals with HTTP related stuff. Like it receives the body, it receives the query parameters and all, it parses it, it validates it, and it passes on all those input arguments to the service layer, and whatever things that are returned from the service layer is passed on to the controller layer, and it sends those responses appropriately with appropriate HTTP status codes and appropriate data format, and etc. etc. Thus the overall flow looks like in a typical backend layer. Now, some backend system might not have a service layer. The controller might use the repository layer, but it's just all about terminologies. Typically, we have 3 layers. Now, we have this repository. This is an open source repository called Incubator Answer, and you can take a look at it. This has very good patterns that you can learn from and scalable patterns, scalable backend patterns that I personally use to learn a lot of stuff. So anyway, we can see here that there is an interface here. We have an auth service, basically a service which don't need to understand any of the code, just focus on what I am explaining here. Okay, we have an auth service which basically deals with different operations related to authentication. Okay, we have an auth service. It's a service layer. Above that there is a controller layer. Below that there is a repository layer. Now this auth service in argument in its parameter, to initialize this auth service, Go has a very good dependency injection convention. We will explore more about dependency injections and all in later videos when we are building projects, when we are reading different project codes. Now, what dependency injection basically means, instead of directly importing the auth repo, you take the auth repo implementation as a parameter, and then you return this instance of auth service which has all these methods. So this is a struct. A struct has different methods associated with it. If you scroll down, this is all these methods in this user service struct. Okay, we have explored methods just a while back, so you should have some idea that what's happening here. And what's happening, it is taking an implementation of auth repo, the repository layer for authentication, and it is returning a service, auth service, with auth repo inside it. Okay, that's what's happening here. This is a constructor, you can say the initializer of this auth service struct. Now here auth repo is not a concrete implementation. It is not coming from a struct. This auth repo is actually an interface that is declared in the service layer itself. There is one convention when you are dealing with interfaces, when you are declaring and using interfaces, which are always, interfaces should always be on the consumer side. Now, of course, there are exceptions to it, very valid exceptions, not very rare also, but it's a general thumb rule, a very generic thumb rule that works most of the times, that an interface should always be on the consumer side. What do we mean by consumer? Whoever is using that interface, they should declare the interface, and the producer should satisfy that interface instead of the other way around. The producer should not define an interface and export it. The consumer should define the interface and the producer should satisfy the interface. Now, auth service takes an interface instead of a concrete implementation, instead of a concrete struct, because the reason is, in a typical backend system, you have all these services, repository, methods and all, a lot of functionality. Now, every time you change something, you have to test all the previous functionality, that all the previous functionality is intact or not, whether you broke something or not. And in order to do that, we have tests, and we write tests to verify if all the previous functionality, all the present functionality is intact or not. Now, during testing, what happens, you have a local database. You have a local database, and you have a production database. You have a database for tests. Now, if auth service took a concrete implementation instead of an interface, it is very difficult to replicate all these, to test all these methods during tests. So there are different types of tests. There are unit tests. We have not gotten tests yet, but on a high level, there are unit tests, there are integration tests, and there are end-to-end tests, end-to-end tests. During unit testing, when you are unit testing services, when you are unit testing your business layer, you don't actually want to make database calls. Let's say you want to make your tests faster. You don't want to spin up a Docker container, and you don't want to do all those database queries and all those inserts operations. You don't want to test with a real database. What you can do, since we are taking an interface instead of a concrete implementation, instead of a concrete struct, what can happen in this case, when we are unit testing our services, the caller, the test which is testing this auth service, it can pass a mock. It can pass a mock struct. A mock struct, let's say it is called test auth repo. And this struct has all these methods, all these same methods. And that is the reason it can pass that struct to this auth service, because this auth service takes an interface. And as long as The struct that is getting passed as a argument, it satisfies that interface, we can pass it. The Go compiler will not throw an error. And so during testing, what happens? We create a mock repo instead of the actual auth repo, which calls all these database methods, which makes all these queries and inserts and operations, deletes and all. We create a mock repo. What it does, it instead of doing database calls, it just returns strings. It returns hard-coded strings, or it does some very simple calculation and it returns in-memory structs or in-memory slices instead of doing actual database operations. Now, what is the advantage do we have? During our actual production deployment, what we can do in our main code flow, not our test code flow, in our main code flow, we can pass the actual repo, which has all the database related methods, which has the concrete implementation of database related methods. Now, during our CI/CD pipelines, when we are calling our tests, there what we can do in another code flow, we can pass the mock. Now, both this actual database repo and this mock repo, both of them implement this interface. Both of them implement this interface. That's why we can pass both of them to auth service. Now, auth service does not care whether it is a concrete struct or not. It just cares about that it satisfies this interface as long as it has these methods and it has these parameters and it has this return values. It will call the auth repo like this, and depending on what is the actual implementation, whether we are in the main code flow or whether we are in the test code flow, depending on that, whether we'll get a hard-coded value during tests and we'll get actual database value during our main code flow, during our actual production environment. Now, that is a huge advantage. If you are someone who has written tests before, this reduces a lot of boilerplate code. It makes the program flow much cleaner, since we don't have to use any external testing libraries or packages to create mocks and all. Go natively supports all those mocking and all because of the interface design pattern. Okay. Now, that is just one of the use case out of hundreds of use cases that interfaces do. We already saw different cases, like we have stringer. Because of stringer, we can pass anything to printf, and as long as that type, it can be struct, integer or string or boolean, anything, as long as that type has the method string, we can pass it to printf or sprintf or any of the print function. Same way, as long as any type that has the method error, it satisfies the error interface and we can treat it as an error. In the same way, there are a lot of interfaces in the standard library. We have io.reader, we have os.file, a lot of interfaces. Because of this interface's implicit satisfying nature, there is a lot of composition that we can achieve using the interface pattern. And we'll explore that more when we are going through different resources, when we are reading more open source codes, and when we are building our own projects. That's all about interfaces for now. Now, there is a very new concept in Go language, which are called generics. Which are called generics. And in order to understand why do we have generics and why did we need generics in the first place, let's see how did we get there. So in this example, we have two functions. We have index int and we have index string. And index int returns the index of x in a slice of integers, or -1 if it is not found. In the same way, index string returns the index of x, a string, in a slice of strings, or if it is not found, then it returns -1. A typical implementation of finding index of a integer or a string. Now, what does the implementation look like? We are ranging through this slice of integers. We are ranging through it, and we have the key here, we have the index here, we have the value here, and we are checking for each iteration. We are checking if the value is equals to x, if the value is equals to the target. If it is true, then return that index, this index. And if the loop finishes and we reach the end statement, we are returning -1. The same way, this is what you notice here. In the same way, we have this code for I, v are ranging through the slice of strings. The only difference between this function and this function is, here it is a slice of integers, and here it is a slice of strings. That is the only difference we have. Here the target is an integer, here the target is a string. Now we are doing the same operation. We are trying to find the string. If it is found, we are returning the index. If it is not found, then we are returning -1. Now, how are we using it? Here we have a slice literal with a couple of integers, and we are calling this function with this slice and a target 15, and output is 2. Same way, we have a slice literal of type string, and we have 3 strings, and we are passing hello, which is not in the slice. That's why we'll get output -1. Now, the thing to focus here is we have two different functions which do the exactly same thing. The operations are very similar, almost exact. The only difference is their types, these types. Here it is an integer, here it is a string. Now, and because they are of different types, we had to write the same implementation twice, and that increased the boilerplate code. And this is the reason we have generics. Generics help us reduce this boilerplate code by providing what we call type parameters, which basically means we can use types as parameters. As far as now, until now, we have been using values as parameters. Now with generics, we can use types as parameters. So let's look how using generics, we can reduce this code. Here we have gotten rid of those two functions, index integer and index string. Now we have a single function which is called index. Now there are 3 new additions here. What we are doing here, the first part, this is where we declare the type parameter, where we pass the type. Okay. And here we are saying we are declaring a parameter called t. You can imagine it as a declaration. We are declaring a parameter called t, which has the constraint comparable. Now this basically means the type has to satisfy the constraint comparable, which basically means that whatever type it is, it has to be comparable, which means it should be able to compare with, like it should satisfy the equality operator. We should be able to use equality operator on that type. That's what we are saying. We are putting one constraint on this type, that it cannot be any type. It has to be comparable type, which means it has to work with the equality operator. Okay. Now this is the type parameter declaration. Now, once you've declared this parameter here, now we can use it in the function parameters. This is the type parameter, this is the function parameters. Here we are saying whatever type is provided here, we are taking a slice of that type, and in the next parameter, a single variable of that type. Here it is a slice of that type, it is a single variable of that type. All of this will be dynamically assigned during compile time. Here we are just saying it can be any type as long as they are comparable. Okay. Now after this, pretty much the implementation is same. We are looping through it and we are checking it, and if it's true, we're returning the index, otherwise we are returning -1. Now how does this work? Here we have a slice literal of slice of numbers, and we are passing this slice to index, which is a generic function. Now in the same function, we pass a slice of integers, and to the same function, we pass a slice of strings. And because it is a generic function, and we did not have to assign, we did not have to explicitly pass the type of t. We did not have to say that here t is a integer or here t is a string, because in most of the cases, Go compiler is smart enough to derive, to infer the type. Whatever type we are trying to assign here, it is able to infer that type using these two. It checks that SS is a slice of strings and this is a string. And using that, it can deduce that in this function implementation, the t will be string. And using this nice feature, now instead of 2 functions, we have one function, one generic function, which can handle both string type and integer. That's one use cases of generic function. Now generic are a pretty new addition to the language. They were not there from version 1, and they were added later on. So you might not use generics as extensively, when you are starting out, but you will definitely see different implementation, different use cases of generics. That's why it's a good thing to understand why do we have generics and what do they do, how do they work. And there isn't a lot of things in generics, as long as you understand that we have type parameters and we can use that type parameters in the return type also and in the function parameters also. And using this feature, we can reduce some amount of boilerplate code as long as the implementation is the same, as long as the function body looks similar for two functions. That's a typical use case of generics. That's all we need to know as of now. We'll see more generics as we proceed through different resources. Now, finally, we reach concurrency. One of the strong points, one of the strong selling points of the language Go. And there is a lot to say and there is a lot to understand in this topic. And as I said in the initial part of this video, this is one of those topics in the language where if you're a beginner, you should not try to understand everything. If you do that, that will only intimidate you. Of course, if you get all the concepts and if you're comfortable with all the concepts that Go has to offer in this topic, then that's fine. Then that's great. But if you don't get it, then that's also fine. If you get some of it, then that's fine. If you don't get any of it, then that's also fine. We'll explore more and more resources later on in this series, and eventually you'll get it. Eventually you'll get the hang of all the constructs that Go has to offer in this area. Okay, with that, let's jump into this example of Go routines. Now, what's happening here? We have a function called say, and it is taking one string. It is taking one string and it has a for loop. Inside the loop, it is looping 5 times starting from 0 to 4. And in each iteration, it is blocking the execution. Time.sleep blocks the execution and it is blocking for 100 milliseconds. We have a constant called time.millisecond for each millisecond, and we are blocking for 100 milliseconds in each iteration. And after blocking for 100 milliseconds, we are printing that string, whatever string that has been passed to this function. Now it happens 5 times. For each function call, it happens 5 times. Okay, now what's happening in the main function? In the first line, we have this function. We are calling this function, but before that, we are adding this prefix called go. And then in the next line, we are calling this function normally. Now, what does this go do? This syntax, go and then calling a function, this actually spawns a new Go routine which runs concurrently with the main Go routine. Now, there are some concepts to understand here. In every Go program execution, whenever we are running a main function, a new Go routine is created. It's called the main Go routine. And everything that gets executed sequentially, that happens in the main Go routine. So this part, the say hello, the normal function call, and all the examples that we've been seeing so far, all of them have been executing in the main Go routine. Now, Go provides us this construct called Go routines. Then what is a Go routine? Go routine is basically similar to a thread that are offered by other programming languages, but it is very different from a thread. To wrap your head around the concept, you can think of it as a thread, but Go routine is something that is managed by the Go scheduler. It is managed by the Go scheduler. It is not managed by the operating system. Now, that's one thing that is a difference between a Go routine and a concrete operating system thread that is offered by other languages. Number one, they are not managed by the operating system. They are managed by the Go scheduler, the Go runtime. Go has a dedicated component, which is called a scheduler, and that manages all the scheduling and running of Go routines, the blocking of Go routines and everything. Number one difference is Go routine is managed by the scheduler. Second, one of the advantages of using Go and using concurrency primitives in Go is Go routines are very lightweight. And what do you mean by lightweight? Typically, when we spawn threads in other programming languages, which are operating system threads. Threads are pretty heavy. A typical thread, depending on the implementation, depending on the language, they might range from a 256 KB to 1 MB of memory in stack. Now each thread takes up this amount of memory. Now, on a high level, this might not seem a lot, but when you spawn a lot of threads, then it can cause your system to run out of memory, and it can cause memory leaks and a lot of problems if you are not managing your concurrency workflows efficiently. Now, Go routines, which are provided by the Go runtime, they are advantageous in this scenario because they are very lightweight. A typical Go routine has a size between 2 KB to 4 KB, is starting size, and they are dynamically resized, which means they are not fixed. Depending on the requirements of the Go routine, depending on the memory requirements, the allocation requirements of the Go routines, they can resize themselves up to whatever size they're needed, from hundreds of MBs to GBs, depending on the system requirements, until the system runs out of memory. Now, that is the second advantage. Go routines are very lightweight, and Go routines are managed by the Go scheduler instead of the operating system. Those are 2 points. Now, that's about Go routines. But why do we need Go routines in the first place? Go routines are the Go's way of providing concurrency features. Now, what do we mean by concurrency? Now, a lot of languages provide concurrency in their own way. JavaScript provides concurrency using the construct of event loop. And different languages have different implementation of the concept concurrency. So what do we mean by concurrency in the first place? Concurrency is basically managing execution of different tasks efficiently so that it does not block the system flow. Now, that is a very abstract definition of concurrency. Now, whenever we talk about concurrency, a different topic also comes into discussion, which is called parallelism. There are a lot of resources. There is a lot of debate surrounding the difference between concurrency and parallelism. And you can explore that to understand the concepts that surround them. But on a very high level, parallelism is a hardware feature we can imagine, and concurrency is a software feature. It is something that is provided by your language, your software, your system, is an operating system, whatever. And parallelism mostly depends on your hardware, depends on your CPU cores. How many CPU cores do you have? Because concurrency is executing tasks in the most efficient order to have the minimum amount of latency, to not waste resources of CPU, to not waste resources of memory. Okay. Concurrency does not mean that two tasks are being executed parallelly. Okay. Concurrency basically means if you have, let's say, 4 tasks all spawned at the same time, then depending on your system's implementation and depending on your language handling capabilities, those 4 tasks might get executed in any order. The order is not specified when we are talking about concurrency. Now, these 4 tasks can be executed in any order. The first, the second, the fourth, then the second, then third. At a time, one task might be executing, and if your system supports parallelism, then at a time 2 tasks or 3 tasks might be executing. But that is completely different from concurrency. Concurrency is basically executing your tasks in a most efficient order. The order is not specified. It depends on your implementation. It depends on the programming language. But parallelism is truly executing tasks in parallel. Like both tasks are getting executed in parallel in your CPU cores. Okay, that's basically a high-level introduction of concurrency versus parallelism. And now, as I said, there are a lot of resources that you should explore. A lot of resources in YouTube. For example, very good talks by Rob Pike, one of the co-founders of the Go programming language. And a lot of other resources that you should definitely explore. I don't have the capability and definitely don't have the time to get too deep into the concurrency philosophies and the parallelism versus concurrency debate. So this definition should be enough. Now, circling back to where we started from, Go routines are Go's way of providing concurrency features to the users of the language. Now, Go routine is the primary component which provides the capability of concurrency. And the thing to remember is every Go program execution starts with the main Go routine, and other Go routines are spawned from the main Go routine. And the moment the main Go routine returns, the moment the main function returns, all the Go routines are abandoned and they will be collected by the garbage collector and all, but you won't see the execution, the results, whatever you are expecting from them, because as long as the main Go routine is running, all the other Go routines are executing in concurrently with the main Go routine. So you can imagine it as this is the main Go routine and this is the execution flow of main Go. And during the execution, we can spawn different Go routines from main. For example, we spawned 2 Go routines here from main. Okay. And those Go routines can spawn more Go routines during their life cycle. And it can go on and on. But at the end, the main Go routine has to wait for all these Go routines to finish. Otherwise, you won't see the results. You won't see whatever results that you are expecting from these executions. Even though these Go routines are running concurrently with the main Go routine, they cannot run independently outside of the main Go routine. They depend on the main Go routine to wait for them. That's something to remember. Now, with that basics, now we can jump into the example of what's happening here. We have a function and we have the syntax called go. And whenever we call a function with this syntax go, this language spawns a new Go routine which executes concurrently with the main Go routine. Now, when we run this example, this is what we see. Now, other thing to remember is once you spawn a Go routine, there is no guarantee. There is no way to know for sure that if this Go routine started executing immediately or if the next instruction, whatever the instruction in the main Go routine executed at that point of time. You cannot say. The moment you spawned a Go routine, there is no way to know for sure that which statement executed first. Now we can just imagine to distinguish between those two. In the Go routine that spawned from the main one, we are printing world. We are printing world 5 times with a blocking time of 100 milliseconds between each iteration. And in the main Go routine, we are printing hello 5 times with a blocking time of 100 milliseconds with each iteration. Now, if we look at the results, this is what we find. First, we see world, which means the moment we spawn this Go routine, it started executing immediately after the 100 millisecond blocker. Then we see world, then we see hello, then we see world, then we see hello, then we see world, then we see hello, hello. So if you look at it, there is no specific order. As I mentioned, concurrency means the order is not specified. It depends on your implementation and it depends on your language. Now Go promotes this philosophy, CSP, communicating sequential processes, which basically states that, which is very different from how other programming languages approach concurrency, which is basically by sharing state. Now Go promotes a different philosophy, which states that don't communicate by sharing memory, share memory using communication, which is a very abstract way of saying instead of using shared memory or shared state to implement concurrency, you should depend on communication between different threads, or in this case, communication between different Go routines to implement concurrency. Do not share memory, because sharing memory for historical reasons, from historical evidences, we have experienced that sharing memory or sharing state gives birth to a lot of problems if you are not someone who is expert at implementing concurrency primitives. Problems like starvation, problems like deadlock, and all these problems. can be avoided using communication as the means of concurrency implementation. Now, all of those problems do not just go away, but the philosophy, the mindset of sharing state using communication can prevent a lot of those bugs. It does not prevent all of them, but the way they are structured, the way they are implemented, the way they promote people to use it, they can avoid a lot of those bugs. There is a very small room for making classical or historical mistakes when it comes to concurrency. That's why Go has this primitive, Go has this construct called channels. And channels are, in one line, channels are data types. They are data types which allow two Go routines to communicate with each other, which allow two Go routines to send data to each other. That's a very revolutionary idea, and you can do your own research to study all the materials surrounding it. But that's the philosophy behind it. Instead of sharing state, instead of implementing mutual exclusion, Go also has construct for classical implementation of concurrency for like concepts like mutual exclusion and mutexes and semaphores and all. But Go promotes heavily the idea of channels. And the idea of channels are, in most of your concurrency based implementation, try to see if you can solve the problem using channels, which basically means try to see if you can solve the problem using communication between two Go routines. Instead of using primitives like semaphores and mutexes, try using communication as your first approach to solving concurrency based problems. That's why we have channels, which are basically data types, so that two Go routines can communicate between each other. Now, that's what's happening in this example. Let's explore this. We have a function called sum, which takes a slice of integers called s. In the second parameter, we have a variable called c, which is of type channel, and it is a channel of integer, which means a channel is basically one hierarchy above other data types. So a channel can be thought of as a container. Channel itself is not a data type. Channel can be thought of as a container data type, and you have to specify what kind of data goes inside the channel. So if we think about channels, if we think of channels as these tunnels, we have one Go routine and we have other Go routine, and we want to send data. Okay, we want to send data. Data might be this side, that might be this side, and this data we have to specify what kind of data goes in these channels. So it can be integer, it can be string, it can be any kind of Go data type. So a channel has to specify what kind of data goes inside the tunnel, what kind of data Go routines will send each other. That's what we have this integer. This basically says this is a channel which will have integers inside it, which basically Go routines will send integers using this channel, using this tunnel. Now, inside this function, we are declaring a variable called sum, and then we are ranging over this provided slice, this slice of integers, and we are basically calculating the sum and storing it here. Then after we are done, we are sending the result into this channel. As I said, channels can be thought of as a tunnel where we will send data. Two Go routines will send data to each other using a channel. That's why after we have this result, we are sending our data through this channel or this tunnel. You can imagine channels as tunnels. You are sending the result into this channel. Now, another thing to focus here is this signal, this part. We use this construct, this angular bracket and a hyphen to send data to a channel. This is the syntax that you have to remember. Now, moving on. Then we have the main function, which is the entry point of our program. In our main function, we have a slice of integers, positive and negative. Then we are declaring a channel. Now, as I said, channel is one of the reference types. We have 5 reference types. We have slices, we have maps, functions, channels, and pointers. And channels are one of the data types, which are of reference types. And as we know, reference types can be declared with a make syntax. So we declare a new channel with make and we say it is a channel of integers. Then what we do, we spawn two go routines. As we saw in the previous example, we can spawn new go routines from the main go routine using the syntax called go and the function call. What you're doing, we are taking, since it is a slice of 6 integers, we are taking the first part of the slice, starting from the start to the first half. We are sending this 7 to 8 in the first function call. So we are trying to find the sum of the first half, and in the second function call, we are trying to find the sum of the second half. We are spawning these two go routines. Now this is the important part. We spawn two go routines and we pass this channel, we pass this tunnel, we pass this data type using which those go routines can send data to our main go routine. As I said that main itself is a go routine and all the go routines are spawned from main. And since we know that channels are a means of communication between two go routines, what we can do, we can spawn different go routines from main and we can use channels to send data, to send signals to our main go routine, to our main execution. And that's what we are doing here. We created a channel which is of type integers, which basically means we can only send integers to this channel. And we spawn two go routines which call two functions which are running concurrently with the main function. Now in this line, what we are doing, we are declaring two variables x and y, which is a short form declaration, and we are receiving data. We are again using this syntax. We are receiving data from this channel, which is the variable c, which we pass to these two function calls with the go routines. We are receiving from this channel using these two variables twice. So basically we are saying we want to receive two values. We want to receive two values from this channel, and then we are printing it. We are printing x, we are printing y, and we are printing sum. And if we run this, we are getting the sum of the first half, and then we are getting the sum of the second half, and then we are getting the result of x plus y, basically the sum of all the elements. Now, what are we trying to do here? First thing, we are trying to divide our work. We are trying to divide our work between two go routines. If we just call the sum function without spawning a new go routine, we just call the sum function in the main go routine. If we did that, then it will just go through all the elements and give us the sum. Now, since we know using concurrency, we can divide our work as long as the order is not specified. That's the important thing to remember. As long as the order is not specified, we can divide our work using concurrency, and we have go routines to implement concurrency. That's the reason we spawned two go routines and we divided our work. We called the first go routine with half of the elements and the second go routine with half of the elements. Then this is the important part. We waited, as I mentioned earlier, if the main go routine does not wait for all the go routines that were spawned from the main go routine, then the execution will stop. Then we will never find the result. So channels, receiving from a channel is a blocking execution. You should remember this. Receiving from a channel is a blocking execution. And since we tried to receive here twice, then we got the value of the first go routine, which tried to send some value into this channel. And then we got the value of the second go routine, which tried to send some value into this channel. And we received twice from this same channel. And that's the reason the main go routine did not end. The main go routine waited for these two go routines to end because of these channels. Now everything comes together. We have go routines. We have go routines to spawn, to divide our work, to have the capability of concurrency. And we have channels. We have channels to synchronize or to orchestrate or to communicate between these go routines, whatever you can imagine. There are a lot of use cases of channels. There are a lot of implementation, a lot of starting from basic to very complex implementation. And this is a very simple example of using channels to orchestrate different go routines, because of the property that in the main go routine. As long as you're receiving from a channel, it will block. Now we have two types of channels. One is called a unbuffered channel and the second one is buffered channel. And the high level difference between these two are, a buffered channel acts like a queue. We have a queue here, and if we have a buffered channel and we have a go routine, so the go routine can push values into this buffer or a queue. Let's say this size of this buffer is 4. So this go routine can keep pushing into this queue until the size is filled. So it can push 1, it can push 2, it can push 3, and it can push 4. And until the buffer is full, this go routine, whatever go routine it is, it can keep pushing into this channel and it won't have to block the execution. And on the other side, if there is another go routine which is receiving from this end, which is receiving from this same channel, then the whole workflow will go in a very nice way, because the producer, we can think of this go routine as a producer and this one as a consumer. The producer can produce at its own pace. It won't have to wait for the consumer to take out the data. It can keep pushing and the consumer can consume at its own rate. So there are no blockers here until the buffer is full. But in a unbuffered channel, we don't have a queue. We just have a tunnel. There is one go routine, which is the producer, and there is another go routine, which is the consumer. And this interaction will block. Let's say this go routine has a value to send, which is called 1. This is the value it wants to send. So until this receiving go routine takes this value, until both of these are in sync, until this tunnel is synchronizing, this interaction will block. So on a high level, as you can see, buffered channel has a little flexibility, and whenever we have a producer and consumer based scenario, when the pace of producing, the pace of sending is different to the pace of receiving or the pace of consuming, then we can go with a buffered channel. Or if we know the maximum size of this channel, if we previously know what is the maximum size of this channel going to be, how many values that we will be needing in future, in those cases we can go with a buffered channel. And since we have the construct of make, which provides some kind of capacity during initialization, as we saw with slices, as we saw with maps, in the same way, using make, we can assign a predefined capacity to a channel, and that channel will be a buffered channel. It will have a queue. It will have some kind of storage mechanism so that the interaction does not block. That does not mean that we should always use buffered channels. Sometimes we also need unbuffered channels, which causes the interaction to block. And because the interaction is blocked, unbuffered channels are mostly used for synchronizing. When the property of synchronization between two go routines are of utmost importance, or if we need the property of synchronization, if we need the property of blocking, then that's the scenario we go with unbuffered channels. We don't want any queue, we don't want any buckets, we don't want any storage mechanisms, we just want to synchronize two go routines. On a high level, those are two different use cases of unbuffered channels and buffered channels. And in this example, what's happening? We are creating a channel which has a capacity of 2, and we are using the make function to create this channel. And this 2 is basically the size of our queue. It can maximum push 2 elements, and until the buffer is full, until it has 2 elements, we can keep pushing to it. And that's what we are doing here. We are pushing the first value, we are pushing the second value into this channel, and in the print statement we are waiting for this value. Okay. And if you try to run this example, we get 1, 2 as expected, nothing special. We just explored this example to look at the two different types of channels. One is unbuffered channel, the second is buffered channel. Now in this example, we have a couple of new concepts. We can see there is one, we are using close the second one, we have a range. Instead of ranging over a string, instead of ranging over a slice, we are ranging over a channel. Now what's happening here? So we have some notion about Go routines and channels and the main Go routine blocking and all. Couple of properties to keep in mind while we explore this example is, first one, main Go routine has to wait until all the Go routines are finished executing, until all the values are received from the channel. Basically, main Go routine has to wait. Otherwise, the Go routines that has been spawned from the main Go routine, they will never finish executing. That's the first thing. Second, we already know that channels are used to communicate between two Go routines. They are some kind of tunnels to communicate between two Go routines. Now, in some scenarios, you might ask the question, if two Go routines are communicating, one is sending, one is receiving, or other one is receiving, other one is sending. In those scenarios, how will the other Go routine know that the sending has been finished? Or when will it stop receiving? When to stop waiting for values in this channel? That's the reason we have this function called close. And this function is a predefined function provided by the Go runtime, which is used to send a broadcast signal. A broadcast signal to inform the parent Go routine that the sending has been finished. We don't have any more values to send in this channel, so that you can stop receiving, you can stop blocking the execution. Those are the two concepts that we will focus in this example. Now what's happening here? We have a function which calculates the Fibonacci series, and it takes one integer and it calculates the Fibonacci series up to that integer. We already know what is the Fibonacci series. We basically have this series 0, 1, and you add these two numbers, we have 1, and you add these two numbers, you have 2, you add these two, 3, then 5, then 8, then 13. This is basically a Fibonacci series. It's a mathematics concept, and that's all you need to know. What is a Fibonacci series? What's happening here? This function basically calculates the Fibonacci series. It declares two variables x and y. They start with 0 and 1, and it loops until the number n, whatever you provided. How much to extend the series? That is basically the number n. It loops until that number, and in each iteration, it sends the current value. Basically, first it will send 0, then 1, then 1, then 2, then 3, then 5, then 8, then 13. It will send all these numbers in the Fibonacci series one by one into this channel. That's what it's doing overall. But in the end, it is calling close. So let's say we have provided the number 4 in n. What will happen? In the first iteration, the I will be 0, and it will send the value of I to this channel. So we have this channel, and this channel has the capacity of 10. It has the capacity of 10, so it can maximum hold 10 values at a time. As long as there is a receiver taking values out of it, it can hold any amount of value. But at a time, maximum amount of value without any receiver taking out values from it, it can hold 10 values. The capacity is 10. Now, first, this in the first iteration, it sends 0. It has 0. Then in the second iteration, I has 1. Then it sends 1. Then in the next iteration, 1, then 2, etc., etc. This is how it works. In the end, since our value of n is 4, and maximum it will run 0, 1, 2, 3, 4 times. It will run 4 times. After it is done, after this for loop ends, it calls close. Now, the reason we need this close is because after this loop ends, we want to inform the channel. We want to inform the main Go routine, or whatever the parent Go routine is, that we are done. We are not sending any more values. And that's the reason we need this close. And when we close this channel, it sends a signal to the main Go routine, and we'll see how that signal works. It sends a signal to the main Go routine that you now can stop receiving. You can now stop blocking. Now what happened here? It finished the loop, and in the end, it called close. Okay, that's done. Now coming back to this line. Here what's happening? We are ranging over a channel. Now in Go, you can range over a channel which does a couple of things in the background. What it does, when you range over a channel, it sequentially receives, it takes out values from those channel as the other Go routine is sending the values from the other side. It takes out values in that order from that channel until a close is called on that channel. Now those two properties work very nicely. The range loop on a channel basically does two things. It takes out values from a channel sequentially so that you don't have to manually take out one value. You basically do not have to run a for loop yourself. If we did not have this construct called ranging over channels, what you would have to do, you have to do a for loop and you have to keep the maximum range of that for loop as 10, and you'll do a traditional for loop and you will receive from that channel 10 times yourself. Now because of this construct called range, now we don't have that boilerplate code anymore. This basically ranges over this channel. It takes values serially from that channel as the other Go routine is sending values from the other side. And when the other Go routine calls close, it stops receiving. Okay, it stops receiving. The range also does this. The moment close is called on the channel, it stops receiving and will exit out of this main function. And what happens if we run this? We can see the Fibonacci series up to 10 integers as expected: 0, 1, 1, 1, 2, 3, 5, 8, 13, 21, 34. Okay, those are two new concepts. We can use close to inform all the Go routines that are receiving values from this channel that we have stopped sending values. Now you can stop receiving one thing, and we can use range to sequentially, serially take out values, receive values from a channel. Okay, those are the two things in this example. Because of our needs of synchronizing different Go routines using channels, Go also provides us another nice construct which are called select statements or selecting on channels. How does it work? Here we have a function called Fibonacci again, and it is taking two channels, one channel called C and another called quit, and both are channels of type integers. We can only send integers in this channel. Now initially it is declaring two variables, x and y, and it is doing all the x and y, and then it is doing an infinite loop. It is starting an infinite loop. As I said, as we have discussed before, if inside a for loop we do not have a condition, then it is by default an infinite loop. Now there is nothing to worry here. As I said initially during the start of the video when we were discussing for loop, there are uses of infinite loops in Go, especially in the concurrency section, and this is the first time we see it. We have an infinite loop here, and what's happening inside the infinite loop, which this infinite loop basically means this will not stop executing until there is an explicit return or an explicit break, and we have a return in this. Now inside this for loop we have a select statement. Now typically we use select to do different case checks and run executions depending on those case checks. In this area, in this application, what we are doing a select statement without any expression initially. There are no expression initially. There are two cases. First case, we are sending the value of x into this channel called C. This is the first case. This is an expression. As we already know, in select cases in Go, we can do expressions. It does not have to be constants like strings and integer. We can call expressions. And in this expression, we are sending the value of x into C. And inside that, what this basically means, if this is successful, if we can send it, then this gets executed. We assign y to x, then we assign x plus y to y. We also have another case. You'll see how these cases work together. We have another case where we are seeing if any value from quit comes. We have a quit channel, and if we receive any value, it does not matter in what value it is, as long as it's an integer. As long as we receive any value, any integer in this channel, quit channel, will print quit and will return, will break this loop. That's what's happening in this function. Now coming back to the main function, we are initializing one channel for C, another channel for quit. Both are of channels of integers. Then we are spawning a go routine. And this is another concept here of anonymous functions. In Go, since we know that functions are first class citizens, you also can use anonymous function calls. So you can just write Go instead of creating a function somewhere else, naming it, and then calling it here. You can literally define the function and call it at the same time. And it's called an anonymous functions. And what this function does, we are spawning a new go routine and we are calling this function in that go routine. What this function does, it loops from 0 to 10. So starting from 0 up to 9, loops from 0 to 9. And with each iteration, it receives from the channel C. It receives from the channel C in each iteration. Basically, it receives 10 times from the channel C. Then after the loop is finished, after we are done from 0 to 9, it sends one value, the value of 0, into the quit channel. As we said, quit can take any integer. So we are sending the value 0 into the quit channel. That's what's happening in this go routine. Then in the main go routine, we are calling Fibonacci. Now these two functions, Fibonacci, in the main go routine, we have the main go routine here. That's how execution is working. From the main go routine, we are spawning another routine, which is basically doing this for loop thing. This is happening here in another go routine. And these two are executed concurrently because of how go routines work in Go. Now, in order to communicate between these go routines, what we have channels that we have already discussed before. And how are channels working here? We have two go routines, and what's happening in this go routine? We have two go routines, one main and one that is spawned from main. In the main go routine that is being executed, which is basically here, this function call, what's happening? We are sending the value of X with each iteration. We are sending the value of X to this channel, to the channel C. Now, the way select works with channels is it checks different case statements at the same time. Of course, concurrently, but you can imagine they are happening at the same time. Now, because both of these checks are being run concurrently, what happens is, as long as we can send values to C, as long as we can send the value X to C, and because C is an unbuffered channel, and in the spawn go routine, we are receiving 10 times. In the spawn go routine, we are receiving 10 times. And since C is an unbuffered channel, here until we reach the value of 10, X can be sent to C. But the moment this for loop ends, this go routine sends a value to quit channel. And what happens? The moment it receives a value in this channel, the moment this case gets executed, it keeps checking both the cases at the same time. That's happening. But it is not coming inside. It is only coming inside because we can send value of X to C with each iteration of I here. So both of these are being run concurrently. It's a little hard to imagine it, and that's fine. Just try to follow me, and it's fine if it does not make any sense. It's just an example to show the use of select and how select works with channels. You don't have to exactly understand how everything is working. You just have to understand the concept that we have a select block and we can orchestrate channels using selects. Now, we are just going through concepts. You don't have to master concurrency at this phase. Okay. Now, both of these are being run at the same time. And the moment this block is true, the moment this block satisfies, the moment we receive some value in this channel, because we are trying to receive from this channel using this syntax, the moment it happens, we come inside, we print quit, and we return. This loop breaks. And the moment this loop breaks, we get out of the main go routine. As I said, the moment you get out of the main go routine, all the go routine stop executing. Okay. Now, what happens if you print this? Let's print this. And as you can see, with each iteration, we are receiving the value of x into this, and we are printing it 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. And in the end, the moment we send the value 0 into quit, it reached here. This statement became true, and it came inside, it printed quit, and it returned, and this loop broke. And the moment this loop broke, we came here and we exited out of main go routine. And that's the end of our program execution. Now, this example was just to demonstrate the use of select case and the use of the infinite for loop and how they work in the concurrency space. Now, for us to understand how select works in a much deeper way, in a little deeper way, we have another example. What's happening here is we have one variable called tick, and it is using the standard library package time, and time has different functions for different things. Tick basically provides us a channel. So these two variables are channel types. They are provided to us by this function tick and this function after. Now what's happening here is what we're saying, every 100 milliseconds, this tick function, because we initialize this variable using this tick function, every 100 milliseconds, this channel will get triggered. Will receive a value in this channel every 100 milliseconds. So it is kind of an interval running. Every 100 milliseconds will receive a value in this channel. Any value, does not matter. It's just an interval counting. Now we have a second variable called boom. And this channel, what we are saying, after 500 milliseconds, send a value to us using this channel. This sends a value every 100 milliseconds. This sends one value once after 500 milliseconds. Now what's happening? We have the same infinite for loop and select case construct here. We are blocking here with this for loop. So this main go routine will not exit. This main go routine will not end unless we break out of this infinite for loop. That's the use of it. And what's happening inside this interval? What's happening inside this infinite for loop? We are doing the select case. Inside selects, we have three cases. One case, if we receive a value in the tick channel, will come inside and will print this. If we receive a value in the boom channel, will come inside, will print this and will exit. We'll call return. The moment we call return, we exit out of this for loop and we exit out of this main go routine and the program ends. So this is our ending statement. The moment we receive a value in this boom channel, we will exit out of this for loop and we will exit out of this main go routine. But there is another case here, which is the default case. And this is provided by select. If this is false and this is false, we will reach here. So this is an iteration. We are inside a loop. So we are going through infinite iteration. We are repeating the cycle. In one iteration, it checks this. Then it again starts, it checks these, again starts and it checks these. That's how it works. So in every iteration, if this is false, then it executes this. Again, in the second iteration, if this is false, it executes this. In the third iteration, if this is true, then it executes this and continues to the next iteration. That's how this infinite for loop and this select case works. Now, in the default case, what happens? We print this and we sleep for 50 milliseconds. We block the execution for 50 milliseconds. Okay. Now, when we executed it, this is what we got. Since we said we send us a value every 100 milliseconds, in the first iteration, 100 milliseconds is not done yet. That's why this is false. And this is of course saying send us a one value after 500 milliseconds. So this is also false. That's why we reach the default case where we print this dot. That's why in the first iteration, we see this dot and we sleep for 50 milliseconds. Now we sleep for 50 milliseconds. Now, when we reach here, second time, at this point, we in the first iteration, we run the default case and only 50 milliseconds is done. Now, in the second iteration, what happens? We again come here, we check if we receive a value from tick, it is only 50 milliseconds. We only receive a value every 100 milliseconds. That's why this is false. This is obviously false because it's only been 50 milliseconds. We will only receive a value after 500 milliseconds. Okay. Now this is also false. We again reach the default case and we again printed dot. Then we again sleep for 50 milliseconds. Now it is 100 milliseconds. In the third iteration, when we come here, in the third iteration, the 100 milliseconds is over now. Now we should get a value in the tick channel. That's why in this iteration, in the third iteration, this is true. That's why third time we printed tick. We came inside this, we printed tick. Okay. And this is how it works. In the fourth iteration, again, we'll receive another value after 100 milliseconds. And it has only been 100. So in the fourth iteration, we still have 100 milliseconds more to wait until we'll receive a value in the tick channel. And the boom channel is obviously due for another 400 milliseconds. Okay. So that's why we reach default here. And we print a dot here. Then we sleep for 50 milliseconds. Then we, in this next iteration, of course, it's only been 150 milliseconds. So we again reach the default case and we print this dot and we wait for another 50 milliseconds. In the sixth iteration, again, it's now 200 milliseconds over. So we reach the second cycle of this tick channel. Now we'll receive a channel in this tick channel because it's been 200 milliseconds is the next iteration of getting a value from tick. That's why we printed tick again. And we continued the loop. In the next iteration, again, it will reach default and so on, so on, so on, so on, so on, until in the 15th iteration. In the 15th iteration, we reach here. This is false. It's not been 100 milliseconds before, after the previous iteration. And we reach here. Now it's been 500 milliseconds and this sends us a value. Now this case becomes true. And the moment this case becomes true, we come inside, we print this boom and we call return. And because we called return, we break out of this infinite loop. And the moment we break out this infinite loop, we reach here. And this is the end of the main function. And the moment we end the main function, our program stops executing. That's why this is the result we see. Now here we have a struct. Inside the struct, we have a field called v, which is of type map. And in this, the key is string and the value is integer. And this struct has two methods. One is increment and one is value. Increment basically mutates the value of the map and we are using pointer receiver so that whatever mutation that we are doing here, it shows up in the original instance. And this value method returns the value of that key. Okay, that's this part. In the main function, what we are doing, we are initializing this struct with make function for initializing the map, and we are starting a loop. And this loop will run for 1000 times. This will run for 1000 times, and in each iteration, it spawns a new go routine. It spawns a new go routine which calls the increment method for this key. And this thing happens for 1000 times. So ideally, 1000 go routines are spawned from the main go routine, and each go routine increments the value of this map for this key. In the end, we are calling time.sleep because, as we already know, if the main function exits, we will never see the results of the spawned go routines. That's the reason we are simulating. We are simulating the blocking of the main function. Ideally, we should use a channel or a wait group. We have not explored wait groups yet, but we'll explore them later. We should ideally use a channel or a wait group to block the main function. But for the sake of this example, we are using time.sleep to block the execution of the main go routine so that we can see the results of all these 1000 go routines. And in the end, we are fetching the value of this key from this map. Now, ideally, what should happen? 1000 go routines are spawned and all of them are incrementing the value of this key. So ideally, it should start from 0 and by the end, it should have the value 1000 because we spawned 1000 go routines and each go routine incremented the value by 1. Ideally, we should have 1000. But what happens if we run this? When we run this, we get this error. And when we go to the top, it says concurrent map writes. And what that means is we spawn 1000 go routines and all the go routines are trying to access. They are trying to write a value to this map in an unspecified order. And because of that, Go was able to detect that there is a problem in this program. When you are working in the space of concurrency, you have to constantly think about orchestrating state between your go routines. So this is a classic example of that. You have different Go routines, in this case 1000 Go routines, and all of them are trying to mutate a value in an unspecified order. And to prevent this case, to prevent this exact scenario, we have a construct which are called mutex. Mutex, basically it's a concept from operating system. If you have studied mutex, what they do, they are basically gatekeepers. They keep the gate, they have an entry point and an exit point, and whatever happens in this area, which is called mutual exclusion area, whatever happens, this is safe from concurrent access, so that only one Go routine at a time can access this area. It does not matter how many Go routines you have. In this case, we have 1000 Go routines. Even if you have million Go routines at a time, only one Go routine can access this area. Okay. And the moment it unlocks, at this point it locks, and this point it unlocks. After it unlocks, another Go routine can acquire this lock, and it can do something, and it can then unlock. And with this flow, now we are safe from multiple Go routines, all of them trying to concurrently mutate the value of a map. Now what happens? How can we fix this? For this exact use case, Go provides us this package called sync, and inside this sync, we have this value called mutex. Now, inside the same struct, we add this another field called mutex. And now what we do, in the increment method, we lock it. At the start of the execution, we lock it, and we mutate the value. After you mutate the value, we unlock it, so that this is the mutual exclusion area at a time. Does not matter how many Go routines are trying to access this, how many Go routines are trying to call this increment method. At a time, only one Go routine can get inside this area. And at a time, only one Go routine can call the increment function successfully. If not, other Go routines will have to wait for acquiring this lock. And only after that Go routine unlocks it, another Go routine can acquire the lock, and it can mutate this. In the same way, if we have the value function, and this value function acquires the lock, and it defers the unlock function. As we already know, we use defer in different scenarios, so that it does not matter when the function ends, in what scenario that function ends. Before the function returns, before the function ends, Go will automatically call this function, because we added defer here. That's what we are doing here. We are acquiring the lock, and we are saying before this function returns, unlock it. So we are not exclusively guarding what the area is. We are just saying we want to acquire the lock when we enter, and we want to unlock it when we return from this function. And in the mutual exclusion area, what it is doing, it is getting the value for that key. Okay. Now we have concurrency safe mutation and concurrency safe access for this map. What happens when we run this now? Let's run this. And as you can see, we have our expected result of 1000. We spawned 1000 Go routines, and all of them incremented the value for this key once. And in the end, we have the value 1000. And we were able to do that in a very predictable manner, in a very systematic manner, because we have this construct provided by Go for mutual exclusion, which is called sync.mutex. We can guard the access of Go routines using mutexes, and that's what mutexes are used for. And with that, we have covered all the examples of the tour of Go with the end of concurrency. Now, this is by no means a very comprehensive or even a very correct approach to teaching the basics of Go. I might have made a lot of mistakes. I might have confused you even more. And I have definitely missed a lot of concepts. I have missed reflection, and we have missed different channel types, the receiver types of channels, the sender types of channels. And there are still a lot of concepts in Go that I have definitely missed, because they were explicitly not mentioned in the tour of Go, which is the guide that we followed in this video. Now, the idea is you do not have to reach 100% in this video. My goal with this video was to get you to 10%. Even if you were able to retain 10% of what we did in this video, and because in the initial part of the video, I especially asked people to cover tour of Go on their own, to do all the exercises, to get the feel of the syntax and to try to understand themselves. And hopefully with this narrative, with this video, I was able to add some value after you did it on your own, with all my insights and all my examples and all my explanations. Hopefully you have reached 10% in the basics of Go. And if you have, then this video was successful for you. And even if you have not, then that's also fine, because we have a lot of content. We have a lot of content planned for our journey with Go. And if you watched the first video, we are going to explore more content from the official documentation. We are going to explore effective Go. We are going to explore modules reference. We are going to read the language specification and how to write Go code. A lot of documents from the standard documentation. We are going to read the code from the standard library. We are going to read the code from a lot of open source repositories, a lot of open source production grade repositories, actual backends that run businesses. And then we are going to build projects. And throughout this journey of doing all of these things, hopefully this 10% will get to 70%. And by the time you reach 70%, you will be very comfortable with the language. You will be able to build actual production grade backends with the language.